ଯାହା ତଳେ ଏଠି ପଚାରି
Eminent American astronomer and planetary scientist Carl Sagan once said, "Somewhere something incredible is waiting to be discovered. Science is the vessel through which we navigate the unknown, driven by curiosity and wonder at universe's endless possibilities."
Rightly said. The pursuit of science today is not about certainty, but about embracing doubt. It teaches us that discovery is a journey, not a destination, and that every question answered opens the door to new mysteries. Good morning, everyone. I am Disha.
And I am Stuti, and we welcome you all to the 38th Annual Conference of Orissa Chemical Society and National Conference on Advancements in Materials Chemistry. As a core pathway to science, materials chemistry stands at the forefront of numerous scientific revolutions, driving advancements that impact everything from energy storage and electronics to healthcare and environmental sustainability. As we stand at the crossroads of these exciting breakthroughs, we are reminded of the crucial role that chemistry plays in shaping a more sustainable and technologically advanced world. The journey of innovation in materials chemistry is not just about creating new substances, but about reshaping the very fabric of the society.
Over the course of this conference, we will be delving into the latest research, innovations, and applications that are transforming the landscape of materials chemistry. From new materials for clean energy solutions to the latest in nanomaterials, we are set to witness discussions that will inspire and inform, paving the way for future breakthroughs.
And with this in mind, today, Odisha University of Technology and Research takes the solemn opportunity to welcome you all to the prestigious 38th Annual Conference of Odisha Chemical Society and National Conference on Advancements in Materials Chemistry for the year 2024. It aims to explore the cutting-edge developments in chemical sciences that are shaping the future of materials science, bridging the realms of innovation, sustainability, and technology. As we embark on this journey of discovery and intellectual exchange, let us keep in mind the impact of our collective efforts. The insights and innovations shared here today have the potential to shape not just the future of science, but the future of society as a whole.
Now, I invite all our distinguished dignitaries to please come to the dais. Our chief guest, Honorable Minister Shri Jukta Krishna Chandra Patra, Food Supplies and Consumer Welfare, Science and Technology, Government of Odisha, to please come to the dais. I invite guest of honor, Professor Vibhuti Bhushan Biswal, Vice Chancellor, Odisha University of Technology and Research, to please come to the dais. I request the President, Odisha Chemical Society, Professor Ajay Kumar Behra sir, to please come to the dais.
Then I request the Secretary cum Treasurer, Odisha Chemical Society and the Patron of National Conference on Advancements of Materials Chemistry, Professor Achyutananda Acharya sir, to please come to the dais. Then I request the convener of our 38th Annual Conference of Odisha Chemical Society and Advancements in Materials Chemistry, Professor Vigyan Ranjan Das sir, to please come to the dais.
The lamp symbolizes the removal of darkness, ignorance, and despair, and the illumination of wisdom, peace, and prosperity. Let us invoke divine blessings as we light the lamp and mark the beginning of this beautiful event. May I now invite the distinguished guests on the dais to kindly join us for the lamp lighting. of flowers. It is a symbol of our heartfelt emotions and appreciation for their presence. Let us now proceed with this beautiful tradition of extending our greetings.
May I now request the student volunteers to present the bouquet to our esteemed guests. With this warm and fragrant gesture, we extend our heartfelt gratitude to our esteemed guests for gracing us with their presence. May this token of respect and appreciation set the tone for a truly memorable day ahead.
Music gives a soul to the universe, wings to the mind, flight to the imagination, and life to everything. A melody has the power to touch hearts, uplift spirits, and create a connection that words alone can never achieve. To welcome you all with warmth and joy, we present the state anthem that resonates with the very spirit of this occasion. May I request all to please stand up for the state anthem.
What a magnificent start to our event. Let us thank our student volunteers for their captivating performance, which has infused this gathering with warmth and positivity.
Orissa Chemical Society joins the nation in paying heartfelt homage to the departed noble soul of late Manmohan Singh, former Prime Minister of India. This country will be commemorating him forever for his visionary leadership, unwavering dedication, and for being a source of inspiration to strive for a better future for India. Let us all stand together to observe a minute of silence for this great man.
Family members Professor Ilarani Patnaik, Dr. Arun Kumar Rai, and Professor Vaishnav Charan Singh and Dr. Sashi Bhushan Mahanti have left us for their heavenly abode during the year 2024. I now request all the dignitaries and members to rise and observe a minute of silence for them.
Thank you all. The President of the Odisha Chemical Society presides over the inaugural function. Every successful event requires the guidance and wisdom of a capable leader to steer its course effectively. On this occasion, we are privileged to have with us the Honorable President, Odisha Chemical Society, Professor Ajay Kumar Behra sir, whose guidance will ensure that its purpose is fulfilled with his clarity and direction. Sir, your guidance will undoubtedly add immense value to our deliberations.
The future belongs to those who believe in the beauty of their dreams. As the driving force behind this event, Professor Vigyan Ranjan Das Sir, Head of School of Basic Sciences and Humanities, and the convener for this 38th Annual Conference of Odisha Chemical Society and National Conference on Advancements on Material Chemistry, has also worked tirelessly to bring this gathering to fruition. It is only fitting that we begin by hearing from him. I request the audience to put their hands together and join me in welcoming Professor Vigyan Ranjan Das Sir to deliver the welcome address, followed by introducing the distinguished guests and invited speakers. Sir, please.
Good morning, one and all. Chief guest of the program, Sri Yuta Krishna Chandra Patra, Honorable Minister of Food Supplies and Consumer Welfare, Science and Technology, Government of Odisha. Guest of honor, Honorable Vice Chancellor of OUTR, Professor Bhubaneswar, President of Odisha Chemical Society, Professor Ajay Kumar Behra, Secretary cum Treasurer, Professor A.N. Acharya, former Presidents, Executive Members of Odisha Chemical Society, Deans, Heads of Schools of Departments of OUTR, faculty members, student participants, members from print media. On behalf of organizing committee, it's my pleasure to welcome you to the 38th Annual Conference of Odisha Chemical Society and National Conference on Advancements in Materials Chemistry. It's said to unfold in the historic temple city Bhubaneswar. I take immense pride in welcoming the chief guest for today's inauguration ceremony, the Honorable Minister for Food Supplies and Consumer Welfare, Science and Technology, Government of Odisha, Sri Krishna Chandra Patra. I extend my welcome to our guest of honor, Professor Vibhuti Bhushan Vishwa, the esteemed Vice Chancellor of Odisha University of Technology and Research, and the Patron-in-Chief of this conference. I also welcome the President, Orissa Chemical Society, Professor Ajay Kumar Behera, and Secretary cum Treasurer, Professor A.N. Acharya, Dean Academics OUTR and Patron of this conference to this August gathering. I heartily welcome the former presidents, the patron members, the executive committee members, the light members of this. It's my pleasure to invite professionals from academia and industries, research scholars and students from various institutes. Last but not the least, I welcome friends from print and electronic media who have gathered here to cover the occasion. The theme of this conference, Advancements in Materials Chemistry, aims to serve as a platform bridging the gap between academia and industries. This event looks for further improvement of global chemistry in its very broad scope of fields, trends and applications including canonical organic, physical and inorganic chemistry, analytical chemistry, medicinal chemistry, biochemistry and associated drug discovery, polymer chemistry, surface chemistry and even quantum chemistry. The event highlights the multi and interdisciplinary nature and very broad scope of materials chemistry and engineering and will provide all participants a catalytic opportunity to exchange ideas, learn from each other and initiate collaborations. One of the key features of the conference is to exchange breakthrough ideas in the field of materials chemistry to promote top-level research by focusing on the recent trends. In this context, design and synthesis of new materials would be one of the most important part of global chemistry. Those perspective aspects will provide us with new angles to look at the chemistry in the upcoming decades and inspire the development of new methods, technologies and strategies to illustrate the chemistry as a core element of a changing world. Keynote speeches will be delivered by distinguished experts from academic and research institutions, oral and poster presentation by delegates as well as by young junior participants during the course of the conference. The flagship category of OCS, that is the memorial lecture, will continue to thrive in this year's conference. OCS has instituted 4 memorial lectures to be delivered by distinguished professionals in the field of chemistry during the annual conference every year. This year, Professor Mahendra Kumar Raut Memorial Lecture that is dedicated in fond memory of Professor Mahendra Kumar Raut, the founder president of the OCS, shall be delivered by Professor Iris N. Number 3, IIT Bombay. Professor S.R. Mohanty Memorial Lecture that is dedicated in loving memory of Professor S.R. Mohanty, former professor and head Department of Chemistry, Utkal University, will be delivered by Dr. Sandeep Basu, Homi Bhabha National Institute, Mumbai. Professor Gangadhar Sahu Memorial Lecture instituted in fond memory of Professor Gangadhar Sahu, former president of OCS, shall be lectured by Professor T.P. Radhakrishnan, School of Chemistry, University of Hyderabad. Lastly, OCS has instituted CPET-sponsored Professor Padmalochan Naik Memorial Lecture in the fond memory of Professor P.L. Naik, an accomplished researcher of polymer science. This memorial lecture will be delivered by Professor Arun K. Nandi, Eminent Scientist, School of Material Science, IACS, Kolkata. This event is also graced by eminent speakers from various IITs, NITs, Central University, IJR, ILS, etc., focusing on energy generation and storage, environmental application, design and application of polymers, materials in biomedical application, and many more. As we see, speakers from various fields are participating in this conference. The platform of this conference is vast and encompasses diversity. This conference will provide excellent opportunity to establish highly productive relations and collaborations for future research and projects. So, your participation and contribution are fundamental to the success of this conference. Together, we aspire not only to deepen our collective understanding, but also to propel innovation in design-driven materials chemistry. Last but not least, my deepest gratitude goes to Professor Bhubaneswar, the patron-in-chief of this conference, the advisory board, organizing committee, companies and volunteers who have directly or indirectly paved the path to conduct the conference smoothly. The committee has organized a vibrant scientific program and is working hard to present esteemed speakers to lead it. Although we try our finest to be professional, on behalf of OUTR, please accept our sincere apologies should there be any inconvenience that occur before, during or after the event. I wish you a very productive conference with exciting and encouraging discussions and exchange of knowledge so that together we can anticipate a future of groundbreaking knowledge, research and technology for humanities. Thank you.
Thank you so much, sir, for your inspirational words and for welcoming the distinguished guests and invited speakers and delegates.
Established in 1985 with the support of several eminent figures who shaped the vision for advancement of modern chemical science, the Orissa Chemical Society is a distinguished institution that has continuously promoted and improved the standard of teaching and research in chemistry and allied sciences in Odisha. To know more about the institution and the objectives that drive it forward, I extend my heartfelt welcome to Secretary cum Treasurer, Orissa Chemical Society, Professor Achyutananda Acharya Sir, to present the report on the activities conducted by the OCS in 2024.
Very good morning to all the delegates. Esteemed Chief Guest, Sri Krishna Chandra Patra, Honorable Minister, Food Supplies, Consumer Welfare, Science and Technology, Government of Orissa, respected guest of honor, Honorable Vice Chancellor, Professor Bhubaneswar, respected President, Orissa Chemical Society, Honorable Professor Ajay Kumar Behera sir, my colleague, Professor B.R. Das, Convener, Orissa Chemical Society, and Advancement in Material Chemistry. My revered teachers, esteemed former presidents, distinguished guests, invited speakers, delegates, researchers, scientists, students, members from the press, print and digital media, ladies and gentlemen. It's my privilege and I feel honored to present the report of the activities of Orissa Chemical Society conducted during last 1 year. The Orissa Chemical Society stands as a beacon of scientific excellence in teaching and research in the frontier areas of chemical science in the state. It was conceptualized in 1985 at Sambalpur University's School of Chemistry and formed in 1986 by late Professor Mahendra Kumar Rao as the founder president. The Orissa Chemical Society has flourished over 38 years, boasting of more than 1200 life members and 200 patron members. It was established with a mission to promote chemistry education in Odisha and inspire advanced research in the field of chemical sciences. The Society's dynamic activities, from regional conference to prestigious annual conference, nurture a vibrant community passionate about chemistry. These events showcase pioneering research, conferring awards to exceptional contributors, and recognizing outstanding students. The OCS has expanded its horizon to include higher secondary education at the +2 level, organizing Olympiads in chemistry known as OLYChem to ignite young minds. In addition, programs such as 2-day regional conference, OCS 1-day extended lecture series, OCS Industry Interface Meet are included in its activities to broaden the domain of OCS to achieve its goals. The Executive Committee of 23-24 was formed during 37th Annual Conference held at Ravenshaw University, Cuttack. It's privilege and I feel honored to act as Secretary cum Treasurer for this term, serving in the role of Odisha's oldest vibrant scientific society. OCS this year under the leadership of Professor Ajay Kumar Behra, President, who assumes the presidency, embarks on its journey forward. A total of 16 office bearers of the OCS Executive Committee for 2024 was formed. Throughout this year, we have fervently fulfilled our responsibilities by organizing various activities. Our efforts included orchestrating 1 2-day regional conference, 2 OCS 1-day extended lecture series, Polychem 24, and conducting our annual conference alongside our regular engagements. The OCS honors excellence in teaching and research in chemistry by conferring several awards every year. For selection of awards this year, and 5-member award committee was formed consisting of 4 former presidents and senior professor Dr. A.K. Mishra at Madras. This year, a record number of applications were received from Odia students and faculty members nationwide for different awards, for which the award committee meeting was held for 2 days for the first time to nominate the award winners. 14 award winners are nominated for various awards. In addition, 2 awards, that is Professor R.K. Nanda, Best Oral Presentation, Professor Subhash Singh, Best Poster Presentation. It will be awarded during the valedictory function. Further, another 2 awards were given, that is Sarath Chandra Science Promotion Award and a Best Graduate during 2-day regional conference held at Panchayat College, Bargarh. The synergy between curriculum and research trends forms the bedrock of innovation. Aligning academic syllabi with cutting-edge research not only equips students with contemporary knowledge but also foster curiosity, critical thinking, and adaptability. The 29th 2-day regional conference was organized at Panchayat College, Bargarh on 16-17 November 24, and the theme of this was Recent Advances in Chemical Sciences, wherein speakers are invited from academia, DRDO labs, industry, etc. It truly inspired the regional teachers, researchers, students to reorient their teaching and research activities. In 2024, 2 number of 1-day extended lecture series was organized. The 5th 1-day extended lecture series was organized at Bhadrak Autonomous College, Bhadrak on 29th November this year with a national seminar on new trends in chemical sciences. Similarly, the 6th 1-day extended lecture series was organized at Rajendra University, Balangiri on 11th December 24, along with a national seminar on frontiers in chemical sciences. In addition, the 2nd OCS Industry Interface Meet 24 on the theme Bridging Academia and Industry, Advancing Chemistry for Sustainable Innovation was organized at KIT DMD University on December 7, 24. This year, 8-member Polychem committee was formed to pursue and oversee the conduct of Polychem examination. The Polychem 24 examination was held on 3rd November 24. It is worth noting that 3,856 students of Frost 2 registered for Polychem and 3,196 students appeared at Polychem 24 at 50 different centers, which is highest in OCS history to date. Notably, this year all the Polychem registration fees were collected only through online mode and the expenditures were also made by check. Since last OCS General Body meeting, 4 of our revered teachers have passed away, and they are Professor Ilarani Patnaik, Professor Arun Kumar Rai, Professor Vaishnav Charan Singh, and Professor Sasi Bhushan Mohanty. They will be remembered for their remarkable contributions to teaching and research in chemical sciences, along with their administrative responsibilities. This year, the 38th annual conference of Odisha Chemical Society is dedicated to 4 teachers. They are Professor D.V. Raman Rao, Sri Gopinath Rajapati Narayan Deo, Dr. Jagannath Prasad Nath, Professor Ilarani Patnaik. And in this annual conference, we have received 152 number of abstracts from the different research scholars and junior faculty members. Along with these, 4 memorial lectures, 10 award lecture of OCS, and 15 invited lectures are also included. And we feel honored, and it is a joyous moment for all of us that in today's inaugural ceremony, we are felicitating our teachers who are above 85 years and those have outstanding contribution in research, administration, social work and also sports arena. Our sincere gratitude extends to Honorable Minister Srijukta Krishna Chandra Patra, Food Supply and Consumer Welfare, Science and Technology, Government of Orissa, for graciously accepting our invitation as chief guest at the inaugural meeting. Sir, your presence will definitely boost to our endeavors. With heartfelt gratitude and humility, on behalf of the OCS, I extend my thanks to the organizers of OCS Annual Conference. I also extend my sincere thanks to Professor Bhubaneswar, the Honorable Vice Chancellor of Orissa University of Technology and Research, for his unwavering source of inspiration and guidance. My special thanks to all the officials of the university, deans, heads, PICs and staff members of this university for their valuable support for organizing this conference. I sincerely extend a warm note of gratitude to Professor Vigyanathan Das, the conference convener, and he is also the joint coordinator of OLICAM 24 and head of School of Basic Science and Humanities, Orissa University of Technology and Research, and a heartfelt thanks to him and his team, including all faculty, staff members of Department of Chemistry, other staff members at this university for successfully organizing the OLICAM 24 and this annual conference. The conference esteemed speakers aim to foster scientific curiosity among young researchers and students. Therefore, they deserve special thanks. Lastly, I extend my thanks to all supporting staff whose hard work ensured the grand success of this meeting. We have successfully executed all the annual events of OCS more efficiently and with enhanced professionalism and following new protocols. The talks covering the advanced areas of research in chemical sciences, including material chemistry, will definitely boost our young researchers, teachers and students to build their successful careers. I am confident that the delegates will find this annual conference a memorable and exemplary one from the valuable academic deliberations and exchange of ideas. I express my profound thanks to Professor Ajay Kumar Behera, President Orissa Chemical Society, most simplest and innocent individual whose support and guidance have made all the activities of this society in successful manner. My heartfelt thanks to all the esteemed former President of Orissa Chemical Society, all the members of the Executive Committee, all the members of the Award Committee and OLICAM Committee for their relentless support and valuable contribution to the Orissa Chemical Society. The students, our strength and future, played a vital role in the conference success and deserve commendation. Heartfelt thanks to members of the press, print and digital media for covering this academic conclave. Thank you all for your wholehearted and valuable support and contribution. Vande Utkala Janani.
Thank you for your insightful words, sir. It has been a privilege to know that the annual activities of the OCS are organized most efficiently.
It is with immense pride and profound respect that we welcome a luminary whose accomplishments and brilliance have illuminated the path for many. We are truly honored to be graced by the presence of our esteemed guest of honor, Professor Bhubaneswar sir, who has been a beacon of inspiration to many as the first Vice Chancellor of Orissa University of Technology and Research. His valuable insights and visionary leadership have made a profound difference, and we are eager to hear his thoughts today. With utmost respect, I take the pleasure of inviting Professor Biswal sir to deliver the address and share his wisdom with us. Sir, please.
Good morning, everybody. On the dais, Honorable Minister, Civil Supplies, Consumer Welfare, Science and Technology, Government of Orissa, Sri Krishna Chandra Patra, the President of Orissa Chemical Society, Professor Ajay Kumar Behra, the Secretary and Treasurer of OCS, my colleague, Professor Acharya, the convener of this function, Professor Vigyan Ranjan Das, executive members of Orissa Chemical Society, all the members of Orissa Chemical Society, the distinguished personalities, and who is rule of chemistry of our state. The participants of this annual conference, my dear students, friends from print and electronic media, ladies and gentlemen. It's a matter of great pride that this annual conference and the convention of OCS is happening here in my university. I'm grateful to OCS and I'm thankful to my colleague, Professor Acharya, who did bid for conducting this annual conference in the premises of Odisha University of Technology and Research. 1 year back, when he told me that, sir, we are bidding for this conference to happen in OUTR, I was more than happy to say yes without any second thought. I'm happy and thankful to the Honorable Minister who has put his feet in the lands of OUTR today. He has agreed and he has elevated the very significance of this conference and OCS convention in our university. Friends, before coming to this hall, we had a little bit of chit-chatting in my chamber, and Honorable Minister was saying that he understands science only by chemistry. This chemistry, over a period of time, if you go back to the history, we start with chemistry, and today we also think of chemistry. Tomorrow we shall be thinking of chemistry. This is a University of Technology, OUTR. Technology, I believe, and it's a fact, is based on strong foundation of science. In the first meeting that I had here with my faculty colleagues, I told that I want to make the science base stronger here. See, today I have not been able to do that, but my wish is to make the science base stronger. If you do not understand science properly, you cannot work on any technology. And that too, chemistry is such a subject that it is the most difficult, most confusing, and most interesting sometimes, and last but not the least, it's the most powerful subject. Powerful, I mean, chemistry can save your life. chemistry can destroy your life, not life. Chemistry can destroy the entire world. So be cautious when talking about chemistry, but not chemistry. So I won't be talking much about chemistry. I don't know which direction I'll go. Think of life-saving elements. Like, the pharmaceutical industry, they develop a lot of medicines for us. Today we are talking about development of cancer medicine, the most dreaded disease in the world. And it is because of success in chemistry research. Think of pandemic like corona. The vaccines were developed because of the research in chemical science. Think of chemical weapon. That is the power of chemistry. It can save life, it can destroy the entire world. That's what I mean. In our life, in our professional life even, if you look at any industry, for that matter, any industry including IT industries, forget about processing industries, metal industries, pharmaceutical industries, food processing industry, whatever. Chemistry is a must. Without chemistry, you just cannot develop any kind of thing, and industry has been in the bottom of any civilization. We are talking about industry 4.0. We are talking about industry 5.0. And this has come into being, or this should be coming to our life because of developments and research in science. And chemistry plays a major role in it. I have certain, things to, when I was sitting here, and some of your executive members approached Honorable Minister for creating an institute of chemistry in Orissa. I just got reminded of my experience at different institutes that I have worked, I have been to and seen the chemistry people. I don't know, in my intermediate time I was very fond of chemistry. And I find a very good thing in chemists that they talk about chemical bond, and their bond is also very stronger. I don't know out of what they make the bonding between them, bonding between the members. The bonding in chemistry is very, very strong. I mean, the people of chemistry is very, very strong. You go to any chemistry department of any college or university, you will find a very good relationship between the members out there. And probably for that matter, this room has been insufficient, inadequate to accommodate all the invitees. Professor Acharya was saying that some people were willing to come today. He requested them to come tomorrow because he couldn't accommodate all the people out here. So that is the kind of bonding, love, affection towards the society by chemistry. I was talking about the different institutes I have visited. If you look at here in Orissa, some years back, like 30 years back, 35 years back. So there are great personalities, including some of my teachers, who worked in the area of chemistry, and they were institutions by themselves. And they created a lot of things around them, a lot of products were available today. But the matter of surprise, you can say, regret, you can say, that today, if I look at different first rung, second rung institutes today. We have very few Oriya chemists in place. I worked in two national level institutes, and there I found Professor Sahu is very much here. I visited the IIT Kharagpur very often. I know him, and he knows his students very well. He is so fond of his students. Now I find in even Orissa, in national level institutes, you will hardly find any Oriya chemist working, Oriya chemistry faculty working. I am talking of only eastern part of India. And you find mostly the Bengali people, they have, engrossed our field, not the right word, and they have created a market, they have created a value in them, so that when they come in competition, they come up successful. And we fall behind. Over the time this has happened in the field of chemistry, in the research and education of chemistry in Orissa. This is because I can attribute this reason to different good institutes in West Bengal and Kerala. I had spent some 4.5 years in Jadavpur University. I had also, as I said, I was working in a field which also related some of the chemistry kind of thing. Visited Presidency College, now Presidency University, Calcutta University. Around Jadavpur University, there are few institutes like IACS, Indian Association for Cultivation of Science, Institute of Chemical Biology, Institute of Chemical Engineers, all around that. So everywhere you will find chemistry research at a higher level is going on. And today, if you look at the university, general university research, we are not able to fund the research properly. Even I find difficulty in providing proper support to my chemistry department here, so far the consumables are concerned. Talk about research, because this is essentially a teaching university. A bit of research is happening, but research has to happen in a larger scale, in a higher level, and for that we need a focused type of institutes like IACS or ICB, and even those institutes you find a lot of good chemists out there. So because of that, they are getting trained, the Bengali people are getting trained, and they are taking the market out of other people. In the competition, you will find a lot of good research happening out there, which is not possible in general universities. So what I mean to say, we need to have a similar kind of institute in our state as well. A focused institute which will cater to the needs of the researcher, which will promote, high level of research, and which will create people to be at par with the national level at least. So that is what is the demand of the day. Yeah, actually. So actually that is what I feel. Already a document has been handed over to the Honorable Minister, and he has been very happy, very kind, very magnanimous in accepting that and assuring that, yes, it will happen here in India, say in Orissa. In Orissa, if you find other institutes like, there are many like Institute of Physics, Institute of Mathematics, Institute of Life Science. So all these institutes are there. And probably we had big luminaries in chemistry, still some are there. But they work like individual institutions. Probably for that, they didn't think of establishing a separate institute of chemistry. But time has come, we should think of it. and we should try sincerely to establish here in Orissa state as well. So, as I was saying, that you go to any field, there was an advertisement, caption going like, in everybody's life, there is a little bit of chemistry. Okay, one thing, if you can see the logo of our university, OUTR. So we designed it here, we gave input. Since it is Orissa University of Technology and Research, there should be something very stressing like Orissa, that's why this Konak wheel is there. And I gave more emphasis on science and especially chemistry. That is what is central to the logo is the atomic structure. So you can think of our emphasis here in OUTR on science. Probably in coming days, we shall be able to have a very stronger team of science department, and hopefully things will go a long way in achieving what we desire today, what we aspire today. So we have not many luminaries in the field of chemistry. Some of them are my teachers, some of them are my teacher's teacher. So I welcome them to our university and hope that OCS will be working hard and sincerely to take our research in Odisha to a greater height. Thank you. Thank you.
Thank you so much, sir, for your inspiring and thought-provoking address. Your words have undoubtedly resonated with each one of us and have set a powerful tone for the day ahead.
We have now arrived at one of the most awaited moments of this event, the presentation of the OCS Lifetime Luminary Awards. This is a moment to celebrate excellence, dedication and hard work. Each award signifies not just achievement, but the relentless pursuit of greatness. These awards honor the individuals who have distinguished themselves through their exceptional contributions. It is with great pride that we now move forward to recognize their remarkable efforts. As a token of appreciation for his outstanding service, we now request our Chief Guest, Honorable Minister Sir, to present a special token of felicitation to our great luminaries.
I request Professor Balram Sahu Sir, former President OCS, an eminent academician and researcher, to please receive the award. I now request Dr. Chittaranjan Mishra Sir, former President OCS, to read out the citation. Sir, please.
Now we are going to celebrate the day with the Lifetime Luminary Award to Professor Dr. Balaram Sahu, former Professor of Chemistry, IIT Kharagpur, distinguished chemist, educator and researcher, and former President, Orissa Chemical Society.
I request our Chief Guest to confer the OCS Lifetime Luminary Award to Professor Sahu Sir.
And this book, which is about 200 pages, almost complete. Now, something on uranium chemistry, which is a significant contribution towards nuclear energy production, and I hope to higher output. There, I continued some time on uranium chemistry, then I switched on to cluster complexes, many metal associated complexes that magnetical studies. There also
तारे अच्छी प्रोग्राम है ना
pioneer in the world, and after that, research through most of them works have been published in books and have come to textbook level because of their fundamental character.
Thank you, sir. I request Professor Prabhat Kumar Mishra, sir, former President, OCS, visionary leader, and an able administrator, to please receive the award. I now request Professor Ashutosh Samantray, sir, former President, OCS, to read out the citation.
Let us first give a big hand to Professor Prabhat Kumar Mishra. Professor Dr. Prabhat Kumar Mishra, former professor and head Department of Chemistry and a principal, Orissa College, Cuttack. He is a distinguished academician, administrator, and celebrated sportsperson, and former president, Orissa Chemical Society. Honorable Minister is requested to felicitate Professor Mishra.
ହାପି ଆଉ ଟିକେ କର୍ଣ୍ଣର ହେଇକି ଉଠି ପାରିବ ଭାଇ
Now, I request Professor Pranabandhu Tripathi sir, former President OCS, visionary leader, to please receive the award. With an applause, I now request Professor Vijay Kumar Mishra sir, former President OCS, to read out the citation. Sir, please.
Namaskar. Let us give a big hand to Dr. Bhubaneswar. Now, this is the Lifetime Luminary Award presented to Dr. Pranabandhu Tripathi, distinguished chemist, researcher, academic administrator, and former president OCS.
Thank you, Orissa Chemical Society. I'm honored with this award. As you know, chemistry is my passion as of today, and administration as compulsion. With that, I wish you all the best. I wish you a happy new year.
Thank you, sir. I request Professor Gopabandhu Behra, sir, former President, OCS, eminent academician and social worker. With an applause. I now request Professor Satyaban Jaina, sir, former President, OCS, to read out the citation.
Orissa Chemical Society gives the Lifetime Luminary Award to Professor Dr. Bhubaneswar Behra, former Professor and Head Department of Chemistry, Sambalpur University, distinguished academician, accomplished researcher, mentor, and former President of OCS.
Thanks to OCS, and thank you very much. When you honor people, you honor yourself. Thank you very much for progress in the OCS for this last 38 years. Thank you.
May I now request Professor Rudra Prasanna Dwivedi, sir, former President OCS, an outstanding teacher. With an applause, I now request Professor Sarat Chandra Das, sir, former President OCS, to read out the citation.
Now, Orissa Chemical Society presents Lifetime Luminary Award to Dr. Rudra Prasanna Dwivedi, distinguished professional, academic, technology scholar, and former President of Orissa Chemical Society. Let's give a big hand for him.
ପାଖରେ କ'ଣ ତାପରେ ସ୍ତ୍ରୀକୁ ଆଗେ ଡାକିଦେବେ ଆଗେ ତା ସ୍ତ୍ରୀକୁ ଡାକିଦେବେ
Thank you, sir. I request Professor Dr. Rajnikant Satpathy, sir, former President, OCS, an outstanding teacher and a social worker. With an applause, I now request Professor Rupashu Ragini Das ma'am, former President, OCS, to read out the citation.
Orissa Chemical Society presents its lifetime luminary award to Professor Dr. Rajnikant Satpathy, former head of the Department of Chemistry, Stuart Science College, Cuttack. He is a distinguished academician, researcher, social worker, and former president of OCS.
All my friends.
Thank you, sir. As we conclude the presentation of awards, let us take a moment to reflect on the hard work and perseverance that each recipient has demonstrated. Your achievements inspire us all to reach higher and aim for excellence.
In January 2024, OCS celebrated the birth centenary of eminent educationist, outstanding researcher, visionary leader, able administrator, founder, president of OCS, and have achieved many more honors, Professor Mahindra Kumar Rao, sir. In addition, a team of his inspiring students across the disciplines, well-wishers, and persons from different walks of life contributed to publish the life story along with academic articles of Professor Rao, sir, known as Mahindrayana. The committee formed is known as Mahindra Kumar Rao Birth Centenary Celebration Committee, headed by Professor Prabhat Kumar Mishra, sir, former president of OCS, as chairman. As a token of our appreciation and recognition of hard work, let us felicitate the chairman of this MKRCC committee, Professor Prabhat Kumar Mishra, sir, secretary of this MKRCC committee, Professor Sashadhar Sanal, sir, and editor-in-chief of Mahindrayana, to Dr. Chittaranjan Mishra, sir. I request Professor Prabhat Kumar Mishra, sir, Professor Sashadhar Sanal, sir, and Dr. Chittaranjan Mishra, sir, to please receive the awards. May I request our chief guest to confer the OCS Award of Appreciation to Professor Mishra, sir, Professor Sanal, sir, and Professor Mishra, sir. Today, we gather to honor and pay tribute to a distinguished individual whose leadership, vision and dedication have left an indelible mark on this institution. It is with great respect and admiration that we now come together to felicitate the immediate former president of Orissa Chemical Society, Professor Rupashri Das ma'am, under whose leadership the society flourished, reaching new heights and setting standards of excellence. As a token of appreciation for her outstanding service, we now request the chief guest to present a special token of felicitation to Professor Das ma'am. On behalf of everyone here, we once again express our deepest gratitude. Thank you, ma'am. Your legacy will continue to inspire us all, and we are forever grateful for the path you have paved.
We are deeply privileged to have with us today as our chief guest an individual whose very presence brings a sense of grandeur and purpose to this occasion. Honorable Sri Krishna Chandra Patra, Food Supplies and Consumer Welfare, Science and Technology, Government of Odisha. A paragon of excellence in the field of public service, he has not only enriched the society with his unparalleled contributions, but has also inspired countless individuals to pursue their dreams with unwavering determination. Now, we invite Honorable Minister to take the stage and grace us with his enlightening address.
ओडिशार रसायन समाजर 38तम वार्षिक सम्मेलन उद्घाटन उत्सव में पंचासीन प्रिय अध्यक्ष प्रोफेसर अजय कुमार बेहरा महोदय, आदरणीय अतिथि प्रोफेसर विभूति भूषण विश्वाल महोदय, कुलपति OUTR मान्य अतिथिवृंद और गण्यमान्य व्यक्ति विशेष लब्ध प्रतिष्ठा लाभ कर अध्यापक अध्यापिकागण रसायन विज्ञानी माने ओडिशार एवं राष्ट्रीय स्तर अनेक ख्याति लब्ध संस्थार प्रतिनिधि माने प्रिय गवेषक और छात्र छात्री मुही प्रतिष्ठित अनुष्ठान में उपस्थित हुई अत्यंत सम्मानित अनुभव करुछि। ओडिशार रसायन समाज, ओडिशार विज्ञान एवं गवेषणा को उच्च स्तर को नेबारे जो भूमिका निर्वाह करुछि ताहा आम समस्त गर्व एवं गौरवर विषय। यही 3 दिनिया विज्ञान चर्चा अवसर में आपण माने विभिन्न उच्च कोटिर गवेषणात्मक प्रबंध मान उपस्थापन करिवे एवं एथिपाई आपण माने आपण माननको मध्य मोर शुभेच्छा। या द्वारा युव वैज्ञानिक माने बहु मात्रा उपकृत हेबे एवं सेमानଙ୍କୁ भविष्य जीवन में बड़ हेबार प्रेरणा जोगाए। बंधुगण ये कार्य पाई मते आपण मान डाकिचंती गोरु मु जने साइंस स्टूडेंट किंतु केमिस्ट्री को मुझे भय करे। मु भावे केमिस्ट्री होचे प्रकृत रे साइंस केमिस्ट्री ता प्रकृत रे साइंस जेतेले पढ़ा गला पानी ता H2O मु कहली H2 को एओ कोन ना दीटा हाइड्रोजन गोटे ऑक्सीजन मिसिकरी पानी। आज देखला बेलको हाइड्रोजन रो गाड़ी चलीबा आरंभ होइछि। हाइड्रोजन गाड़ी मध्य लोक व्यवहार करबा आरंभ करछन किंतु एई H2O एटा की डिवीजन करबो अलगा करबो ऑक्सीजन को अलगा करबो हाइड्रोजन को अलगा करबो आपण मान करिवे आपण मान करिवे ना सेटा कोने जाई कि गाड़ी चलिबो। जने बंधु भैया कहउतले मते जे साइंस माने लोक मानको पाई जेतिकी उपकार करिवो से दरकार पड़े समाज मध्य बहुत अपकार करते जमी आम एटॉमिक पावर कर देचे न्यूक्लियर पावर हो जिते न्यूक्लियर पावर विश्व रे हो जाउछंती सेते विश्व पाई विपद सृष्टि हो जाइछि। यूक्रेन रशिया लड़ाई चली सदा बेले आम देखुछु कहीं एटॉमिक बम तो पड़ जाए केबे पड़िबो बेले बेले न्यूज वाला देखे बोधे एटॉमिक बम फाइनल लड़ाई हो किंतु ए पर्यटन जाओ हे नहीं किंतु एटॉमिक बम माने फाइट हेले कौन हम विश्वटा पूरा नष्ट हो तेणु आम जो माने उद्भावन करछंती आपण मान समस्त साइंटिस्ट आपण को तो कोटि कोटि प्रणाम जो माने जो मान को प्रेसिडेंट मान को पूर्वतन प्रेसिडेंट मान को आउ आज सम्मानित कली मोर सौभाग्य जे मु आज 90 वर्ष 94 वर्ष 85 वर्षर माने जो माने समाज को बहुत किसी देइछंती हमको आज मु सम्मानित परिवार सौभाग्य प्राप्त हेली। बंधुगण तेणु मु चाहूची जे डिस्ट्रॉय आदि समाजटा न जाऊ वर्ल्डटा डिस्ट्रॉय की न जाऊ आमे किछि इनोवेशन करबा सेटा समाज पे एमती उपकार हो जेमिति पैंडेमिक आसिला जेतेबेले पैंडेमिक आसिला माननीय प्रधानमंत्री मोदी नरेंद्र मोदी से साइंटिस्ट मान को माने आह्वान दे जो मोर वैक्सीन दरकार अमेरिका रशिया ताको से वैक्सीन तैयार करबा आरंभ कर भारत वैक्सीन एते शीघ्र बाहर करबो ए विश्वास आमन नथिला दीदीटा वैक्सीन बाहरला एवं कोटि कोटि लोक बंची गले सेटा साइंस रो प्रकृत रे स्ट्रेंथ आपण माने बचैछन आपण माने प्रकृत रे जदि ये उद्भावन वैक्सीन नीटा न बाहर करथांते तालु केते जे लोक मर जाइथांते पोकमाछी बोलिया तार किछि हिसाब नथिला खाली आम देश बंचिला नहीं आमे आहुरी 50 टा देश को मागना ए इंजेक्शन वैक्सीन मध्ये आमे देले तेणु समाज को बंचिया पाई साइंस बोधे काम कले भल हबो मोर विश्वास। आउ जो कथा कहला जे प्रकृत रे मैथमेटिक्स रो इंस्टीट्यूट अछि फिजिक्स रो इंस्टीट्यूट अछि बायो टेक्नोलॉजी रो इंस्टीट्यूट अछि किंतु एपन तो केमिस्ट्री रो काहे की इंस्टीट्यूट हेई नै एटा मो मध्य प्रश्न अछि ये आगो होबा कथा काहे की मु कहूची साइंस माने होची केमिस्ट्री मो विश्वास मु सेटा दिए भल करे मुझे पे बहुत करी माथे से आड़ी पढ़ेली माथे से माने ऑनर्स कली तापर पीजी कली एठी रेवेन्सा कॉलेज रे आगे पीजी करछि मु रेवेन्सा कॉलेज स्टूडेंट पीजी करछि तेनो मु केमिस्ट्री को भय करे बोली माथे से आड़े पढ़ेली तेनो मोर कहया कथा आपण माने प्रकृत रे ज्ञानी प्रकृत रे साइंटिस्ट किंतु आमे इंस्टीट्यूट काहे के मु तो भाबुछि मु निश्चित भाव में दायित्व नेली कि इंस्टीट्यूट ऑफ केमिस्ट्री हबो आउ एई वर्ष हबो ताकू कैबिनेट रे आनिबा दायित्व तो आपण मानकर किछि चिंता करबा नै मैडम जेते बेले पुरस्कार नउथिले मैडम कहले आज्ञा इंस्टीट्यूट हबो तो मु ताकू कहली मु कहले आज्ञा हबो मु कथा दउछि हबो तेनु आपण मानको मन भीतर केते माने उत्कंठा रहिछि ए इंस्टीट्यूट होबा दरकार मु भाबुछि मु निश्चित भाव रे लागिबी माननीय मुख्यमंत्री बहुत बढ़िया लोक मोहन मांझी से सब डेवलपमेंट काम रे बहुत आगे चलछंती एवं मु विश्वास करछि साइंस आज्ञा इंस्टीट्यूट ऑफ केमिस्ट्री आमे करबा आपण मानको पूरा सहयोग रहइबो मोर सेही एतिकी कहि कि मु भाबुची अधिका कोन समय नेबी नै माने मुख्यमंत्री ऑलरेडी गोटे मीटिंग डाकी जंती आई एम लेट तेनु मु आपण मानको बहुत बहुत धन्यवाद देई मते माने एते बड़ संस्था रे थी डाकी मते सम्मानित करथिबारु आपण मानको समस्त को बहुत बहुत धन्यवाद भारत माता की जय वंदे उत्कल जय
Let's give a standing ovation to Honorable Minister.
Thank you, sir. Your words have ignited a spark within us all, leaving an indelible mark on our hearts and minds. We are truly grateful for your time, and we would like to present a small token of appreciation by felicitating your honorable sir.
Every year, OCS organizes various types of events to have the synergy between curriculum and research trends, which forms the bedrock of innovation. In 2024, the 29th two-day regional conference was organized at Panchayat College, Bargarh on 16th to 17th October 2024, and the theme of this was recent advances in chemical sciences. I request Dr. Sipun Sethi sir, Head of Department of Chemistry, Panchayat College, Bargarh, to please receive the citation.
There is a slight correction here. The two-day regional conference was organized on 16th and 17th November 2024 at Panchayat College, Bargarh. It is not October.
I now request our chief guest to present the citation to Dr. Sipun Sethi sir.
The fifth one-day extended lecture series was organized at Bhadrak Autonomous College, Bhadrak, on 29th November 2024 with a national seminar on new trends in chemical sciences. I request Professor Padmanabh Patrik sir, Head of Department Chemistry, Bhadrak Autonomous College, Bhadrak, to please receive the citation. I request our chief guest to present the citation to Professor Padmanabh Khatri, sir.
Similarly, the 6th one-day extended lecture series was organized at Rajendra University, Bolangir on 11th December 2024 along with a national seminar on frontiers in chemical sciences. I request Dr. Archana Mai Behra ma'am, organizing secretary of OCS event at Rajendra University, Bolangir, to please receive the citation. I request our chief guest to award the citation to Dr. Behra ma'am. In addition, the second OCS Industry Interface Meet 2024 on the theme Bridging Academia and Industry, Advancing Chemistry for Sustainable Innovation was organized at KEET, Deemed to be University, Bhubaneswar on December 7, 2024. I request Professor Anita Patti ma'am, coordinator of this event, KEET University, to please receive the citation. I request our chief guest to award the citation to Professor Patti ma'am.
Finally, the most coveted event of the OCS, the annual conference, is organized at Orissa University of Technology and Research, Bhubaneswar from 28th to 30th December 2024 along with the National Conference on Advancements in Materials Chemistry. I request Professor Vigyan Ranjan Das, sir, convener of this conference and head School of Basic Sciences and Humanities, Orissa University of Technology and Research, to please receive the citation.
Esteemed guests, distinguished scholars, and respected colleagues, we are gathered here today to celebrate the unveiling of a remarkable compilation, one that encapsulates the essence of intellectual journey we have embarked upon. It is with immense pride and honor that we present to you the souvenir cum Book of Abstracts of the annual conference of Orissa Chemical Society and the National Conference on Advancing Chemistry aims in 2024, a collection that reflects the breadth of knowledge, scientific findings and innovations within our community. Each abstract within these pages represents rigorous research, groundbreaking ideas, and the unwavering commitment to advancing knowledge in materials chemistry. OCS also presents the awards to student achievers in chemical sciences in the state of Orissa. Professor K.K. Patnaik Memorial Award for securing the highest percentage of marks in MSc Chemistry examination in the state of Orissa, and Srimati Parvati Mishra Award for lady student securing highest percentage of marks in MSc Chemistry examination in the state of Orissa. For both the awards, the winner is Ms. Pratibha Raut, securing 90.5% in MSc Chemistry examination from Ravenshaw University, Cuttack. Congratulations to Ms. Raut. She is requested to receive the award. May I now request the President of OCS to kindly present the award to Ms. Raut.
Ms. Pratibha Raut has received the Srimati Parvati Mishra Award and the Professor K.K. Patnaik Memorial Award.
She is the best chemistry student of the entire state of Orissa.
And she has received a cash prize of 1,000 in each award.
Best postgraduate in chemistry in the entire state of Orissa for the year 2024. She is getting 2 awards from the name of
Srimati Subhadra Devi Memorial Award for securing the highest percentile in the GATE score from among the MSc Chemistry students of Odisha, and Professor Pranabandhu Tripathi Award for securing the highest rank among the CSIR UGC JRF NET qualifier from Odisha in chemistry. For both the awards, the winner is Subhashis Raut from NIT Rourkela. Congratulations to Mr. Raut. He is requested to receive the award. For both the awards, Mr. Subhashis Raut has received a cash amount of ₹5,000 for the Srimati Subhadra Devi Award and an amount of ₹1,000 for the Pranabandhu Tripathi Award. May I now request the President of the Odisha Chemical Society to present the award to Mr. Raut. Mr. Subhashis Raut has received an amount of ₹5,000 for the Srimati Subhadra Devi Memorial Award and an amount of ₹1,000 for the Professor Pranabandhu Tripathi Award.
As a token of our respect and regards, it's our privilege to honor our chief guests in this joyous occasion. I now request Secretary Professor Achyutananda Acharya sir to felicitate the guest of honor, Honorable Vice Chancellor sir.
ଆମ ପାଖରେ ବସିଛନ୍ତି ପୂର୍ଣ୍ଣଚନ୍ଦ୍ର ମଲ୍ଲିକ ରିଟାୟାର୍ଡ ଡେପୁଟି ଡାଇରେକ୍ଟର, ତାଙ୍କୁ ଆମେ ଚାହୁଁଛୁ ଅନରେବଲ ଭାଇସ ଚାନ୍ସେଲର ତାଙ୍କୁ ପ୍ରେସିଡେଣ୍ଟ କରନ୍ତୁ। ସାର୍ ଆସନ୍ତୁ ସାର୍ ପ୍ଲିଜ। ଆମ ଟିଚିଂ ଲାଇନ ଲୋକ ବିଜେପି ଆଗରୁ ଥିଲେ ଲିଡର, ସାରଙ୍କ ଷ୍ଟୁଡେଣ୍ଟ ସାରଙ୍କ ଷ୍ଟୁଡେଣ୍ଟ ସେ।
request convener Professor Vigyan Ranjan Das sir to felicitate the Secretary of OCS, Professor Achyutananda Acharya sir.
Thank you, sir. It is now my distinct honor to introduce the individual whose vision, leadership and commitment have been the cornerstone of the success story of Odisha Chemical Society. Our esteemed President, Professor Ajay Kumar Behera, has led this society with unparalleled dedication and passion, constantly striving to shape a future of excellence and innovation. Without further delay, I now invite our esteemed President, Professor Ajay Kumar Behera, to deliver the presidential address. Sir, please.
Respected Chief Guest, Honorable Minister Shri Krishna Patra, Food Supplies and Consumer Welfare, Science and Technology in absence. Esteemed guest of honor, Professor Bhubaneswar, the Vice Chancellor of Orissa University of Technology and Research. Secretary cum Treasurer, Professor Achyutananda Acharya. Professor Vigyan Ranjan Das, convener of the conference. Honorable former presidents of OCS, the members of OCS Executive Committee, dear scientists, invited speakers, professors, researchers, students, and members of Orissa Chemical Society, press and electronic media, ladies and gentlemen. Greeting to all to the 38th Annual Conference of OCS and National Seminar Advanced Materials in Chemistry. In fact, Orissa Chemical Society was conceptualized in the School of Chemistry, Sambalpur University in 1985. The society was formed under the visionary leadership of late Professor Mahendra Kumar Raut as founder president and late K.C. Satpathy, a founder secretary with a mission to promote quality teaching as well as research in frontline areas of chemical sciences. Since then, the OCS has constantly grown with the global visibility. Our Vice Chancellor, I was hearing the speech of our Vice Chancellor. Chemistry is a very powerful subject. Chemistry is omnipotent and omnipresent. And union of three dots, Tridev, so is nothing but a chemistry. The amalgamation of Brahma, Vishnu, Maheshwar is chemistry. And most powerful. And if used for the construction of the world, construct the society, it will help. If you want to destroy, it will destroy. The 38th Annual Conference of Orissa Chemical Society is dedicated to late Dr. D.V. Raman Rao, late Gopinath Gajapati, late Dr. J.P. Nath, and late Professor Ilarani Patnaik for their significant contribution and chemistry teaching and research. As we end the inaugural function of the Grand 38th Annual Conference of Orissa Chemical Society, I feel deeply privileged to stand before you to praise, to express my heartfelt gratitude and appreciation to all who have contributed for making this event a memorable success. First and foremost, I extend my sincere thanks and gratitude to our Chief Guest, Honorable Minister Sri Krishna Patra, for blessing this occasion with his esteemed presence and inspiring address, which has provided us with a vision for the future of science and technology in Orissa in the form of an Institute of Chemistry. So in absence also, I express my sincere gratitude on behalf of Orissa Chemical Society for his commitment to form the Institute of Chemistry in state from this year. I also express my profound gratitude to the guest of honor, Professor Bhubaneswar Biswar, the Honorable Vice Chancellor of Orissa University of Technology and Research, for extending our invaluable support and for hosting in this esteemed institution the 38th annual OCS conference as the chief patron. Your kind guidance at every step has been instrumental in ensuring the success of this conference. Organizing this annual conference has been a culmination of months of planning, dedication, and hard work. I take this opportunity to acknowledge the efforts of the Executive Committee of Orissa Chemical Society in providing their valuable time for policy decisions and the members of the award committee for their meticulous work in selecting the award winners. Their commitment to recognizing and celebrating excellence within our community deserves the highest praise. I extend my heartfelt appreciation to all members of Orissa Chemical Society who have attended various OCS academic events throughout the year, including 2 OCS one-day extended lecture series, the OCS Industry Interface Meet, a regional conference, and 38th annual conference. The OCS organized the Chemistry Olympiad. The Olichem team worked tirelessly to conduct this state-level competition, and they deserve my hearty thanks. These initiatives continue to elevate the standards of academic excellence and inspire the younger generation. My hearty thanks to our sincere teachers and former presidents of OCS for taking all the trouble to attend this conference and receive OCS Luminary Award. I am also thankful to the organizers of the OCS events conducted throughout the year in different locations. These events are the backbone of OCS aims and objectives. My special thanks go to the local organizing committee for this annual conference for their outstanding efforts in planning and executing this 3-day event. This seamless coordination and attention to detail in every aspect from the scientific sessions to the hospitality arrangements have been commendable. I also appreciate the dedicated faculty, staff, and students of OUTR for their unwavering support in hosting this grand event. Your contribution have been vital in making this conference a resounding success. Finally, I am grateful to all invited dignitaries, scientists, researchers, and professors who have participated in this conference to share their knowledge, insights, and ideas. Your presence has enriched our discussion and added immense value to this gathering. I also express my heartfelt thanks and gratitude to the Committee of MKRCC for conducting the birth centenary function of the legendary figure of Professor Mahendra Kumar Raut without fraud and very meticulously and making this function a last grand success in this year, in the beginning of 2024. So once again, I thankful to Professor Prabhat Kumar Mishra, Chairman, Professor Sasadhar Samal, Secretary, and Dr. Chitaranjan Mishra, the Chief Editor of Mandran. Big claps to the three people for their effort, untiring effort to make this function a grand success. Finally, I am grateful to all the invited dignitaries, scientists, researchers, and professors who participated in the conference to share their knowledge, insights, and ideas. Your presence has enriched our discussions and added immense value to this gathering. As we conclude the inaugural function of the conference, let us carry forward the ideas of learning and collaboration we will build here in these 3 days and continue to work together to advance the field of chemistry for the benefit of society. Once again, my heartfelt thanks to every one of you for your support, enthusiasm, and participation. Let us look forward to a successful 3-day event for the growth and innovation and achievement for Orissa Chemical Society. I hope the delegates will have a pleasant stay in the cold winter at the gallant year-end event. Enjoy your stay and enjoy chemistry. Happy New Year to you all. Thank you. Bande Utkalajanan. I also thank the press and media for their sincere effort to widely cover the 38th annual conference of this program in electronic media. Once again, I also thank them for their wide coverage of this program. Thank you all.
On behalf of everyone here, we extend our deepest gratitude for your continued dedication and vision. Your address has not only inspired us but has also set the stage for a bright future filled with endless possibilities. Thank you, sir. Every beginning has an end, and we have now arrived at the closing of the inaugural ceremony. I now request co-convener Dr. Alpha Sharma sir to deliver the vote of thanks. Sir, please.
Good afternoon all, the dignitaries of the dais and the audience of the event. First of all, I am thankful to the organizers to provide me such a nice opportunity to read out the vote of thanks. So I will start with Acharya Prafula Chandra Roy, often hailed as the father of modern Indian chemistry and a true nationalist. He once said, "There is no delight like that which springs from a discovery. It is a joy that gladdens the heart." These profound words of Acharya Prafula Chandra Roy capture the essence of scientific endeavor and transformative power. Today, as we celebrate this momentous occasion of 38th Annual Conference of Orissa Chemical Society, along with National Conference on Advancements in Materials Chemistry, let us take a moment to honor his invaluable contributions that continue to inspire generations. I also take this opportunity to remember and express gratitude to Professor Mahendra Kumar Rao, the visionary founder of Orissa Chemical Society. His relentless efforts and pioneering vision laid the foundation of this esteemed society, a kind of first in Eastern India, fostering the culture of scientific excellence in the state. His legacy continues to guide us as we advance in our mission. Moving forward, I, on behalf of the organizing committee, extend my heartfelt thanks to our esteemed chief guest, Honorable Minister of Food Supplies and Consumer Welfare, Science and Technology, Sri Jukta Krishna Chandra Patra sir, for gracing this occasion with his presence. Your insights today have been a source of immense inspiration for all of us. It's a matter of pride to express our indebtedness for the financial support received from Science and Technology Department to organize this event. I extend my heartfelt gratitude to the guest of honor and patron-in-chief, Professor Vibhuti-Bhushan Biswal sir, Vice Chancellor of Odisha University of Technology and Research, for his support and valuable insights. Sir, your presence strengthens the vital connection between academia and scientific progress. A very special note of thanks to President Orissa Chemical Society, Professor Ajay Kumar Behra sir, for his visionary leadership in organizing the 38th annual OCS conference. Sir, your perseverance and inputs have been instrumental in bringing such a diverse group of intellectuals and professionals together, ensuring the continued success of this prestigious event year after year. I must also extend my deepest appreciation to the patron of the conference, Secretary cum Treasurer, Orissa Chemical Society, Professor Achyutanand Acharya sir. Sir, your guidance and meticulous planning have been backbone of this event. Your hard work and unwavering commitment have left an indelible mark on all aspects of this conference. Your efforts truly a labor of love, which ensured its resounding success, and for that we are deeply grateful. My heartfelt thanks to convener of the conference, Professor Vigyananjan Das, for his invaluable contributions and exceptional organizational skills, which played a crucial role in executing this event seamlessly. We are also deeply grateful to our funding agencies, Anusandhan National Research Foundation, CSIR, Department of Science and Technology, Government of Orissa, industrial sponsors Jindal Steel and Power Limited, Paradip Phosphate Limited, IMFA, IRL, and FU for your benevolent support. I extend my warm gratitude to the friends from print and electronic media for your cooperation. I extend my deepest gratitude to the invitees and speakers of this conference for their dedication to come over here and grace us with their talks. Last but not the least, I extend my gratitude to the local organizing committee members, university authorities and staffs, student volunteers who have worked tirelessly to coordinate and execute this event within a limited time frame. Your dedication and teamwork are truly remarkable. Finally, I thank all the OCS patron members, live members, executive committee members, student and faculty participants who have turned up to make this program a grand success. With these words, I once again express my heartfelt thanks to everyone and welcome all of you again to this conference. Thank you and have a great day ahead.
So, as we have come to the end of the inaugural ceremony, there will be a short break of 5 minutes, after which we will be having the Professor Mahendra Kumar Rao Memorial Lecture, and the session will be chaired by Professor Ajay Kumar Behra sir, the President of Orissa Chemical Society.
The meeting is over. Now the technical session will start without any tea break. If anybody wants, he can go outside for tea break, but session will continue. The first one is Professor Mahendra Kumar Raut Memorial Lecture, and it will be delivered by Professor Iris N.M. Nambutri, Professor Department of Chemistry, IIT Bombay, and it will be chaired by Professor A.K. Behra. Sir. Professor Ajay Kumar Behra received his MSc degree from Uttar University in 1984, MPhil PhD degree from Bhubaneswar University 90 and 96 respectively. After working for a few years at Government College, he joined Postgraduate Department of Chemistry Sambalpur in 1997 as senior lecturer, became reader in 2000, Professor of Chemistry in 2009. In the School of Chemistry, Sambalpur University. His research interest includes synthesis of pharmacologically active heterocycle, spiroheterocycle, and natural products. He has over 40 publications in many international journals of repute, which has chemical reviews, tetrahedron, granular heterocycle, synthetic communication. Sir, please.
I invite Professor I.S. Namuthi, Department of Chemistry, IIT Mumbai.
Saya kong pura panggil lah.
So please, silence please. So before deliberation, I would like to introduce the founder, president of Orissa Chemical Society, Professor Mahendra Kumar Raut. This memorial lecture was in the name of Professor Mahendra Kumar Raut. We know that Professor Mahendra Kumar Raut was the founder president of Orissa Chemical Society. Professor was born in Bhadrak on 4 January 1924 and did his matriculation from Patna University in 1938. He did his bachelor degree from Ravenshaw College and postgraduate degree of chemistry from Patna Science College. He was awarded PhD degree from Uttal University in 1952. So his field of research interests were organic synthesis on drugs and biologically active compounds, dyes and natural products. He started his career as lecturer in chemistry from Ravenshaw College and became professor and head of the department of chemistry. Professor Raut was the pioneer in the state for chemistry research, and we know that he is a versatile administrator. He was the principal of GM College, now is GM University, principal of another premier college of Barampur, Khalikot College, so, and also principal of Ravenshaw College. He was the vice chancellor of Uttal University. He was chairman of Pollution Control Board and also the founder member of Orissa Chemical Society. And his tenure, whatever we have developed, so because of his contribution. So with this short introduction, I want to introduce Professor Iris, the speaker of this memorial lecture. Professor Iris Namuthi is currently professor in the Department of Chemistry, IIT Bombay. Professor Namuthi joined the Department of Chemistry, Indian Technology, Mumbai, where he is currently a senior professor. His research interests include organic synthesis, development of new synthetic methodologies, asymmetric catalysts, mechanical studies, and materials chemistry. He is an elected fellow of Indian Academy of Science and National Academy of Science, India. He is also a recipient of various prestigious awards of Paris University, France, D.A. Albert Senior Fellowship, Paris Calais University, France, Chemical Research Society of India Bronze Medal, 2014, Chairman, Rasayan Shastra, Excellence Research Medal in 2024, and many. He has supervised 26 PhD and co-authored around over 200 publications. He has supervised 26 members. Professor Namuthi has been a visiting professor to Alternative Energy and Atomic Energy Commission CEA, Scalais, France. Federal University Mines of Garis, Belo Horizon, Brazil. He is a member of American Chemical Society, Chemical Research Society of India, and Indian Chemical Society. So with this short introduction, I invite Professor Namruti to deliver his lecture. And I request to complete his talk in 45 minutes.
Thank you. Orissa Chemical Society for the invitation and warm hospitality. I would also like to thank Professor Citation and also Professor Akhil Sahu for nominating me to deliver this lecture. I am truly honored to have got this opportunity to deliver the lecture in honor and memory of Professor Mahendra Kumar Rao, a great teacher, researcher, and academic administrator. And also, he was the founder president of the Orissa Chemical Society. He was also a wonderful human being, as I understand. And the galaxy of elders sitting in the front row is a testimony to that. He has mentored several great personalities. I was also fortunate to have got several students from Odisha. In fact, a couple of PhD students who graduated from my group, which is Smita Sahu. She is at Naipar Ahmedabad. We have a pointer.
The pointer will not work on this.
This will not work. We have another pointer.
Any stick pointer maybe.
Otherwise I can go there.
Stick pointer. Stick.
And Soumyaranjan Pati, who graduated in 2021. He is a postdoctoral fellow in New York. And currently one student from Ravenshaw College is working in my group, Vidyut Pramali. I also had a MPhil student, Ananya Panta, who is doing her PhD in Taiwan. And my first postdoc was from Odisha, Naveen Kumar Mehar, who did his PhD in IIT Delhi. Now, since this is my first talk at the Odisha Chemical Society, let me give you this will not work.
Yes, yes.
Let me give you a brief overview of our research interests. So we are interested in the development of new synthetic methodologies, mechanistic studies, and also synthesis of new molecules with interesting properties. Some of the topics of our current interest are outlined here. The alpha functionalization of nitroalkenes under the Morita-Bellis-Hillman and Rahout career conditions, synthetic applications of diazo compounds, especially Westman-Ohira reagent in the synthesis of polynitrogen containing heterocycles, catalytic asymmetric conjugate addition of active methylene and methyl compounds to various electron deficient alkenes, applications of curcumin, the yellow pigment that is found in turmeric in cascade reactions, magnesium bromoform as a reagent system in 1,2 addition, 1,4 addition, 1,6 addition and cyclopropionation, and sulfonyl thalide, as you can see here,
as a substrate in the synthesis of various carbocycles and heterocycles by Hausser-Krauss annihilation. And in collaboration with a French group, we work on carbon nanotube metal and organo-catalyzed reactions. And we are also interested in several Michael-initiated ring closing reactions. And finally, in collaboration with a combustion engineering group, we work on polycyclic cage compounds. Especially, you're looking at their energetic properties. These are considered as kinetic rocks, but thermodynamic powerhouses. So now, let me come to today's topic on synthesis of chiral molecules in an enantiomerically pure form. Let me begin with a historic perspective. Archimedes has demonstrated that rotation of a chiral object like this, a helical object, could effect translation. So he was able to pump out water from the hold of a ship using this helical device, which is considered to be the first application of chirodynamics. And if you go back to our own mythology, most of you are aware of this, that Bhima was able to kill Jarasandha with the help of Lord Krishna by breaking his symmetry, by splitting his body and throwing the two halves in different directions so that they won't come back together to give life back to Jarasandha. You can also see several objects and living beings in nature that have symmetry. Now, but when it comes to chemistry and biology, a 3-point interaction is very important. There should be perfect match between enzyme and substrate or drug and receptor. If there is a mismatch, there could be mishap. As in the case of thalidomide, many of you may know that thalidomide has been administered to pregnant women for the treatment of morning sickness in the 1960s and 70s in Western countries. But it was administered as a racemic drug. But while the R isomer is a desirable anti-nausea drug, the S isomer is a toxic substance. So the children were born with disabilities. So there is considerable interest in the development of enantiomerically pure compounds. And one way to do that is to resolve the racemic mixtures, like Louis Pasteur did for the first time. And the other possibility is asymmetric synthesis. You can synthesize enantiomerically enriched compounds using enantiomerically pure natural products as starting materials, sugars, amino acids, and so on. It's called chiron approach. You can also attach a chiral auxiliary to your achiral substrate, do the synthesis, and then remove it. But the most attractive approach is the catalytic approach. And several catalysts can be used for this purpose. Biocatalysts, for instance, enzymes, nucleic acids, and so on, organometallic complexes, and the latest trend is to use organic molecules, small organic molecules as catalysts. In fact, it is not a new development. It has been known since 1910 that small organic molecules can be used as catalysts in asymmetric synthesis. But it's only in the year 2000 onwards, this area has received tremendous attention. So this culminated in the award of Nobel Prize to these scientists, that is Benjamin List and David Macmillan, and you can see the tremendous development in the area of organocatalysis starting from 2000 to 2020. Some of these molecules that are used as organocatalysts, like proline, cinchona alkaloid, and the binaphthol, are now household names in catalysis. Now, there was a news recently that the scientists don't rule out the possibility of a mirror image world somewhere in the universe. Now, in this world, 95% of human beings are right-handers. So what could be the handedness of the human beings in the mirror word that could be, left-handed. Now we got interested in the synthesis of various, chiral molecules in enantiomerically pure form. So we began with the synthesis of aminophosphonic acids, gamma, beta, and alpha aminophosphonic acids, because these are considered as transition state analogs of amino acids. These aminophosphonic acids mimic the transition state in the peptide, tetrahedral transition state in the peptide bond hydrolysis. So we thought that we could introduce chirality in such aminophosphonic acid such that such compounds could exhibit interesting biological properties. So initially we have started with conjugate addition of various nitrophosphonates, beta and gamma nitrophosphonates to acceptors like nitroalkenes in the presence of lithiated silicon and also the binol, lithium aluminium binol, Basaki catalyst, and isolated the products, the gamma and beta nitrophosphonates in excellent yields, diastereo and enantio selectivities. Later on we have switched to aminophosphonic acids, which are the surrogates of naturally occurring amino acids. We were particularly interested in the synthesis of quaternary aminophosphonic acids because the chiral center would remain intact even under a variety of conditions. Of course, there are several methods known in the literature for the synthesis of aminophosphonic acid. One can add phosphite amines, electrophilic amination of phosphonates, nucleophilic addition to iminophosphonates, electrophilic quenching of aminophosphonates, etc. But our interest was to use nitrophosphonates and add this to a vinyl ketone. And you can see that we have screened several catalysts, but the best catalyst turned out to be this thiourea, this Syncona twinning-derived thiourea, which provided the product in about 59 in 74% EE. The best result can be seen below. And under those conditions, we have investigated the scope of the reaction with a variety of vinyl ketones. And as you can see that the enantio selectivities are good, but not excellent. In few cases, the yields drop even below 50%, especially in the case of aryl ketones bearing electron withdrawing groups like nitro and also the heteroaryl. However, we went ahead with the further scope of the reaction. By taking an electron-rich aryl vinyl ketone, we have added several nitrophosphonates under the optimized conditions, 10 mole percent of the catalyst, and isolated the products in excellent yields and enantio selectivities. In fact, in the proposed transition state, the nitrophosphonate is deprotonated by the tertiamine moiety, and at the same time the vinyl ketone is activated by thiourea. So this is a Bronsted acid, Bronsted base catalysis, and we have also shown that the products can be converted further to upon reduction, the aminophosphonates spontaneously cyclize iminophosphonates, and upon oxidation, bare medical oxidation followed by reduction, the product cyclize to pyrrolidone phosphonates, which can be considered as proline derivatives, proline analogs. So sometimes we see residue mixtures in nature as well, the objects in both enantiomeric form. So we were not fully satisfied with the selectivities we have obtained, so we decided to screen additional catalysts, especially with the electron deficient aryl vinyl ketones. And you can see here, in addition to thioureas, we have screened several squaramides as well. So the Syncona based squaramides. So when we switch to squaramides, the selectivity is improved from say 19% to 60, 70, and finally 92% EE. The product could be isolated in excellent yields and very high enantiomeric excess. So that was the best catalyst for our reaction. And under the optimized conditions, so we have subjected several electron deficient aryl vinyl ketones as well, this time to the conjugate addition of nitrophosphonates, and isolated the products in excellent yields and enhancer selectivities, with couple of exceptions. Only in couple of cases the E is dropped. For example, in this case 74%, 15, and whenever we had an ortho substituent or alpha-naphthyl substituent, and also cycloalkyl, the E dropped considerably. It was possible to use different nitrophosphonate as well, taking a representative aryl ketone, and you can see in most cases the products were isolated in excellent yields and enhancer selectivity. It was also possible to synthesize the nitrophosphonate on a larger scale, close to 3 gram scale, without any drop in the selectivity. And in the proposed transition state here, the tertiary amine deprotonates the nitrophosphonate. At the same time, the vinyl ketone is activated by the double hydrogen bonding squaramide moiety. Now, we also have shown that the product can be further transformed to aminophosphonates, amidophosphonates, and also carboxylic acids, hydroxamic acids, etc. Such hydroxamic acids are known to show metallar MMP inhibitory properties, matrix metallar protease inhibitory properties. Yeah, now we are much more comfortable. We found a procedure to synthesize enantiomerically pure compounds with very high selectivity. So around that time, Professor Sandanu Mukherjee from IAAC has published a paper on the addition of nitrophosphonate to nitroalkenes. So we thought that although we have been interested in the chemistry of nitroalkenes, we switched our acceptor. So we have chosen this vinyl sulfone because the product can be further transformed, subjected to Julia olefination, for example, acylation followed by desulfonation, alkylation followed by desulfonation, and so on. And also there are several drug molecules that are known in the literature for their for a variety of possessing the sulfonyl group for a variety of biological properties. So we have chosen these molecules as representative substrates, nitrophosphonate and this phenyl vinyl sulfone, and under the optimized conditions, the best catalyst for this reaction was this quinine-derived squaramide, which provided the product in excellent yield, 96% and 98% enantiomer selectivity. Under those conditions, we have demonstrated the scope of the reaction. You can see most of the products are formed in very high yields and selectivities. And it was also possible to transform the synthesized products to corresponding aminophosphonates and then further derivatization to acylated N-acyl derivatives and so on. And the transition state, in the transition state, you can see that the tertiary amine moiety deprotonates the nitrophosphonate. At the same time, squaramide moiety activates the sulfonyl group. So we further wanted to investigate the scope of this conjugate addition strategy for the synthesis of enantiomerically pure compounds. And this time we have chosen nitrosulfone, and addition of nitrosulfone to vinyl ketone was investigated. A variety of catalysts. Again, this Syncona-derived squaramide turned out to be the best catalyst, which provided the product in 98% yield and about 94% enantiomer selectivity. And the scope of the reaction was very broad, you can see. In fact, we could further improve the conditions by choosing just 0.2 mole% of the catalyst, a homeopathic dose of the catalyst, and lowering the reaction temperature to -60. And several vinyl ketones were employed for the addition of nitrosulfones, and as you can see, the products were isolated in excellent yields and selectivities without any exceptions. It was possible to add different nitrosulfones as well to a selected vinyl ketone. Again, the yield dropped only in one case. Then we had a long alkyl chain as part of the nitrosulfone, and it was also possible to scale up the reaction and synthesize nearly 3 grams of the product without any drop in yield or selectivity. So the transition state is similar to what we have discussed earlier. It was also possible to derivatize the product further to hydroxamic acids, carboxylic acids, etc. That means aminophosphonates with additional functionalities could be, aminosulfones with additional functionalities could be synthesized without any problem. Now, can we use acrylates, that is conjugated esters, for this purpose? In fact, acrylates are less reactive, so it was more challenging. In fact, we found suitable conditions for this reaction. This time, the best catalyst was not cinchona based, but amino acid based. Tertiary leucine derived squaramide turned out to be the best catalyst, which delivered the product in 98% yield and 92% EE. So those conditions were employed to demonstrate the scope of the reaction, and you can see in most cases, in fact in all cases, the products were formed in excellent yields and enantiomeric excesses. It was also possible to vary the nitrosulfone in this case, and again the E's and yields were excellent without any exception. And in this particular reaction, the product crashed, the catalyst crashed out of the reaction once the reaction was complete. So we could recover and recycle the catalyst without any drop in the yield or selectivity. And the transition state, in this particular case, the tertiary amine moiety deprotonate the nitrosulfone and then activates the acrylate. That is a favored transition state. And it was also possible to carry out post-synthetic transformations on this product by converting it to carboxylic acid, hydroxamic acid, and so on. Yeah, this is an edible vegetable found in Australia. You can see this is chiral. It has helical chirality. The entire structure is chiral. If you take a substructure, even that is chiral, that has helical chirality. If you take a portion of it, a substructure, even that is chiral. Again, a wonderful creation of nature. Now, our next objective was to use nitro esters as donors, Michael donors, because the product could be easily converted to amino acids, alpha amino acids, which are naturally analogs of naturally occurring amino acids. Again, we have screened various catalysts, and this particular catalyst, the tertiary leucine derived squaramide, turned out to be the best for our purpose, and the product was isolated in 95% yield and 82% EE. So those conditions were employed to show the scope of the reaction, even though the E's were moderate compared to what we have seen in the previous schemes. These are amino acid precursors of amino acids. So, and in most cases, except maybe one or two, I think a couple of cases, E's were in the 70s. Whenever we had an ortho substituent, orthoaryl group or a cycloalkyl group, the E dropped below 50%. And the scope of nitro ester was also investigated. Again, you can see the E's are very high, about 60s, in the 60s and 70s, and some of them more than 80%. So it was possible to scale up this reaction. How much? So it was possible to scale up this reaction and synthesize this compound in up to 2 gram scale. okay, transition state is similar to what we've seen earlier, and it was possible to synthesize, transform the nitro carboxylate to a glutamic acid and confirm the absolute configuration by correlation with the glutamic acid. So there was no need to get an X-ray structure to assign the absolute configuration. So we have seen the application of certain organocatalysts, particularly thioureas and squalamides in our reaction. Now, the pK of thiourea is about 16, but the moment we replace the toluene group, that is paramethyl phenyl group in this thiourea, the bis trifluoromethyl, it improves to about 12 to 13. Now, if you replace the thiourea moiety, then it improves to, by squaramide, it further improves to about 10.5. So that is the main reason why we found thiourea, the squaramides, to be the best catalyst for our reaction. So what we have seen so far is the application of vinyl ketones, vinyl sulfones, acrylates in the synthesis of alpha amino acids and their surrogates by adding nitrophosphonates, nitrosulfones, and acrylates. Now, some of you may have read the novel written by Lewis Carroll, Alice in Wonderland. So it is easy for writers and philosophers to stretch their imagination and go from one world to another world. But for scientists, it requires a lot of hard work to synthesize an enantiomer of a particular compound. Certain enantiomers are available in nature, but certain others are not. So to synthesize them, it requires a lot of hard work. So now, since the time is limited, let me skip some of these. So this is one of the highlights of our work. Uses squaramide as the catalyst. In fact, one of the schemes we have developed, that is addition of hydroxynaphthaquinone to nitroallylic acetate for the synthesis of pyranonaphthaquinone is shown here. Its flow chemistry version was developed by a Spanish group, and they were able to not only reproduce our reaction but also isolate the intermediate we have proposed in our reaction. So this is I happened to visit Brazil a few years ago, and on my house table I found this. His name is Antonio Luis Braga. In fact, he also kept the mirror image of his picture and named Antonio D. Braga, which reminded me of D and L isomers of naturally occurring, isomers of amino acids and sugars. Okay, I'll skip this chemistry on curcumin, which is, I've told you in the introduction that the active methylene compound curcumin can be used for conjugate addition as a Michael donor and also acceptor because it has an enone moiety. And we have developed several schemes, including catalytic asymmetric ones for the synthesis of complex molecules using curcumin as a donor. Even, in fact, we developed several methods for the synthesis of spiro-oxindoles, and using curcumin as a donor and this oxindole ester as an acceptor, and also this synchronic thiourea as a catalyst, we have been able to synthesize these spiro compounds in highly enantiomerically pure form. You can see complex spiro compounds where desymmetrization of curcumin also takes place. And finally, we have observed some interesting kinetic resolution of nitrochromines when we treated this with curcumin. only one of the enantiomers in the presence of this zingonin catalyst, zingona-based furamide catalyst, only one of the enantiomers of nitrochromine reacted to give the product. The other enantiomer was left behind. The yields we have obtained for the product and also the leftover enantiomer were moderate, but we are currently improving that. And in collaboration with the French group, we have developed methods for the heterogeneous catalytic methods for several reactions, like aldol reaction of ketones to aldehydes in the presence of carbon nanotube support, CNT supported, the amplifiers containing a long alkyl chain and also toluene. Toluene is the chiral catalytic moiety there. Okay, so to summarize what I have presented today, we could use nitrophosphonates, nitrosulfones, and also nitrocarboxylates for conjugate addition to various acceptors like vinyl ketones, vinyl sulfones, and also acrylates for the synthesis of alpha amino acid derivatives and their surrogates. And we also see application of curcumin in cascade reactions for the synthesis of highly functionalized cyclohexanones, pyranol and naphthalenones, and also several spiro compounds as well, spiro-oxyzones. Okay, these are some of the cover pages that highlighted our work. I draw your attention to this book, which I have co-authored with my Israeli supervisor, postdoc advisor, Mr. Hasner. So this covers more than 750 organic reactions, and the next edition of this book will be published anytime soon, probably early next month itself, which covers around 800 organic reactions. During COVID, we also published a book called Catalytic Asymmetric Reactions of Conjugated Nitroalkenes. And recently ChemCom has highlighted our work on polycyclic cage compounds. I told you in the beginning that these are cubane-like structures with two additional carbons known as bis-homocubanes. So these compounds are like kinetic rocks, but thermodynamic powerhouses. We can use them as energetic materials, as additives to conventional fuels to improve their performance. This is also chiral. This is C2 symmetric. The basic structure is C2 symmetric chiral, and ChemCom, which is celebrating its 60th year, has chosen this to publish on their cover page. So this is my present group, and one student from Orissa, Vidyut, is still with us. And these are the students who contributed to the work I presented today. Vishal, who is now a professor at IISER Bhopal, and Narasimham Ayyagiri is in Hyderabad, working in the company. Alishankar did most of the work I presented today. Is again in a company in Bangalore. Divya is in a college in Kerala. Vishika is now a faculty in New Jersey, small university, and Shivashankara is in a postdoc in the US, Florida. Okay, and as you know, there are as many as 23 IITs now, and we stopped counting. There could be more in the coming years. And I come from here, and we are here right now. Okay, and if you have not been to Mumbai, this is the iconic gateway of India, and these are 2nd century Buddhist caves. Elephanta caves, 1 hour drive from gateway of India. Again, the Chhatrapati Shivaji terminus railway station, and the Taj Hotel, which was under attack 26/11 in 2009. This is the aerial view of our campus, IIT Bombay. You can see the Powai Lake, and these are some of the hostels on one side of the lake. On the other side, you can see a very expensive neighborhood called Hiranandani. And we have some distinguished visitors to our campus. They come from the nearby Sanjay Gandhi National Park, and you can find several crocodiles in our Powai Lake. And regularly, students conduct yoga sessions in our indoor stadium. Also, we have sports facilities of international standard. These are some of the snapshots from our campus, and this corridor is known as Infinity Corridor. Most of the departments are on either side of the corridor. And one of our students, I forgot to mention her name, Archana, my Behra Award. She was a PhD student of my colleague, Professor Kulkarni. So I forgot to mention her. So at one point, in the corridor, you can read this inscription, which reads, Jnanam Paramam Dheyam, which means knowledge is the supreme goal. I'm sure I was standing between you and lunch, but I can only offer it this. One can cut an apple into two homochiral halves, if you can do it carefully. Okay, I'm grateful to all my co-workers whose names are listed here, and my collaborators, French, Brazil, and also Indian. Finally, I'm also thankful to all the funding agencies, especially the CRB that funded the work I presented today, and CSIR that supported the students. Okay, I'll leave you with a philosophical question. You can see right hand drawing the left hand and left hand drawing the right hand. Which hand started first? So this has some relevance to the origin of life. One school of thought thinks that life originated in racemic form and then over a period of time it got enriched. The other school of thought thinks that first enantiomerically pure advanced intermediates, biomolecules were generated, then from that life originated. So which started first? So which hand started drawing first? Thank you very much for your attention and patience.
For your nice talk, particularly using asymmetric organic catalyst for monitoring the selectivity of the reaction, and he has used so many nitrophosphons, nitrosulfones, etc. So big hands to Professor Namudi for his brilliant talk.
Although we have two talks in this session, but we have to proceed for lunch. I request all the delegates to please proceed to the lunch nearby in the SAC building. Our volunteers will guide you to that. And only the senior teachers, they have to stay here. For them we have arranged here, in the same room where breakfast is arranged. All others are requested to please proceed for the lunch. And I thank Professor A.K. Behra, sir, who is President of OCS, to chair this session. Thank you, sir. Break for lunch. And we will assemble here 2:45, sharp 2:45.
Yeah.
talk is rescheduled. Dr. Nimai Misra will be given his talk in place of Prabhat Maiti, and only Prabhat Maiti will give afterwards. So I now request Professor Satyavan Jana to chair this session. Sir, please. Just a short introduction about my teacher. Professor Satyavan completed his PhD in chemistry from Utkal University in the year 1984. He is the gold medalist from Utkal University. He joined in 1985, became professor in 1999. Before joining Utkal University, he was a lecturer at GN College, Sambalpur, Revencha College, Cuttack. Professor Jena published large number of research papers in various national and international journals, seminars, symposium, conferences. After superannuation from Utkal University, Professor Jena is the working director at KT University, Bhubaneswar. Professor Jena is considered as a leading chemical scientist of the country, and his contribution to chemistry is unparalleled and praiseworthy. And overall, he is my revered teacher. So I now request Sir to please chair this session. Sir, please.
Okay, thank you. Good afternoon to you all. It is my pleasure to chair this session. And the speaker is Dr. Nimai Misra. He is currently an associate professor in the Department of Chemistry, Institute of Chemical Technology, Mumbai, Indian Oil, Orissa campus, ICT, IOC campus. Dr. Misra completed his MSc in Indian Institute of Technology, Madras, received his PhD degree from National University of Singapore, NUS, Singapore. He was a postdoctoral fellow in Los Alamos National University, USA, and Italian Institute of Technology, Geneva, Italy. Before joining ICT, he was an assistant professor in SRM University, Andhra Pradesh. The area of his research interest is high temperature colloidal synthesis of different semiconductor nanocrystals, synthesis of peroxide nanocrystals, and study of their optoelectronic properties, optoelectronic applications, light emitting diodes, photocatalysis, photodetectors, and thermoelectric measurements. He has more than 50 publications with an HE text. This I invite to start his lecture. The time allowed is half an hour is the time. So after 25 minutes, you stand up so that we will know that
around 20 minutes you stop. So I will get it. So I am putting my time. But this will not work, right?
That will not work.
That will not work. Only slide change. Okay. Okay. Thank you so much. First of all, I'd like to thank the convener, Professor Vigyan Das, who has kindly invited me for this Orissa Chemical Society. Thank you so much, and really wonderful gathering. I think all the people across Orissa, they came here, the chemistry people. But I was talking to him, the timing is a bit odd. This is a holiday timing, so unfortunately you can see, I'm sorry to Professor Maiti and Professor Pradhan, they're supposed to speak, but you know, my relatives are coming. I have to go to the Bhubaneswar railway station to pick them up. You know, after shifted to Bhubaneswar, it's become joy and also pain, because many people want to visit Puri, they're coming to my home. So that has been happening. My mom, my in-laws, my cousins, they're the last 2 days, they just went today by drive. 2 of my close friends are coming. So that's how this changes. I'm really apologize for that. Thank you. And also I can see all those, very famous professor from this Bhubaneswar and Orissa. Professor Jana, thank you so much, sir, for your kind introductions. Also, I'm very thankful and very happy that 2 of my teachers are here. In front of them, I'm giving this talk. Professor A.K.M. Mishra, sir, is here, and Professor Ruchita Portner, ma'am, is here. So, it's my privilege, so I can speak something in front of them. So, let us, without further delay, let us discuss. As Professor Jana has mentioned,
I'm coming from Institute of Chemical Technology, Mumbai, Bhubaneswar campus, and a part of our campus is actually here in CET campus. Our instrument facility are hosted here. So I often come here as a facility in charge. I often come to CET campus to look after our high-end instrument facility. So today I'm going to discuss about the perovskite nanocrystals, a new class of materials, a new class of semiconductor materials that's also called quantum dot for the next generations of electronic applications. So these are our state-of-the-art facilities that we have installed because we are still functioning from a temporary campus, which is IT Kharagpur Extension Center. So our all high-end instrument facilities actually is installed here. When you have time, Professor Das can take you or have a look. We have all hydrogen 10, XRD, NMR, single crystal XRD, GCMS, everything is figured. So there are on payment basis you can use it. Everything is functioning. If you have any difficulties, just write to me, and there's an email given on the website. So feel free to use this facility, which is open to all. So with this, I just want to mention, but anyway, I have been doing this in every gathering. Let us stand and make our voice against what happened in Article. A heinous act to kill a woman doctor. And heinous act is happening in our academia. It is our time to stand very firm against the crime against women so we can make a good society. So we have been doing this in every conference to somehow make this awareness. So that's brief note. So now come to this discussions. Okay, I'm going to discuss about the semiconductor nanocrystals, which is also known as quantum dot. You can see in 2023, these three professors, they have been awarded Nobel Prize. And I'm fortunate to Professor Boundy. He's my supervisor, so academic grandfather. So my boss from University of Singapore has did his PhD with Professor Munji Boundy. So all this year we have been working in quantum dots, during my PhDs and postdocs we have been talking. We always have been discussing when Munji is going to get Nobel Prize. It happened last year. And these tiny dots, why they are given Nobel Prize, you can understand. The Labrus, which is in the left, in the middle, Ekimov in the left, and the Munji Boundy from MIT on the right. They discovered this tiny quantum dot, okay? And those have very excellent optoelectronic properties, and that can be useful in different ways. Like we can make them in devices, as well we can have them in biological applications. You can see I just given an example from this Nature Chemistry paper. We can give a summarize how these tiny molecules, it is actually called inorganic molecules, like organic molecules, made of like few atoms, 10, 20, 100 atoms. These are like 500 to 1,000 atoms, inorganic molecules. When they come together and they are semiconductor, their optoelectronic property dramatically changes and make them material useful in across spectrum. Either we can make use them from biological detections, diagnosis, imaging. You can use them from the devices. One of the most common example or uses of this material is display applications. So you can see the LED, the QD LED. Samsung has put forward this material in QD LED televisions, and these people contributed how to make these materials, very easy chemical approach, and that's why the Nobel Prize was given in last year. So the year dot, you can go through this article, lots of information you can gather from there. So I'm trying to connect you my today's talk, why this semiconductor nanocrystals. In the title also there are perovskite semiconductor nanocrystals. So these are conventional semiconductor nanocrystals, which many of us are aware of those things. Those are cadmium selenide, cadmium sulfide, zinc telluride, right? 2635 semiconductor nanocrystals. But very recently, last 7-8 years back, there are another class of semiconductor nanocrystal emerges. Those are called perovskite nanocrystals. So these are like made of a lead halide kind of material. So why I'm putting forward here is this perovskite is a new generation of semiconductor nanocrystals that going to change or that can open a new avenue of different applications. So that's going to connect it. So before that, let us see what are semiconductor nanocrystals, because there are some students in the back. So for them, these are semiconductor nanocrystals. Those are very tiny in size. Their sizes are more, most of the time less than 10 nanometers. So real TM images you can see, it is not very clear. Looks like, and this is a schematic shows these nanoparticles. They are surrounded by surface capping groups. So these are organic molecules. Make this molecule stabilize in solutions, and also these organic molecules helps us to play with this nanocrystal. So either we can attach to some biological body. So for imaging, also we can play with the surface ligand to make a high efficiency devices. So the surface chemistry is very important. These are real images and real TM images of this material. Then, why this material is so interesting? Because of this quantum confinement. There is a high school physics now. When we studied, it is like our BSc quantum chemistry, particularly in the box. Again, sir is here. He's a very expert of fluorescence spectroscopy. So you can see this material has very narrow initials and very broad absorbance. So the solid line is absorbed. So it absorbs very good amount of solar spectrum of light. And the emission is very narrow. And because of the why it is narrow, because this quantum confinement and because of this, the band gap. And what is the quantum confinement? So this is a bulk material. When you go to the nanoscale, the energy level got discretization. So that's why we call quantum confinement. That's follow particularly in a box model. But looks, whatever so far I have said, this material is fantastic. Nobel Prize is given. LED devices has been made. Those are in market, like television has been made. But they are not all good about this material. There are several challenges are there about this material. You can see, so what are these challenges? Still the people are working on this material. So you can see the semiconductor materials, which are very good, very robust, but if you put them for some times in open atmospheres, so their surface cause oxidations, right? So that's become a problem for the semiconductor material. Once they are very happy initially, but once the surface goes oxidized, the photoluminescence property, electrical property drastically gone down. So my material is no longer is useful. So that's the problem. So how to overcome all these situations? The problem is that a bare quantum dot is not at all good. And then people came up with a new approach. It's called core cell quantum dot. So what is the core cell quantum dot? That I try to connect you guys with some common examples. People are very fond of in Orissa. This is called kakra pita, right? So all of us are aware of that. You can see in the kakra pita what happened. Inside you have something, some stuffing is there, and outside there is a coating. So the core cell material is something similar. While my core material is different, which is inside, and cell material is different, which is outside. In the same thing, you can also try to connect the samosa or chop, but inside another material, outside there is a coating. So protect the inside material from the outside one. Even more relevant example, a few days back, is an insane rain was going on in Bhubaneswar. Why does it rain? We try to put a raincoat, so protect ourselves. So when we protect the secondary cell on top of our first material, and so the stability got enhanced. So that's why the core cell concept came from here. And so how in this case, in semiconductor nanocrystal, what is the coating? In this case, the coating should be another semiconductor material. If you see the schematic, the red color one, which is a semiconductor nanocrystals, it is called bare quantum dot. You can take an example, cadmium selenide. Now I am putting another green color semiconductor, a different semiconductor on top of it. So that's called core cell semiconductor nanocrystals. So what actually makes new about this core cell semiconductor, what is actually exciting about the core cell semiconductor nanocrystal, that due to this cell, we can minimize the oxidations on the surface of this core material. And thus this coating helps us retain the photoluminescence property, optoelectronic property. So I can use this material for devices. Let's say LED. One of the most applications of this I have been talking, that is the LED. So I hope I am able to make you guys understand why core cell. But still there is a problem. This is the application that I have mentioned. That dye-sensitized solar cell, phosphor as a laser, light emitting diode, bioluminescent tissue imaging. But still there is limitations. So there is another phenomena in the fluorescence spectroscopy we can notice. That again, maybe all of you are aware of that, but I think again sir is expert in fluorescence spectroscopy. You must know that when we see this material at a single particle level, when you see any fluorophore at single nanoparticle level, there is a phenomena called blinking. Okay, so what is a blinking? Like that, our eyelid often closes and opens. That is something called blinking. We cannot open our eyes constantly for a few minutes. So that is something called blinking. Okay. So in these nanocrystals also, those are highly fluorescent. They often goes to the off state, again coming back to the on state. What is on state? When they are giving light out. That means when you are getting fluorescence out, it is the on state. When they are not giving light out, that is called off state. How on and off state can be distinguished? Again, very simple, radiative recombination and non-radiative processes, isn't it? So even though the core material is not good, so we put a cover like a jacket. It is improved the stability as well as minimize the surface oxidation. But still, there are another big issue challenge still remains, which is called blinking. So we have to find a way how to minimize the blinking. Now you can ask me again, that what is the big deal? Why people are bothered about the blinking? Why you need to minimize the blinking? Because as I said, this material have been used in LEDs. We are desired material is blinking free. If material is blinking free, that means I'm giving 100 photon, I should get out 100 photon out. Quantum yield should be 100%. I should not lose any photon. So my efficiency will be, very good. So that's why it will be economical also. So I need highly stable, oxidation-free, blinking-free quantum dot. So normal core cell can give you oxidation-free quantum dot, but that is not sufficient in order to make this material completely blinking-free. So let's say, blinking quantum dot, that's the problem we try to motivate, you guys understand by now. But how to mitigate? So there's a new concept I'm bringing here, it's called core cell giant quantum dot. Now you can understand core cell. Now I think I have to inform you guys, but it's schematic to try to understand what is blinking. All of you just came over after the lunch, so our mood is something like that. Some of you have tried to sleep, some of you may not be, you are thinking why this man is discussing all those things. So you may not be focused. So our mood is swing. On different mood swing, that is also called blinking. Blinking means sometimes we are looking, our eyes is open, sometimes closed. So that's how you can try to understand that how the eyelid is coming off and off, that is called blinking. Okay. So that's the thing, once you try to open it, it's not possible. Continuously can open out, it is actually through human eyes you try to understand. I have discussed all this thing. Now, the scientific way to understand what is blinking is, as I told, that non-radiative processes. So these are non-radiative processes, they are called OJ processes, OJ recombinations, hot carrier, trion formation. So generally the fluorescence comes once we have one electron from the ground state goes to the excited state, and that creates excitons. And if this exciton recombines, radiatively you got a photon out, that is fluorescence. But instead of that, when you can create multiple charges, you create trions, and then you need to OJ processes, and it will also opens up other non-radiative processes. Thus you kills your radiative path, so you got a blinking state or off state. So these are scientific ways. So now let us try to understand. In the previous slide, I had given an example of a jacket. I give an example of kagra pita, samosa, pulling over and secondary coating, which was not sufficient. So we got another terminology called core cell giant quantum dot. By name you will to understand. Giant means very big, like that. I mean, a very big fat man, isn't it? So the winter in Bhubaneswar is not very harsh. One jacket should be sufficient. But if you go with this jacket to Kashmir, it's not possible. Now it is snowing there. What you need? Very thick jacket. So that's why it comes into picture, thick jacket. So Nimai, if I go to Kashmir and put a very thick jacket, if I am going to change, I will remain the same person, Nimai Mishra. Only my appearance will change. So same thing like that. We are going to put a secondary jacket on top of our semiconductor nanocrystals. Though it looks like very thick, very different, but remain the core material same. So the property remains same, but we are able to protect that material from the oxidation, from the photo reductions, from the photo oxidation, as well as suppress the blinking. That's the overall goal. So we can use this material for the LED purposes. So that's how all our research started from here. How to make blinking free quantum dot. This is the initial quantum dot, cadmium selenide without any jacket. Then we put a thin layer of jacket like a normal coat in the Bhubaneswar winter, that is called core cell quantum dot. But you want to mitigate the blinking, we need a thicker jacket, that's called giant quantum dot. Generally, what is giant? Again, it is a nanomaterial. Giant doesn't mean microscale material. The normal core material is 5 to 6 nanometer. The giant quantum dot is around 15 to 20 nanometer. But still in nanoscale regime, little thicker, so we call it giant. Now if you see, this is very pioneer what my postdoc supervisor in the Los Alamos National Lab in the US, who was a pioneer of this area, that once you put a core cell thick, core and thin cell of secondary material, you see lots of fluctuations. So these fluctuations are fluorescent intermittency. So this is an on state, this is an off state. So fluctuation between on and off, lots of blinking. But once you put a thicker cell on it, you can see that is constantly on over the time, the intensity of fluorescence. So that means if you put a thicker cell, the intermittency can be suppressed. Now what is the background about it? Now these all blinking phenomena are supposed to be occurring from the surface. So if you make your surface completely defect free, And if you increase the volume of the nanoparticle, you are able to mitigate the OJ process, the triad formations. Okay? So the blinking will goes down slowly. Understood? I hope I have given enough motivation about this core cell giant quantum dot. So in these areas, my research groups, we have been started working in different directions, so making blinking free quantum dot. There are some examples that I'm not going to discuss today, but what I want to show this core cell giant quantum dot here. When we are started independent career here, the core cell giant quantum dot or green emitting giant quantum dot was not reported. So we we invested our time in order to make blinking free green emitting quantum dot, blinking free blue emitting quantum dot. Now why this green and blue is not was not reported earlier? Again, I just trying to connect you here. Once you put a thicker cell on top of core, what will happen? The exciton which is generated the core, that will delocalize on the cell. So if you understand again from quantum mechanics perspective, there is an electronic tunneling. Due to the tunneling, there is always a huge toxic of the fluorescence. So this is the emission coming from the core. But you can see the moment we put a thicker cell, the emission, let's say I desire to have a material that gives me emission around 525 green. If you want to make a white LED in the green light, green nanocrystals, blue nanocrystal, red. But the moment you put on a green material, you put a secondary material, due to the leakage of electronic wave function, it got delocalized by emission huge toxic, like more than 100 nanometer toxic. So there is no way possible to get a blinking free quantum dot that can emit in the blue region and the green region. So how to overcome this problem? We have developed a process called a graded alloy core cell giant quantum dot. So the cell we are putting, it is not single cell, we make an alloy. And due to the alloying, what is happening, I am restricting my exciton in the core, not allowing it to go out to the cell. So I am stopping the electronic delocalization. So the emission is still coming from the band gap of the core. Whereas still putting the thicker cell, and due to the thicker cell, the blinking got suppressed. So in this that you can see we can develop a core cell giant quantum dot. This is a team images which is around 40 nanometer, highly blinking suppressed, and they can be used for their photo stability is done, also checked. We can use them for the charge term like photocatalysis. So these are the preliminary studies we have done. But most interestingly, what we want to show you here, that as I mentioned, that blinking free quantum dot was challenged, particularly the blue and green region. So in this work, what we have done, that we have demonstrated and we have developed a graded alloy core cell synthesis, and in this process we have developed a blue emitting quantum dot. So this is a blue emitting quantum dot. The sizes are around 30 nanometer on different cell thickness. The thicker one, still the emission is around 480 nanometer, very much blue, 465 nanometer, very blue, and you can see the blinking got suppressed. So this is the blinking characteristics, fluorescent intermittency. The thinner cell is still blink quite a lot, fluctuation. The thicker cell blinking suppressed, highly photostable. This work in collaboration with Professor Shomokanti Khatua in IIT Gandhinagar. We just published in Advanced Optical Materials just a few months back. So this is one of the first report. Sorry, it's around 20 minutes. Another 5 minutes, yeah. So that's I have already conveyed the main message, that we try to develop a graded alloy cell synthesis of core cell giant quantum dot, and potentially we can make completely blinking free quantum dot. So with this, I just also mentioned in the title, is this perovskite nanocrystals are the new quantum dot for the next generation optoelectronic devices? So let us see what is perovskite. Now perovskite, as a chemist we know, it is a AbO3, like calcium titanate. But in this perovskite, what we are talking about is a lead halide perovskite. You can see there is a cesium, there is a lead, there is a halide, AbX3 model. And why suddenly this material, these nanocrystals got huge attention? Because of this plethora of applications. If you try to follow some of the solar cell work, you can see the perovskite, the efficiency is going approaching towards almost 30%. The efficiency, even they have overcome the efficiency of silicon. And there are many other, so these are the real silicon devices and perovskite devices. These are real devices they are making, and there are several other applications of perovskite. But the challenges, so I'll come to the challenges. So why this perovskite getting attention over the conventional quantum dot? Because of their unique properties. They have very high photoluminescence, 100% quantum L. They have very narrow emissions. When I try to make this as a LED, I need really narrow emissions. And then broad absorbance. Again, if I'm talking about the solar cell, it should absorb quite a lot of light. Long diffusion length. Again, it's very important making this material as a device. You should diffuse your carriers. And then defect tolerant. This material inherently prone to have less defect, which is good. So all these make this material very useful in several applications. Thus, this material now actually making in a form in a compared to the conventional quantum dot. And near future, we are very hopeful. We just had a Perovskite Society meeting, last week at the NISHA. I believe Professor Pradhan will be here tomorrow. ISS is coming. Yes, he will give lots of information about the Perovskite nanocrystal tomorrow morning. He is very expert on this. Our area of semiconductor nanocrystals, you get more idea about Professor Narayan Pradhan tomorrow morning. So you can see, make this material quite unique. So these are the, again I'm going to end with another last few notes. So this is actually a routine slide, how this perovskite looks like, and their TM images cubic. Again, they have incredibly good optoelectronic properties, but there is a but. What is this but? This perovskite, which is very good in terms of their optoelectronic properties, but they are ionic crystals. What are the conventional quantum dot, cadmium selenide, cadmium fluoride, those are covalent crystals. In covalent crystal, very solid, rock solid. In ionic crystal, just like our table salt, they are very solid. But you put a spoon of water, what will happen? They will dissolve. So these cesium lead halide, they are very happy. The moment water comes into the picture, water become kabab ka haddi, they got separated, they got destroyed. So again, this is the problem. So problem is how to stabilize this material. So if we are able to stabilize it, it is, in near future we're going to see all the solar cell we're going to replace with this material. So again, we took the same approaches. We are going to make a jacket on top of this material without compromising the property of the material. So that's an extra protection. So we got extra protection for us. We take a noble route. So another 20 minutes, have see. So you can see we take a noble route. So for that, in our lab, we are taking two approaches. We are changing the completely new, we are developing new synthesis process. The conventional way of making this material is using amine as a surface ligand. Then we found, and there are other literature also supports, that amine is very good initially, but long run, it actually destroying the surface. So then we thought of, can you make the completely amine free, but which was very challenging, because there are very difficult to find appropriate replacement of the amine. But we found phosphonic acid is a good replacement of amine, and then we dig out lots of literature in the organic chemistry that how bromine source, that is we found that bromopropane is good bromine source, because we are trying to make cesium lead bromide. We indeed make a cesium lead bromide, and they are highly monodisperse. And this nanoscale paper we have shown that we can make down conversion LED, they are very stable compared to the amine one. But I want to show you something, and this is the last slide. So again in 2024, we have published in Advanced Optical Materials that again my initial motivation of this talk, we want to make blinking free quantum dot. So in the perovskite also, people are trying to use of this material in two major directions. One is solar cell, another is LED. LED again, if the material is blinking, it is not good. So we want to make blinking free perovskite nanocrystals. So we found that our amine free, which is a very cubic in nature, they are completely blinking free, very stable. On the other hand, the amine based sample are highly fluctuating. Okay, we have done detailed studies, and if you are interested to know the spectroscopy and how they are blinking, why they are blinking free, mostly it is, I just want to give a hint, because of its size, because it's a multifaceted. So exciton can be there are less possibility of Roger process and all, so it can be blinking free more stable. So we developed an approach in our lab that can make completely blinking free perovskite nanocrystal, which can be useful for other optoelectronic devices. So that's it for today's story. But we have been doing work, as I told, this is material which is not very stable. These are all publications we have done last couple of years. You can see we try to make this material even year-long stable. Okay, we found new additives on the surface that can make this material stable. Now again there is a catch. All these stability studies are in solution or thin films. Real challenges will come into picture when try to put them in device formats. Then we have to test their stability. So that things are now going on. There are several efforts going on in the perovskite community. So make this material stable. So with this, again, our group also tried to focus for perovskite material. Also lately, last couple of years, people tried to use as a photocatalyst. They got very good results. We are trying to focusing on CO2 reductions, even OER or catalysis with this material. Some nanoscale analysis, JPC, these two papers we have published in this direction. So anyway, this is some more fine. So with this, I think I am able to convey all of you that perovskite material is a new class of semiconductor material. Our emphasis was how to make stable of this material so it can be blinking free. At the same time, it can be stable in the environment conditions, so we can use for real-time applications. With this, I'd like to acknowledge these people. This is my former group members when I was in SRMAP. This is a new group member in ICT. And mostly the work has been shown by Akhil, who got graduated now as a postdoc in NTU Singapore. And some of the work has been shown with Rahul, who is a postdoc in Aiken University in Japan. So these three students has been graduated. These two are the main work, and the DST, CRG funding, startup funding from ICT, and all the facility, and my collaborator, Dr. Khadwal. Thank you so much for your attention. I'll be happy to have questions. Thank you. Yes, sir. Yeah.
What are the cells here?
What is that?
What are the cells? Organic or inorganic material?
What is the size?
Cell.
A cell is inorganic.
No organic.
No organic.
Blinking, does it mean that photostability doesn't link with?
A link with blinking. Photostability also link with blinking. So when you see the single nanoparticle, yeah.
Photostability, if anything is stable in place of light, then you can see
Exactly.
Energy difference.
Exactly. So what I'm trying to answer these things, you are right. But when you try to collect the blinking data, we have to constantly irradiate the sample. So even with this irradiation, sample got destroyed.
Here my question comes. About the thickness of the cell. You said thickness of cell blinking will be lesser.
Lesser, yes.
But if you change the material to same cell. Cell level.
Cell, okay.
It will be better.
Exactly.
Much better.
No, not like that. The core and cell, how it is supposed to be done, the core material and cell material always should be high band gap material than the core material. If it is same material, throughout the band gap is same. Okay. Generally the core material, let's say this is my band gap of core material. My cell is something this. I given a classic example, cadmium selenide core zinc sulfide cell. So cadmium selenide is this and zinc sulfide is this. So exciton is very much confined within it. It is very difficult to leak.
Yeah, no, I from your example, Singapore and outside.
So
thickness, samosa and aloo.
Right.
The thickness is different.
Thickness is different.
Thickness is small and aloo thickness is more.
Correct.
And samosa is more tasty than
right.
Okay, no, so what I'm saying. For that I'm saying.
Yes.
The cell is like.
After the lecture is over, you will enjoy.
Yeah, we'll discuss. Yeah.
Can I customize the thickness?
Yes, we can customize. This is all solution process, and so we can put layer by layer cell. Okay, let's say my starting is two different synthesis. We first synthesized core in a hot injection method, and then we took the core, clean it up, again put it on 3-neck RPF, and then we took the cell material. Let's say I'm putting zinc sulfide cell. So in my one syringe I have a zinc precursor, another syringe sulfur precursor. So one by one layer, it goes like few hours. So let's say 1 layer, 2 layer. If you stop 2 layer, it will be 2 nanometers, something like that. Depends on the how layer thickness. So we can really control it. And always inorganic material. Then on the outside, we have a organic ligands in make this material in colloidally stable. That is a surface ligands.
Okay. Thank you.
Yes.
This is my time.
Thank you.
But let us give it giving hand in favor of. Now I request Satyavan sir to felicitate Dr. Mishra.
Big cloud, okay. I'll take it to home, give it to my wife.
Side.
Next lecture will be by Devabrat Pradhan. It is my duty to introduce Devabrat. It is just homecoming for him. I think he was last month in Inaugural University to deliver a lecture. And Devabrat belongs to Orissa. He is currently a professor in Material Science Center, IIT Kharagpur. Professor Devabrat Pradhan received his PhD degree in 2003 from IIT Bombay under the guidance of Professor Maheshwar Saru. He joined IIT Kharagpur in 2010. His research area involves nanotechnology, synthesis, characterization, and applications of nanomaterials, solid-state electrochemistry, electrocatalysis, photocatalysis, biosensors, supercapacitors, fuel cells, and everything in his material chemistry. Right?
Yes.
He is an expert in all areas. Professor Pradhan has more than 150 international publications in referred journals, 2 Indian patents, 1 edited book, 2 book chapters to his credit. He was awarded with MRSI Medal 2019 by Material Research Society of India in recognition of significant contribution to the field of material science and engineering. Faculty Excellence Award 2019 by IIT Kharagpur for outstanding contributions towards teaching, research and institutional development. Agani Award in IIT Bombay for excellence in teaching physical chemistry to the first year BTech students at IIT Bombay. He was the founding and associate editor of Materials Express, an international journal on materials research published by American scientific publishers from 2011 to 2019. With this, I invite Devabrat to start his lecture. Time allowed is 30 minutes maximum, and after 25 minutes, I will be coming here.
Thank you. Actually, I'm not expert in anything. That's why Professor Jana mentioned. So actually, I am from material science. So I have to deal with different students from different disciplines: physics, chemistry, ceramic engineering, metallurgical engineering, mechanical engineering. So I have to tune to their requirements, and I have to work. There is no other way for me. So anyway, you will see that I mostly work on the energy, and people do not like also energy. But as you will see that the future next 2 decades, energy will play an important role without any other ways. So now you see that after China and US, India coming at 3rd rank in energy consumption. So you have to look the way to not using the non-renewable sources. So we have to find renewable sources so that probably we can manage our climates greener, or actually we do not create the climate that may hazard happening to the climates. So renewable energy, including the solar, water, wind, that has to play important role for future generation, and energy storage also will play important roles, batteries, supercapacitor, other things. So we work on energy related studies, and just coincidentally, Professor Jana was the chairperson of Orissa University my presentation. At that time, I was also talking about photochemical and photoelectrochemical hydrogen generation. So today, not today is different. Today different. So it will be, I will talking about fuel cell batteries like of this, and just now Dr. Misra was talking about perovskite nanocrystals. We the physics students of my group, they wanted perovskite solar cell because it is hot. He already mentioned that 30% efficiency has been achieved. In our lab, we achieved 16% efficiency with perovskite solar cell, not with nanocrystal but thin film, because we have to make device. So we also achieved the stability up to 1 year. 90% efficiency remains same. So there are many ways of energy conversion, but we mostly this solar energy, chemical energy, electrical energy, we revolve like that. So I skip those things. So I will talk about oxygen reduction. There I was talking about hydrogen evolution. Now I will do oxygen reduction. Minister now understand water splitting producing hydrogen, and nowadays this month December itself India started running the hydrogen trains. So but hydrogen generation also simultaneously requires oxygen reduction. If you want to run the train with hydrogen, you have to reduce the air or oxygen. Otherwise, you cannot use your fuel cell. It runs with fuel cell. Actually, you have hydrogen as a precursor or source. Then you have air, and now they will give you electricity. So, in order to make the fuel cells to work, you must have oxygen reduction reaction. That's why I will talk about oxygen reduction reaction. That is chemistry. Synthesis of the material chemistry and the chemistry is the topic of my talk. So, okay, let me skip. This is a simple hydrogen fuel cell, proton exchange membrane fuel cell. In the left side, you have hydrogen oxidides and produce proton and take the electrons out in the circuit and use the rod and bring the electrons here, and the oxygen you have to reduce in presence of electrons. Then if you can reduce the oxygen efficiently with 4 electrons, then you produce the water. Byproduct is water. You have hydrogen, that is what I was talking in the Orissa University. I work on photocatalytic hydrogen generation. Once you have a hydrogen, then again you have to use fuel cells to use the hydrogen to produce electricity so that you can run your car or vehicles or anything. So if you look at the different type of fuel cell, in all fuel cells in the cathode side, you see the oxygen. So oxygen reduction is very crucial and it is very complex. You need 4 electron process, and otherwise you cannot get it pure water. Otherwise you can get hydrogen peroxide, etc. So in all different type of fuel cells, you will need oxygen reduction. So for oxygen reduction, I will give an example of microbial fuel cells. That is what we have done with an example of oxygen reduction reaction, and that's why. And you can also use the wastewater as a electrolytes. And the wastewater, when you do wastewater, have like lot of pollutants and contaminants, so that pollutants can be oxidized to break down, and in the anode sites and the cathode sites, you reduce the oxygen or air. So this way you can clean up your wastewater and also produce electricity. But yes, efficiency and other performance, its power etc. is not very high. So it is used all for some light etc. Emitting some light etc. So this is the microbial fuel cell work. In the left side you have like anode where you oxidize the pollutants and produce the carbon dioxide. Then in the right side you have oxygen and you produce the water. And the bottleneck is there, instability of the voltage generation, fuel oxidation, and one of the most important point is the cathode reduction reaction in presence of oxygen. So again, oxygen reduction is a two process. One is 4 electrons pathway and second 2 electrons pathways. I am not going to details reactions etc. But not to tell you that direct 4 electron pathways is the linear process to produce water. In case of second 2 electrons pathway, you will produce hydrogen peroxide. Hydrogen peroxide will make the system corrosive, and also the stability will be reduced. So we work on material synthesis, we synthesize the materials. So as a chemistry, we synthesize the materials both by using the just simple by precipitation or hydrothermal, subthermal type of things, and the students will find that interesting. That means what you see the microscopic image, like this is a cerium ammonium nitrate solution, and I put some of the reactions conditions, and I use different temperature. Use different temperature, give different type of morphology. It is a very spherical type of morphology, these 2 temperature. Then you like a little bit of nanowatts and then like type of flakes, triangular flakes, and then going to 180 degrees centigrade, you have very uniform triangular type of sets, and then going to like a flower type of assemblage of the triangle of these materials. So when the materials undergo different type of morphology changes, the materials also give different properties because their size, shape, everything changes. Shape changes means it will go with a different type of exposed facets, and therefore the atomic arrangements of the different type of crystals is different. Their surface energy will be different, and when the heterogeneous catalysis happens, heterogeneous catalysis occurs at the surface. So when the shape changes, the properties of the materials undergo changes, and as a chemistry students, you can tune and you can produce the materials of different shape and size etc. And thereby you can say that what type of morphology, what is their properties and what type of application it can be used. These are our hollow spheres. Then hollow spheres are made up of these very fine particles of less than 5 nanometer. They will assemble to a spherical morphology of around 100 to 150 nanometers, and these are hollow. So in the TEM you see that in middle part is the outside is the more darker contrast, it is brighter contrast. So these are different type of morphology which are representing the different type of morphology. And then when we do oxygen reduction reaction, we study by electrochemical oxygen reduction, we always compare with platinum, because platinum is used as a standard or reference catalyst for oxygen reduction reaction. When we did the studies, then we found that the hollow sphere gives the better performance. In order to understand their mechanism, either 4 electron pathway or 2 electron pathway, we do KL process and to find this process, and we found that it is like the 4 electron process, and also we do EIS data to find the charge transfer resistance to find the performance of these things. And without this, we found that these hollow spheres give the better performance. That's why we did also one study for methanol tolerance, like in the direct methanol fuel cells. For example, in direct methanol fuel cell, methanol is oxidized at the anode, but during the fuel, in the fuel cell, some of the methanol can go to pass through the cathode, and in the cathode it's supposed not to do anything. But as you see, in presence of the platinum, so methanol is crossing to the cathode catalyst, and the voltage, the current is changes. That means it undergoes oxidation, and this is what that reduce the efficiency of the direct methanol fuel cells. And the right side is the stability. We know that platinum has one of the main disadvantages is that catalyst poisoning at the surface of the catalyst poisoning. Normally, pure platinum is not used. Platinized carbon or a platinum coated carbon is used, and when the system works, the surface of the platinum is carbonized, and that's why the efficiency decreases. So as it was this hollow sphere was giving the better performance, we make the composites, because ceria is itself not very highly conducting. So we make the composites with Gc3N4. So and again synthesis was conducted in a manner that I can prepare the composites with different ratio of the Gc3N4 and ceria, like pure Gc3N4 and with different ratios. Ratios indicates here it is written 5%, 10%, 15%, 20% of ceria into the Gc3N4 as a composite, where Gc3N4 is more conducting in nature, therefore it will give the better performance. And these are the TEM studies of the composite of selective sample which give the better performance. XRD etc. characterization was carried out to understand that things. And this is what the oxygen reduction measurements was carried out, and that is also used for finding their different type of performance, like electrochemical performance that includes the onset potential and the limiting current density etc. All these are measured. The electrochemical surface area is also calculated for all kind of samples, and we found that one particular ratio is give the better performance, that is 15% ceria to Gc3N4. All these EIS studies, and after doing the whole sample, we found that 15% ceria with Gc3N4 giving the better oxygen reduction performance as per all these experimental that means measured data. We found this is the best performance comparing to for the oxygen reduction process, and therefore again the methanol tolerance was studied the same way that before. Then we have used for microbial fuel cell. In the fuel cell setup, we used the selected sample. Not only selected sample, all kind of all these are used in the that means 6 device. And as we expecting our electrochemical studies, 15% ceria giving the better performance of the microbial fuel cell itself, like our basic electrochemical studies. So this is what, and in order to understand why the 15% was giving the better performance, when we do the XPS analysis, we found that the oxygen vacancies into the composites, that particular composites of 15%, giving the better performance on not only the oxygen vacancy but also the nitrogen contents in the Gc3N4 and also the ceria 3+ materials is giving the better performance.
Disconnection coding.
Okay, sorry. Sorry. So this is what we have found that the nitrogen, oxygen vacancies and pyridinic nitrogen was measured quantified with the nitrogen 1s spectrum of XPS, and also this area 3 plus, because XPS gives us the oxidation states and also their percentage of the oxidation states. So with detailed study we found that it is the nitrogen contents. I have time. I have not. Okay, this is what one of the examples. Coming to the oxygen reduction reaction is important also in the batteries performance. Like in the GKR batteries, you have two reactions involved: oxygen reduction reaction for discharge and oxygen evolution reaction for discharge. So as our Celia was giving a good oxygen reduction reaction, so we use that one for oxygen reduction, and we make a composite with NiO, nickel oxide, because nickel oxide is a good oxygen evolution reaction. So we make a composite so that we can use this composite for bifunctional catalyst. So in order to bifunctional catalyst, this is our Celia ceramics, spherical Celia nanoparticles. This NiO is our plate type of sheet type of structure. So by making the composites of different ratio, we prepare the materials to use this for bifunctional catalyst for GKR batteries. So with the different ratio of the NiO and Ce2, we have measured. And as you see here, so these are this is pure Celia, this is NiO sheets, and this is our the composites. So that is stem, etc. Detailed studies I am skipping this, and space also analysis was done. So then for oxygen evolution reaction, what we found that 50% of Celia and nickel oxides giving the better oxygen evolution reaction through the LSB and also Tucker's plots and other electrochemical studies, we found the better performance for oxygen evolution reaction. Similarly, for oxygen reduction reaction, also the same sample which equal percentage of the Celia and NiO give the better performance. So therefore that composites, selected composites was used for JKR batteries. And in JKR batteries, so we prepare, certainly in the anode part we have zinc, and the cathode part is our materials with oxygen evolution reaction and oxygen reduction reaction. So normally platinum is considered oxygen reduction reaction, and oxygen evolution reaction you use iridium oxide or ruthenium oxide as a pure material. So what we have done, so we compared with a set of with our sample and also platinum iridium, and it is the performance. We found that our materials has a much slightly higher performance, even though our material is simple oxides. So this was done with collaboration with Professor C.R. Raj of the chemistry department. So they did the battery applications. So this was the examples of the Celia, which is oxygen reduction, and in presence of the nickel oxide as a performance for oxygen evolution reaction. This is what the example of the second application for this is for batteries. First one was for energy conversion. Then coming to nitrogen reduction, because these are all, we are talking about oxygen reduction, and then I am talking to nitrogen reduction. So these are also similar things. But as we know, this as of now, the ammonia synthesis is one of the very crucial technology, and 1% of the global energy consumption comes for producing the ammonia. Because first of all, you have to produce the hydrogen, and then hydrogen is used for ammonia production, and ammonia has a lot of application. So therefore, we have to find a way to produce ammonia in a simpler way with an energy consumption, that means energy effective way. So for that they got Nobel Prize in 1918, etc. So this is a very crucial, because it is a very energy consuming process. As you see that 400 to 600 degrees centigrade with high pressures, you produce the ammonia production. On the other way, you can do electrochemical nitrogen reduction for ammonia production. I am not going to different mechanism. So major challenge of the electrochemical nitrogen reduction is that its low activity and selectivity, because we do not have a suitable electrocatalyst that could have a higher activity and selectivity. And again, it is a reduction process in the aqueous process. Hydrogen evolution also will simultaneously occur. So it is preferred that hydrogen evolution will occur automatically because that is what free energy process occur. Therefore, whenever you want to do a nitrogen reduction, automatically hydrogen evolution will take. So you need a catalyst which will suppress hydrogen evolution and facilitate nitrogen reduction. So due to this hydrogen evolution, the performance of the Faraday efficiency is always low for nitrogen reduction reaction. So in order to achieve the Faraday efficiency more than 50%, we need suitable catalyst so that actually ammonia synthesis by electrochemical nitrogen reduction would occur. So as of now, we have mostly around maximum 25 to 30% of Faraday efficiency we have achieved. So we have synthesized with different materials. The reason is there because this is a bismuth molybdenum oxide was chosen because bismuth has a 6p orbital and nitrogen 2p. They have a more strong interaction. And first thing. Second thing is that the bismuth with hydrogen bonding is also needs more energy. Binding energy is higher. So the bismuth will not produce. It will not interact for hydrogen producing hydrogen evolution. So therefore bismuth we have chosen. Molybdenum we have chosen because molybdenum is used in the natural nitrogenous process of producing ammonia. So therefore we have chosen these metals for producing the oxide because we normally prepare the oxides. And then by changing the experimental parameters, we have synthesized this type of morphology, by different morphology. And then we have used for electrochemical nitrogen reduction. All thorough catalyst, thorough experimental was carried out, material characterization was done. Then we have done the nitrogen reduction process, electrochemical nitrogen reduction, satellite LSCB studies. And at that time, during this process, automatically hydrogen evolution also will occur. So hydrogen evolution will occur, but now which sample will give better nitrogen reduction and producing more ammonia? So we have used endophenol process. Simple the electrolyte was used by using suitable chemical reagent, using the UV visible, and then as you see the photographs also, this is much greener. Much greener means that we produce more that produce more ammonia of this. And we found that at this point, at this voltage approximately 0.6, we have maximum production of ammonia then and less hydrogen evolution reaction process. And that was also again reconfirmed by the NMR studies because that was studied by endophenol process, and here we do with simple NMR studies. And our the Faraday efficiency is almost nearly close to each other. These two different processes of producing of the ammonia production. So, and again all the detailed electrochemical studies was carried out. We have achieved around the Faraday efficiency around 20% or 19% for producing the ammonia synthesis by using this catalyst. So now we have to look a more efficient catalyst that could produce us efficiency at least 50% to actually use for commercial purpose. So this is what about the bismuth molybdenum oxide for synthesis. So I think I have how much time? Then I will. Okay. So summary of this that so you see that material synthesis plays important roles producing the good catalyst, and then find the efficiency. So what I have shown you, that means in the renewable energy generation. So you need to have a suitable catalyst that could be utilized for energy conversion. And in addition to that, also we also work on some of the materials which are suitable, which is for energy storage, particularly supercapacitor, and sometimes also a little bit of collaboration with will do batteries. So here I have given example that you can synthesize some of the materials and then utilize for those applications. So this is what I have presented here by the two students. So these students, one for oxygen evolution reaction and oxygen reduction reaction, and other students here for nitrogen reduction reaction process. So this is the thank you. I
one or two questions, if any. Yes, sir.
What is the motivation for taking nickel?
Yes, we have looked at the literature. We found that nickel oxide is giving the better oxygen evolution reaction. That's why we have chosen it.
Because it
will not help any increasing any dilution.
No, it helps for oxygen evolution reaction because Ceria we use for ORR. NIO gives giving better performance oxygen evolution. That's why we make it two things to make a bifunctional material. Because in zinc air batteries we need bifunctional material. In the cathode you need a material catalyst which will do both things: oxygen reduction reaction and oxygen evolution reaction. Both things should simultaneously should. That's why we have to.
I have only one question. I was listening to your lecture. Your conversion of nitrogen into ammonia is thermodynamically favorable. Okay? Conversion of
Yeah, I could listen. Thermodynamically stable in the
conversion of nitrogen into ammonia is thermodynamically favorable because heat of reaction is negative. Del G0 also negative. But why do you require catalyst for conversion of nitrogen into ammonia?
First of all, nitrogen is a triple bond things. Once you produce it will bond with your with the catalyst, you breaking the triple bond of nitrogen is difficult task. So that's why we need the lot of heat and pressure in case of normal process, in the Haber's process. But if very high temperature.
conversion of nitrogen into ammonia is not kinetically favorable. Conversion of nitrogen into ammonia is thermodynamically favorable, but conversion is not kinetically favorable. It is passing through different intermediates.
So cutting to
Now that is also I agree. Yes. Yes. Then they use iron based catalyst.
because earlier in Haber's process,
Yes.
it was iron oxide.
Yeah.
Fe2O3 was the catalyst. Because nitrogen bond is very strong.
Very strong.
Nice talk, sir.
Okay.
Sir, I want to know on which basis your catalysis is good for best overall catalyst.
Yes, yes.
What is inside the sphere?
It is hollow sphere. Yes.
What is that?
Nothing is there. Nothing is there. Clean. Hollow sphere. Yes. Vacuum. Not vacuum. It can, if you put any gases.
The direction I had seen it is 100 mm. Okay, 100%.
Waste to accumulate the gas.
Yeah.
Let me tell you. If you put into gases, nitrogen will go inside. If you put any other gases, it will go inside. If you put air, it is
storage device.
storage. And you may.
What are you doing here?
Sorry.
In this case, how they are sure?
No, I am not interested about gas here. You wanted to know what is inside.
Yeah.
It is inside now. It is not vacuum. Let me tell you. Because it is porous. Even though it is porous.
Okay, I thought that closed plus.
No.
Closed sphere.
Not, it is not cloth. It is porous. Because this sphere is made up of again particles, very fine particles, and assembled to a spheres.
Okay, then.
Nice talk, sir. I want to know on which basis your catalysis is good for OR.
Yes. That is a good question. And first of all, you have to choose. First of all, your d orbitals. D orbitals, the pair of the free electrons should be available for producing or bonding with oxygen. And then oxygen has to have a adsorption and desorption to make it to happen oxygen reduction reaction. First one, your oxygen will form a bond, and then at the surface your reduction reaction will happen. Unless and until oxygen gases is not going to form a bond, you will not do the reduction. So that binding energy. So why I say platinum? If you look at the volcano plot, which atoms have a better binding energy preference, then only you have to choose. So selective materials, let's say molybdenum, platinum, tungsten, some of the materials in the volcano plot, if you see, that is the Nanocomposites plot. So in that theory, you will find that which atoms you should, which elements you should choose, which materials you should choose.
Okay, sir, thanks. But I have also a question.
Yes.
All LSPs compare at 1600 RPM.
1600 RPM, no, not 1600 RPM. We have different RPM.
Yes.
Different KL plots.
Sir, in your data, all
Yes.
are
Not all
potentials or currents are compared.
Huh.
But in rotation speed, increase in rotation speed,
Yes.
the onset potential and currents also increase.
Current will increase. Onset potential will not
Also
function.
sometimes changes.
Yes.
So
I prefer for kinetic study.
Yes, that is kinetic studies care process.
Sir, Kell not sufficient for kinetic study. Also kinetic current shown yes better.
Okay. No, that's why, see, in the Tafel plots, what we are measuring? It's kinetic studies.
Yes.
In the Tafel plot, the Tafel slope is nothing but kinetics of the reactions. So, lower the Tafel slope, you have a higher kinetics. So, that is what we confirm. Both the reason together you will. There was a question, Professor Behra also wanted to ask.
Due to shortage of time, so it is restricted. Please discuss with the Jaguar if you are free, you can discuss with him. So let us give a big clap for Jaguar for excellent day. Okay.
Now request Satyavan sir to felicitate Dr. Devabhat Pradhan.
Nice lecture. I enjoyed your last month lecture and this lecture.
Now I request Professor Vijayanandan Das sir to felicitate Professor Siddhartha for Mother Procedures.
I will come to you talk to you. I have 85 hours and 19 hours now, 4 o'clock, online. So I will now just take the Viva.
Could you recognize me first of all?
Yes. So, nice.
Dr. SKC.
Yes, I am.
Here is the announcement. Those who have posters 1 to 54 poster stands are there. It was numbered. Please post your posters there. Now move to next session. I request Professor Vijay Kumar Mishra to please chair the session. Professor Vijay Kumar Mishra completed his PhD in physical chemistry in 1981, DSc in surface chemistry in 2003 from Sambalpur University. He joined Sambalpur University as a lecturer in chemistry in 1987 and became professor in 2004. Chemistry, correlation analysis, organic synthesis, surface chemistry. He has guided 32 students for MPhil degrees, 24 students for PhD, 2 students for DSc. Professor Mishra was a reviewer for many national and international journals. Professor Mishra was member of editorial board of Journal of Natural Products, Anthem publication. Professor Mishra has published 170 research papers both in India and foreign journals and has a citation of 47743 with H index 32. Professor Mishra has also published a book entitled Precipitation and Dehydration of Hydrated Alumina co-authored by Dr. Varsha Das and Dr. I.N. Bhattacharya, which has been published by MS Lambert Academic Publishing on June 2, 2014. Now I request sir, please chair the session, sir.
So good afternoon to you all. Thank you, Professor Acharya, to giving me the chance to chair the session. Today we have 2 talks in this session, and the first speaker is Professor Maiti from IIT BG, IIT Banaras. Professor Maiti has received his Master in Chemistry from IIT Kharagpur in 1991 and PhD from ICS Kolkata in 1996. His area of interest involves polymer, nanocomposites, biomaterials, self-assembly, biodegradable polymers for renewable resources, and radiation resistance polymer, food cell membrane, polymer electronics, and is a master in polymers, and is published around 245 research articles, 28 book chapters, and 3 technical reports. He has 30 patents in his name, a good thing, and he has also been recognized with different prestigious awards like Advanced Material Awards by International Association of Advanced Materials in 2024, and Dare to Dream 4 by DRDO, Edward General Memorial Award by BioWeek 2023 in the International Conference of Biomaterials and Healthcare, and again there is a Satendra Bose Diamond Jubilee Scientist Award by International Association of Advanced Material, and he has many more prestigious awards. So now I request him to give his talk, and the topic is on sustained delivery of drug for better disease control, and my request to update it with the time. Okay, so add some time to discuss.
Thank you, Professor, for your kind introductions. And at the outset, I would like to thank the organizers, especially Dr. Das, for inviting me to what we are doing tonight. The last year. So, I will. Slides, right? Okay. So this is on. There is a change of gear from energy to the healthcare materials. So I would like to designate my work on materials chemistry for healthcare. And what we are doing that we are designing different kinds of material, inorganic and organic. And
can you use the microphone?
Thank you. And then we are developing different kinds of material, say inorganic and organic material, but they are being used for healthcare technologies and in different aspects, starting from cancer, soul healing, and other disease control. Oh, it's not working. One thing. Okay, so let me talk about that whenever we take a pill to control the disease, so the kinetics of the drug release in the bloodstreams follows this kind of the rate one. And there is a two limit. One is minimum inhibitory concentrations. Beyond that, the drug is effective for disease control. But if the concentration is slightly higher than this one, and then it becomes toxic. So, in order to be a drug to be precisely to be control the disease, so the kinetics should be like this, and the drug concentration in the bloodstream should stay between these two limits. So that's the conditions. I mean, as you know, I mean, especially in this winter, whenever we take, say, high dose antibiotics, definitely next day or after twice taking 2 pills of antibiotics, we have certain problems of the stomach problems and so on. And this is the reason is, I mean, it is exceeding this limit in the bloodstream, so that causes these liver problems and so on. And so there is a need to control the concentrations of the drug in the bloodstreams, and that is only possible if we have a delivery vehicles and which can control these things. So the delivery vehicles is required which will release the drug in this concentration limit. In order to do that, the polymer is the best particle or best materials which can hold the drugs through specific interactions and can release the drug systematically. So there are different kinds of microstructures and functionality present in the polymers which can specifically interact with the drugs and release the drugs in a very sustained manner or slow patterns. So there are functionalizations are possible. So we are indicated like this way. So there are functionality hydroxyl based on the drugs that we can manipulate it. And another one is the microstructures of the polymers. We can alter the microstructures and where the hydrogen bonded interactions can play the role where release kinetics will be following these traits only. And there are biodegradable polymers also whose degradation rate can be determined by using nanoparticles and so, and then it will release the drugs systematically. And then there are some barrier can be introduced through a different dimensional particle like two-dimensional nanoclay and so on. So they will be diffusion controlled, the drugs, and then it will be slowed down. And further, the nanoparticles of polymer can be generated, and depending on the surface area, so the release kinetics of the drugs can be determined or manipulated. And there are other ways, say the inorganic nanoparticles, which are layered in the geometry is a layered geometry, and one can hide the nanoparticle, the drugs here through specific interactions, so they will be more hiding there, and depending on the need, so they can be released from the systems. And sometimes they are wrapped with polymers also, and then again it will be further, the kinetics should be slowed down. And then first one we'll be talking about the biodegradations, where the polymer is biodegradable polymer, and they gradually biodegrade, and the biodegradations can be controlled by using nanoparticle embedded into the polymers. So there are different nanoparticles available, say 30P, and these are the imported clay. And we will be talking about, in this country we have a beautiful nanoparticle better than this imported one, which will be eventually helpful for bone healing and other disease control. If we put the few percentage only in the polymers, and then we can see that they are biodegraded SEM images, and once they are degraded from this morphology to this, and then if we embed the drugs, so they can be slowly released from the systems, and that controls this glitch. And here is a unique case. So this is a PHDP, polyhydroxybutyrate and valerate. If we use two different nanoparticles, around 4% into the biodegradation rate can be suppressed, biodegradation rate can be enhanced. And by doing that, by dispersing just nanoparticle, and we will be able to do it. We will try to understand why it is so, and then we have gone to the molecular mechanism that the two different nanoparticles form the different pH of the systems. Here pH of the two clays are around 7 and 8.2, and by that way the enzyme kinetics are different, and there is a lock and key model, so which will the biodegrade at differential manner based on the pH which is provided by the nanoparticle to the systems. So if we like, we can enhance the biodegradation. If we like, we can reduce the biodegradation depending on the need of the drugs that we would like to release in the bloodstreams and so on. And here we talk about the hydrogels. The chemistries are very simple. It's a polyurethane chemistry, diacylate and diol, and so we use this sometimes this cytosans kind of stuff, and then through an MR and spectroscopic technique we understand that what are the functionalities in the polymers in the cytosans, which is highly hydrophilic, and we are making hydrophobic by changing the amount of polyurethanes that is connected with the systems. And what are the advantages of that? So we can have a say good kinetics of the gelations by controlling the different amount of the polymers of hydrophobic polymers on top of the hydrophilic polymer. And another way of doing it, say by using different kinds of nanoparticle, we can control the gelations, or we can make the hydrogels out of it. So this is a hydrogel using water only. And then we try to make this kind of scaffolds. So these are the strength is high enough, and we can put these scaffolds in different bones and so on. I will show you this one. But another advantage of it, so there is a lot of space here. We can use this type of material as the catalyst, the nano catalyst, that we can do it. So mechanically they are very strong. We can even make these materials as cushion materials also. So here we demonstrate that we need to develop an injectable hydrogen, and injectable hydrogen utility I will be mentioning. So this is one of the demonstrations that we put the injections, and maybe after 5 minutes within this animal it is becoming solidified, so it is converted into the gel, and then next day we open up this animal and we can see that there is a hydrogel which was initially the solutions, and then it is converted into the gel. And the advantage of this, at the particular location, you will be able to place these gels wherever we like. So we put them in different parts of the body, the animal body, and sometimes we put it in humans also, I would say. And then the kinetics of this one, we have shown this one by using either by changing the nanoparticle or by changing the chemistry of 3%, 4% functionality, 3 and 6%. And by that way, we will be making different kinds of gel depending on where we will apply. Somewhere the gel strength should be low, and where the tissues are soft. Where the tissues are hard, the gel strength should be hard, and so we can have the stronger gels. And then we try to put these materials for cancer treatment. Whatever we designed a layered type of material. This is called the layered double hydroxide. And here there is anions which is replaceable. Through ion exchange reactions, there is a varaloxifene which is anti-cancer drug, known drug, and this is negatively charged. Through ion exchange reactions, we are hiding the drugs within the gallery. That has a very important implications. We can control the drug release rate by controlling the anions present in the LDH. And then we have different types of the release of drug from these systems, and we apply it to the cancer. So this is a model for the breast cancers. So we generate it, and the advantage of this slow release kinetics is if we apply pure drug, and then it is the cell systems, and so it is killing the cells, very few cells only. And the reason is the anti-cancer drugs are negatively charged, and the body cells are negatively charged, so they repel each other. So the pure drug, they don't go to inside the cells. That's what the killing rate is very low. And on the other hand, if we use these interconnected systems where the drugs are hiding, and then it is killing the large number of cells, because they can, and now the zeta potential of this is very near to the zero. So that's what they can go to the cells and kill the cells. And another most important effect is if it is injected into the animals, the pure drug, there is a huge weight loss, and that is well known for the normal chemotherapeutic patients undergo huge weight loss. The reason is the liver is getting damaged. They cannot, the patients cannot take food. There is a hair loss, loss of appetite because of the damaged liver here. But on the other hand, if we put it into the regulated systems or our delivery systems, the liver is, that lesion is very small, and that tells that the liver is normal, and there will be no further damage to the systems. Okay. So, I mean, we wanted to further slow down the kinetics. That's what we wrapped the previous systems with the polymer. So now this has gone down, so it is very less or very slow release is possible. And then we have done the similar works, that whether how it is going inside the cells and so on, what are the cell morphologies and so on, so that we are trying to show it here. And then we have done other the kind of the polymer reactions within the confined space. So this is a layered nanoclay. So part of the polymer chains we are inserting, and then so this is this polymerization reactions, diisocyanate diol, and then the chain extender. So at different sequence we have done the polymerizations. So we have by doing that, so a polymer is prepared here, and then we insert into this. By doing that, we have 4 different kinds of microstructures. So these microstructures, so their cumulative release rate or drug release rate is very differential. By that doing that, we will be able to control the disease in either in cancer or in other things, like as a biomaterial. So they will be nicely used. So here just we have shown these things for the students that are differential, the structural aspects that we will be able to do through the neutron scattering. we have a collaboration with BRC and the AFM and the POM. And then by doing that, what we can do, we can generate this kind of inhomogeneities, either small or large, through this chemistry that we will be able to do. And secondarily, we will be able to, if we put some of the nanoparticle here, which is two-dimensional in nature, which has X and Y, Z is 1 nanometer. So by doing that, we can able to release the kinetics rate very high to this very low. And depending on the need of the drug, that we will be using a different chemistry and putting the nanoparticle or not, that will decide the slow release of drug. And then we have lots of chemistries here. Say this is a cyclodextrin, which is highly hydrophilic, and we have done the polyurethanes chemistry on top of this, different number density and the size of this the polyurethanes. By doing that, we will be able to control the hydrophobic balance of the molecules, which shows very differential drug release kinetics from these systems. And then we have applied onto this the tumor control. What we did, we generate a tumor in the animal, and then we put the drug, which is an injectable hydrogel, just below the tumor. I mean, that's the efficacy of this one. And by doing that, what is important, if we have this pure drug, there is a lesion, liver lesion is very big, that liver is damaged. But on the other hand, if we use, say, this kind of vehicles to embed the drug, the same amount of drug, that the lesion size is very small, so the liver is very normal liver, and the patient don't have any problem. And here is the tumor kinetics. If we do not use anything, so tumor kinetics tumor will be gradually increased. But if we use our system, so this is completely controlled. So the next one is very important. I mean, here the chemistries are little tricky. So we have a block and unblocked systems. By doing that, so same CD, we generated different kinds of generations. It's called the third generations, where we have a lot of space here, and the outside is this polyurethanes. And so there are a lot of space, and through the specific interactions, the drug release rate is even slower than this one. So this is the kinetics here. And here, this another important part is, so as the drugs are nicely embedded here, so the kinetic control is here, we will be able to check or heal the tumor completely. I mean, here is a experiment. For the first time, we have demonstrated that the tumor can be healed completely if there is the kinetics of around 35-36 days of time, and with the advantage that pure drug it is damage the liver, but our control systems, so they don't damage the liver at all. That's the advantage of this one. So the chemotherapy patient will not undergo any nausea or the loss of appetite. So this is our new that the development that we have done. So this is the intravenous one now currently being used by the doctors, and patches was reported also. So this is the tumor over the skin, that is the melanoma, and so this was available before. So our development is we are injecting the solutions here. After 5 minutes, the kinetics is like that, it is converted into the gel. So now the gel is, its strength is sufficient, so it will remain there for a couple of days. And once it is here, it will inject the drug only at the site of the tumor, not to the other body parts. And that's the reason that the injectable hydrogel provides a best way of treatment, and that is getting controlled by the very damaged layer here, which is the conventional treatment right now. And here is also little less, because that's the transdermic patch, so they cannot penetrate the skins in a large extent. That's what I mean. Still the mild damage of the liver, but in this case, it is healing the tumor without affecting the liver. Liver is the most sensitive organ that we have. So the liver damage is minimum in this case when we have a subcutaneous subcutaneous treatment. And then we've done the other chemistries. So this is the linear dextrins, and if we change these linear dextrins, and then kinetics are very different, and we applied this material as the delivery vehicles, and then we see it either whether it is going inside the cell or not. We tag some fluorescence material with it, and then allow this material to go inside the cell and check the cell whether the cells are fluorescent or not, and we found that it is going inside the cell. So the vehicles are going inside the cell, and it is carrying away the drugs and killing the cancer cells. And this is the kinetics on real animals, and this is the how the tumors are healing. So, and then we try to understand that okay, after this healing, whether there is an infection or not, there is a biological marker. So it's called different kinds of markers like CD31 and so on, that will tell whether the tissues are infected or not, that we have checked. And another thing that I have done, I have started my talk with this experiment, that if we take a only drug that goes to the high drug concentration in the bloodstream, so that is the case for here. If it is the pure drug, the concentration is high, and say after a few hours, so after 12 hours, there is no absolute drug in the bloodstream. So in the chemotherapy, so 12 hours, all the drugs are gone from the systems, and there nothing is available for disease control. But if we have say drug delivery vehicles, and now so there are sufficient drugs are available even at after 1 day at time, and that will be responsible for the disease control in a better way. And that's the advantage of the drug delivery vehicles or systems. Then we have done these drug delivery vehicles for orthopedic infections, and many of the cases after breaking, when they were doctors, made a plaster, and sometimes infections occur. What we did, these infections, we created artificially by applying MRSA. This is the staphylococcus, and if we do not use any medicines, and then we create a small hole into the bones, and then we put the scaffolds I showed you before. We put the scaffolds in this small hole. The size of the hole is around 4 to 6 millimeter, and then here control, there is a huge pass here. That means it is getting infected. But now if we put the vancomycin, which takes care of the staphylococcus microbes, and then we can see. So this is our the implants, and then there is the nice growth of in 45 days, nice growth of the bones that is occurring. So here this implant is gradually releasing the drug of vancomycin, and then controlling the infections, and then the growth, the natural bone growth is taking place. So and this polymer is a biodegradable one. So there is two opposing forces. Biodegradable polymers are getting dissolved, and the bones are healing, and then it is nicely healed with a particular supports from this system. So this is the implant, like a kind of supports is providing to the bone. And then whether it is biodegradable or not, that we have checked it. So this is our implant, and after 20 days it is still there and releasing the drug. So after 30 days, it is this headache. So many of the polymers are biodegraded, and at 45 days, so the PLA, this is PCL, polycaprolactone, is completely degraded, and that's the reason for the gradual the bone healing in this case. Okay, so I will just maybe another 2-1. So we developed some sutures and stained material based on the safe memory polymers. So this is again the polyurethanes in presence of the nanoparticle. So here is the original shape, and if we twisted this material across a rod and keep it at 5 degrees centigrade, but if we keep it at again physiological temperature 37 to 40 degree, it's open up. But if it is polymer, pure polymer, so it is around 60% opened up. But if we put the nanoparticles, so this opening up of around 95%. So this is known as this the shape memory effect. We try to understand this reason behind it through the high temperature XRD and neutron scattering experiment. I am not going into that mechanism, that how it takes place. This basically the molecules can dance from this part to this part. If we change the temperature or the melting point of this one, and that resides within this just below the physiological temperature of 40 degrees. So we apply these things for biomedical applications. So as a suture material, so we cut a mark in the animal, and then we apply the stitch using the same material here, this composite one. So instead of straining it, which gives pain to the patient, what we did, we just apply the hair dryer, and then in 2 seconds and 6 seconds, it is automatically squeezing it, and because it is remembering its previous structures. That's the same memory effect. We applied for the sutures, and then we applied it for the state materials also. So within this tube, we putting our material here, and if we apply, if we put this material at 37 degrees centigrade, so this small stain will take the shape of this one. We have shown it through this one, lateral view and the cross section. So this material can be applied as a state, but we are unable to demonstrate it because we need a very large animal like pig or cow. So we do not have that facility at BHU hospitals. So we restricted for this one, but this is demonstrated nicely for these state suture materials. Here we did something on translational the drug from actual lab to debate. I am fortunate that there is Professor Manoranjan Sahu, who is a very famous colorectal surgeon, and so these are Manjubalkan. The drug is well known from the Choroxus time. So what we did, we make a kind of a stable solutions or the films or the patch pass through the electrospinning the processing techniques. So and then we apply this spinning over this animal. I mean, saying mice, we make a small the wounds, and then we apply all these three things, and then we found that this patch is working very nicely. And we understand this reason that patch is a very porous material as opposed to the films and so on. And then oxygenations can occur on top of the wounds, and pus can come out through the spores. So that's what the wounds are getting healed in a nice manner. And then he has applied to nearly 50% to the BHU hospitals, and they are extremely good. And we transferred this technology to one company, and now they are producing. Now it's in the market. So this is the demonstrations of these actual patients in BHU. So BHU hospital, he has done this experiment. So this is the size is more than 6 inches, and these patients are, I mean, they are from economically poor background. Size, that's what I mean. So the size is very large, but that can be healed in around 56-60 days time. It is being healed. Just I will quickly finish, and then we try to understand the mechanism for this one, how it works and so on, through this tagging a molecule with this conchovolcal, and then we have seen that okay, it is going inside the cell as a function of time. And so this one, we just understand this reason why it is so, and understand the histopathology, whether this treatment is actually operating or not, whether it is giving the pain or some kind of it is called as this TNF alpha. It is a well-known marker which tells you that there is any infection on top of the wounds or not. Okay, so just one slide. Then we have applied these ones in dairy. We have a campus We have a very full-fledged hospitals, AIMS level, and then we have a dairy also. So we applied those things using this gel. We applied these things, and then you can see it can heal the actual wounds of the big animal like the cow and so on. And in order to understand its efficacy, we have a control experiment also. The clinically things are not allowed to control, but dehorning is an experiment where the cow has 2 horns, and we cut the 2 horns, and that is under the same immunological systems we can control or we can compare these things. That we have done it, that this is a betadine, and our system shows very it is completely healed before say around 40 days, but whether control systems, which is the betadine, now the usual systems for wound healing, so that it takes around 50 days time to heal. So this is much better than betadine that which are being used. Okay, so we developed the different kinds of the material, starting from powder, gels, films, and the implant. Actually, this is I did not show it, but we developed some implants also, and showing that how our Indian clay systems are much better than imported one. Okay, so these are I have a large number of collaborations in IMS, Institute of Medical Science, BHU, and other areas. Say ERCs also, we have a good collaborations, understanding the structures and temperature dependence, expertise and so on, and the funding agency and the students are doing. So I will just finish this one, that the drug delivery systems to improve the quality of life. And so we have demonstrated in cancer, in wound healing, and in bone healing. So there are 3 aspects that we have taken. Thank you.
Thank you, Professor Maiti, for a very nice talk, presenting as if he has entered, like a doctor, he has entered the compound with the patient, with the drug to the patient. So 1 or 2 questions from the audience.
In the drug delivery system, you have not mentioned the temperature, because temperature plays a very, very important role in all kinetics process. But temperature variation can also affect your plots.
Yes.
So why you have not studied the temperature variation process?
No, because we will be using it for the disease control. So we have everything, we have done it at ambient condition. So only ambient conditions, because our temperature is 37 degree, and animals are also like that. So we have done it in ambient conditions.
What about the rheology of the
Yes, rheology, I haven't shown it. We have shown
because processability is very important.
Definitely, we have done it fully for say the gels and the mechanical strength also for this one. And so it is sufficient to apply applications process. So that we have checked it. We have applied it, but rheologically we have a
Rheology in water and flood system.
So this is on the hydrogels. This is hydrogel.
No, rheology study in what system?
In hydrogel. So
just to consider one delta.
yes, standard G prime.
He is also patented.
G prime, G double prime.
Doctor, we have been using a lot of polymers in while treating the patients, starting from your saline injection until your suture and all that, and now this biodegradable capsules. Recently there is a concern regarding microplastics. So in the process of using these polymers, are we unknowingly injecting microplastics into our system?
Yes, microplastic would be dangerous if it is non-biodegradable. Say if it is polyethylene, polypropylene, it is going inside even through say fees and other things. I mean, so but then they are damaging. But if we have the say biodegradable stuffs like PLA, which will convert it into the lactic acid, say for not very quickly, maybe not within say couple of months. After months they will be bioabsorbed. So because it will be either caprolactone or lactic acid, which is a component of milk. So absolutely no problem.
And polymers, I think they like semi-biopolymers you can say.
This is
Semi-biopolymers. You are taking dextrine.
dextrine also. It's all
not biodegradable. Okay, so thank you. Thank you. Let us give a big hand to Humanities.
Sir, now I request Professor Vijay Kumar Misra to felicitate Professor Roland.
So our next speaker is Malik. Professor Bhubaneswar Malik. He's from IIT Hyderabad. Professor Malik is from IIT Hyderabad. Professor Malik completed his masters at Utkal University and received his PhD degree from Department of Chemistry, IIT Kanpur. Afterwards, did postdoctoral research work in the University of Notre Dame, Indiana, and then University of Minnesota in Minneapolis. His research interests involve atomic level understanding of structure and dynamics of chemical systems, with specific interest in energy storage, materials and catalysis, classical and first principle molecular dynamics, machine learning, and microkinetic theory. He has more than 130 publications in international repute, in Journal of International Repute, with around 2,000 citations and H indexes 30. And he will be speaking on his talk is on computational modeling of petri gas for energy application, on energy storage or application of energy applications. Okay. So thank you. Time is 30 minutes. Try to complete it in 25 minutes so that we can have some questions.
Thank you for nice introduction. So, yeah, my job is for talking about computational. We have lots of excellent talks. So, also lots of experimental talks are also coming. So, little bit of change of track. So, first of all, I would like to thank from bottom of my heart to support my everything, my travel, my stay, nice, hospitality. So I am from here, but still I felt like I am guest here. So thank you very much for this one. So my earlier research is based on very the water and water aqueous solutions. Last few years, we basically jumped into this area. Before going to those areas or what we are doing, so there is some suggestion from the organizers that I can tell a little bit about the computational methods. So I will not take much time. I will try to introduce this type of methods, and usually this is helpful for the students and those who wanted to enter this area. But already many of you might be knowing this one. So then please bear with some of the repetition of your expertise. So basically there are three types of computational methods we can think of. So one already in first principle simulations. So many people call it DFT simulation. If you tell first principle they may not understand, if you tell DFT they can understand. Because DFT is very popular, so due to its capability to to be used in many areas. So another is classical molecular dynamics. This is a very under discussed area. So maybe I am wrong, but in earlier case, whenever we have very few atoms, then only we can apply those areas. But we need the more accuracy. So that is the way electronic structure works there. But when we have to do in a large scale, suppose you wanted to simulate million numbers of atoms, so then you cannot use that first method, because first method limited to 10, 20, 30. Basically it depends on what is the power of your computer. And second one, you don't need the electronic degrees of freedom, so we need the nuclear degrees of freedom. So basically atom can be considered as the nuclear degrees of freedom and electronic degrees of freedom. So when I don't want electronic degrees of freedom, I can go completely the nuclear motion way. So when I am talking about nuclear motion, I cannot talk about the reaction. So that's why there is some mathematical details will be required to introduce that electronic degrees of freedom to the nuclear degrees of freedom. So another is called, even in the scientific paper they also wrote, this is a combination of the first method and second method. So basically if you want electronic degrees of freedom and nuclear degrees of freedom, but you wanted the reaction. So that means obviously the first method can be less number of atoms, second method is more number of atoms, but it will be in between. So basically these are the areas we are working on last many years, and we wanted to explore or in a dynamic way. Dynamic way means anything we want except electron if nuclear coordinates are changing with time. So that's the dynamic I am talking about. So that means I wanted to track the movement of one particle at initial time one position, but after some time it changing its position. That's the dynamics I am talking about. But the electronic dynamics and nuclear dynamics, they are completely different. I am not talking about the electronic dynamics there. But still here, whatever the approximation in quantum chemistry we read during our first year of BSc, that still it is valid. So that means Born-Upon approximation is valid there till whatever research we are going on. Okay, so let's talk to some materials here. So this part I am not expert about, what I am showing the materials, but in the paper I saw, but I never synthesized anything. So this is the material we are talking about. So this is called the top-down approach. We have the material, but we want to do the simulation, how we can do that one. So from the material, even second picture is also not my expertise. So that means your morphology analysis, how that material will be there. From there, when we come from the morphology to the single atom, there is a huge journey. There are lots of mathematics, there are lots of approximation, but still as a computational material science or computational chemistry we are surviving. So because we wanted to do in a such a way that from top to bottom we will come, but still when we compare the properties, we will go from bottom to the top. Because if whatever property that material is showing, I will do the optimistic simulation. If I cannot get that property, none of you will believe me. So that is the difficulty of the one computational approach, but still we can do that. So some of the other properties we can see. That means yes. So here these are the called continuum theory, not my expertise. Then there are multiphysics phase probe. That also we are not talking about. Basically, if you don't want after atomistic level, those theory can be applicable. But after that, it is called cross grain. Cross grain means if you have a water molecule, it has three sides. Oxygen, because the talk I think since morning we started with H2O, so that's why I am talking about. Rather than three atoms, I can think of one side or one spherical object behaved as water. That is the approximation I am talking about. You can tell that is wrong. Yes, it is wrong. But it can keep the properties of the water. That's what post grading I am talking about. After that it is called classical, then reaction, then finally at the end we see the ab initio. Now when you see, this is the slide which will give idea about from materials to atomic, this is a huge journey. The story does not end there. So what is the another story? Now you see the x-axis, this is the length scale, and y-axis, this is the time scale. So that means if you want 2 micrometers material, you cannot simulate the 2 micrometer material. There is no computer in the whole world. But what I will do, I will take 2 angstrom, 10 angstrom, 20 angstrom, maybe I can go 5 nanometer, not more than that. But when I am doing that, I have to make sure that what property I am getting from that material, I should get the same similar property so that I can compare it. So initially the idea is we will compare many of our properties exactly with the experiment. Beyond that, when some properties are not available, we can apply our theory or computational effort to predict some new properties. So this is the way computational material science goes on. Now we see, whenever we are talking about one more thing, whenever we are, this statement is for the students, whenever we see any reaction, it is spontaneous and any color change, but still it is 1 second. If you see, whenever we are talking, we take some reaction or reagent, we put it in 1 second, but I cannot simulate here. But 1 second time in the computer, that may be only one paper. If you are surprised, I don't know. That may be one paper, but even that is in the scale of microsecond. 1 or 2 paper in the whole world, one can attend with the largest computer available in the whole world. So that means if I want to see the 1 second reaction, I have to do something so that it will show me in the femtosecond. That's why another area or another thing is there, but it's called we are the more kinetic energy, molecule will be more apart, then or they will do the reaction. So that is the way it works. But to bring down to that level, so that is called machine learning. Maybe you might have heard that artificial intelligence machine learning. So the idea is to take the data from this, but data will be very small. So you cannot have a huge data for data. So basically, for example, I wanted to simulate one process which is, for example, maybe 2 seconds. But I will take the data from the femtosecond level, but I will do that, my algorithm develop, so that my method will give with the 2 seconds time scale. So that is the way nowadays you can see that starting from the first principle or classical MD, taking that method, then do the algorithm development, then make the method applicable so that it will give the accuracy of the first principle simulation. So for example, what I told, if you take the electronic coordinates, we are more accurate. That's what quantum chemistry or quantum mechanics is there. But if I don't consider those electronic coordinates, Newton is the king. I use this statement to the student, that's why it automatically came up. So what I mean here, if you don't consider the electronic coordinates, your nuclear motion if you consider, the Newtonian mechanics can be easily applicable. But if you are considering the electronic coordinates, nobody will care about Newtonian mechanics, because what is your maths, all will be coming to the picture, you have to take care of them. Taking care of those scientists, not those, easy, in mathematically, that's what I can talk about. Now this method, what it is doing, it is taking the data from the most accurate method, that means electronic degrees of freedom, and converting that method so that it can be used in the higher length scale or higher time scale. So for example, we will take a very 1 picosecond data, but we can convert that onto 1 nanosecond data. Whenever I am telling conversion, it is a very crude word. It is not the real conversion, it is a lots of mathematics involved there. So overall, this is just a message, or this is a mostly promotion of this area to all of you, those who are not aware of this one, but those who already know, they know much better than me also. Okay, so after this one, how we can use this data? So that means we use this method. So our group, initially we started with non-reactive systems. That means what we are talking about. So today we have the example how we can split the water to get the hydrogen, but you will be happy to know that we are doing without splitting how water moves. What is the hydrogen bond? How the hydrogen bond evolves, or how the changes of environment will change the properties of water. So last few years, that's what I am talking about. One area we are doing it, production or catalysis, I mean there. That means we are producing something in form of energy or in form of a molecule. Another is storage battery. Again I am telling. So I am not expert none of these, because my training is not from electrochemistry, not from catalysis, not from battery, but we are applying or we are taking care from the computational point of view. So maybe if you ask me who is the expert here, my HOD and Professor Martha is sitting there. So he is the one of the eminent personality in this area in the battery field. So initially I learned many things from him. He is current HOD in our department also. Okay, so this is a homogeneous and heterogeneous system. So like earlier we have the talk from, regarding ACR, OER, or even NRR, or even battery and all the things. But what we see, can I set up whatever method I showed you based on those methods, but we want to replicate the way one experimentalist can think of. For example, suppose one reaction is happening in the acidic medium. I should not do a simple DFT calculation, tell that these are the results from my DFT and these are results from my experiment colleagues. They did the accurate method or accurate experiment with the acidic medium or in the basic medium. So I have to do in that way. So what is that solution? That is concentration. I have to take care the concentration of the solution, even I am taking 50 water molecule or 40 water molecule or 30 water molecule, because those stoichiometries should correlate, otherwise I am not doing the correct thing. So basically what I will do, I will compare with apple with orange. My experimentalists, they are doing the apple experiment, but I am doing the orange. At the end, many people you will see that. I am not criticizing them. What I am telling, so we try to understand if any experimental colleague will see the setup of computational, they will happy that I use 1 molar KOE solution for my HCl reaction, and also the computationally this is done like that. So this is one of the area. Obviously I will not talk about that one. So another is also we are talking about very similarly the N2 activation, N2 to NH3, and also some of the kinetic work. So this is basically it is inspired by when I was the student in Utkal University. My teachers are here. So I was very afraid of chemical kinetics because Professor Siddhas was teaching. Always I was telling, sir, it is too difficult for me. But I never realized that time that after so many years, I will track by that chemical kinetics, and we are trying to learn also with my students. I am learning how to develop one microkinetic model from the delta G. That means if I know free energy of the reaction, how I can develop a kinetic model, because this K is the forward rate constant and K is the backward rate constant. Now you just take any chemical kinetics example, reverse this one, because reverse of K is the time scale. So now I am taking this K root to get the time scale of that reaction rather than doing molecular dynamics. Molecular dynamics, I wanted to do the simulation at some time and thermodynamic conditions. So this is the one of the area. So from 2017 or 16, what we saw that okay, there are many gaps are there. But what does that mean? There are many studies, but whenever we are talking about dynamics in the electrode and electrolyte, there are very few studies there. For example, if I ask any material you think of, if I want to ask a question, how ions move in that electrode, there is also very few experiments are there, because sometimes it is difficulty level of doing the experiment or isolating the system to go to that ion to find the diffusion coefficient. Or even nowadays maybe it is very relatively easy there. And in the liquid state and solid state, and most importantly interface. So what reaction is going to happen in the interface of your electrode and electrolyte? So that is the way. I didn't mention one more thing. So when I am talking about this one, all the reactions are electrochemical. But when you are talking about electrochemical, this is a very standard method for the experiment. You apply the potential, you see the product, but there is no standard method for the computational. But if you forget about electrochemical, all the reactions are not electrochemical. 99% papers, unfortunately, because as there was no method, everybody produces the result from the non-electrochemical computational simulation, but they compare that one with the electrochemical one. So basically, what is the rule there? Because they are always thinking that the barrier will be less. If you apply the potential, your reaction will be faster. But not always the same case, because this is a parasitic reaction on the interface. if you charge the interface or electrify the interface, all the reactions will be different. So that is the, when we see that one, that means we are entering, it is very difficult, it needs lots of computer time, but we started to see that one, whether we can do some type of reaction for those electrochemical interfaces. So these are more or less last 5 years we are talking about. So basically every 5 years we are changing our, whatever our interest, going behind the, whatever the world wanted to, because these are things, I don't think this is any of my idea. So what are those ideas? Basically ideas coming from the students. One fellow came that, okay, I want to do EGR, even electrode and electrolyte also, the student told me, we wanted to work on the battery. Then I told, I am the computational chemistry, I don't do the battery reaction or anything, but we can do the dynamics from the battery area. Okay, so what I will talk about, this is little bit of introduction, I may not do the justice combining everything, but even what I can assure you, any of you, wanted to know more, I will be helping. I am talking to some of the, some of the teachers also from the colleges, or some of the, I am talking to the organizers also, and also Dr. Das. So if you wanted, we can arrange any workshop inside Orissa also. I can take care myself. You don't have to worry about me or even my group. I will bring the student. If you wanted any workshop, only the arrangement you can. That is the request. Right? It is not part of this one. So I will be happy to help. So how to starting from this scratch to go to, basically it is a top-down approach, but I will teach from the down, then going to the top. So that is the way I can help if anybody interested. Okay. So what we will do, or we will discuss this one. So these are, as I told that this is a very, very complex system from the theoretical point of view. So I cannot comment on the experiment. Even I heard that, Professor Martha told also this is very complex. It is not like that. So I can give one example. For changing lithium to sodium, we don't have to do anything. From sodium to magnesium, we don't have to do anything. But think about the experiment. From sodium to, or lithium to sodium, sodium to magnesium, it is a huge, experimental different setup. So we see it is a point charge. It has +2 or +1. But experimentally, it is very different. So that's why I can do lithium, I can do sodium, I can do the magnesium. Only thing is time scale I have to check. So that's why how fast lithium is moving, or how fast or how slow magnesium moving. So today's one I just picked some magnesium ion battery. But if you tell that what is the big deal of this one, but as I told that I can do lithium, I can do magnesium. But first criteria of our research or any computational, if you do any unknown problems or any problems world does not know that one, you cannot publish. That is the true fact. So that means they will tell, oh, this material is hypothetical. Nobody synthesized, but why you are doing the computational? So that's the first one, because as I told that if somebody wanted to do any computational, you have to see that, okay, if that material already exists or not. And then you bring the concept there. So here, there are liquid electrolytes, there are solid electrolytes, and there are electrodes for magnesium ion battery. So I will talk about these two materials. Even I am not the chemistry material science, but we are doing the computational material science. So magnesium, cobalt, SiO4, magnesium, nickel, SiO4. So these are silicates. So what we see this one, these are polyanions. So that means, so the polyanions, they have some role to make magnesium transport through the electrodes. And the same concept also we apply in the solid electrolyte, but for liquid electrolyte this is a different. I have 2 slides, if time permits then I will talk, otherwise I will skip that one. So what is the idea is, we wanted to see how magnesium enters to the electrode and also come out of electrode. So basically it is called intercalation, de-intercalation. And how much time it requires or what actually it is doing there. But as I told, I need some of the experimental studies. So because from this slide, I just copied from the experimental part. So what they report? So they are reporting here manganese and cobalt. But for my convenience, I took the cobalt one because I have to pick some material here. And I kept that all other things are same, that is SiO4 and magnesium. and they reported the voltage at 1.6 and 3.61, and also this is your charge capacity and other methods are there. So from here, I am not comparing except the theoretical capacity. So we did some DFT calculation before going to the dynamics, whether that material, whatever they reported, they are giving the correct theoretical capacity or not. That's what we check. Otherwise, we just check the cell parameter. Otherwise, these things we cannot calculate. These are capacity, it is not there. But what I am interested in, only magnesium, how magnesium is moving. So that is the concept. Okay, so another material. So here also it is synthesizable, it is existing. So we compare cobalt with nickel. Fortunately, we wanted Mg and Si for common, and we replace cobalt by the nickel. And now you see the periodic table. That means cobalt is before the nickel. That means nickel is little bit size is more than the cobalt. So that size really changes how magnesium will move. Because this is, if you go back to the structure of these materials, so there is a octahedral, there is a tetrahedral, there is a connection of both, and magnesium moves in between. That's what experimentalists will tell. We wanted a little bit more than that. So then how it is moving? Okay, so this is the way we see. And also what they report, as compared to cobalt, and magnesium moves little bit slower in the nickel. So that is obvious because due to the size, maybe that is happening. Okay, so these are the our structures. I mean, already it is there. There is nothing problem with structure. We just took that one, and here there is no dynamics. Whenever dynamics come, I will let you know. So this is a normal calculation. What every people know that one. And you do the DFT calculation, periodic system, and other things. And then the idea is how do Mg2 plus ions move in these electrode materials and what is the mechanism of that. Okay, so we did little bit advanced level. As I started, this is part of the again method. What method development I am doing? We know first principle method, we know classical method, we know first principle molecular dynamics method. That is not sufficient. But what we talking about, we wanted magnesium in the nanosecond time scale. So if you talk about femtosecond, because femtosecond particles don't move, and this is solid material. Unless you go beyond nanosecond, you cannot study this stuff. I will show that. So what we did, we wanted the accuracy of DFT level, but we want to go the nanosecond time scale. That's why machine learning is coming to it. It is very new to me. As you know, last few years only people started this one. So what we do, we started from the same first principle method, then generate a little data, maybe 1 month of data, 5 picoseconds, something like that. Then we developed the model. We went to the classical simulation. So what I am telling that FPMD, first principle molecular dynamics, is very slow. Classical model is very fast. In between, what we did, we used that deep algorithm, machine learning algorithm, to develop a method or develop a model which can give the accuracy of DFT, but it will run in the classical. I hope it is clear now. So then we did all this cycles so that at the end we saw the accuracy level of what first principle MD can give us, then what classical MD can give us. So this is the comparison. One is force comparison, one is energy comparison. This is machine learning versus DFT. Then I have 5 minutes. That's okay. Fine. So this is the way we compare. Sure, sir. So this is the way. These are some of the details. I can scheme how many atoms we do, how many classical, how many simulations we do, and one more comment I will give here. So we did the simulation at 600, 700, 800, 900, 1100, 1300. So one of the reviewers asked, when 1300 Kelvin battery may not exist, why you are doing this one? So our idea is not to run the simulation or battery performance whatever in 1300, but at 298 our particle will not move because it is solid. That's why we want to extrapolate. Start from 1300, go back to 600. I will get the straight line. Those from the physical chemistry background they can understand, or even these are the organic and inorganic also. So I wanted the conductivity at 290. That's why I started from 1300. my 1300 dynamics will be much faster as compared to 298. Now I can tell that, okay, if that straight line is coming, then only I can get the 291. Yes, that's how it is working. I thought it should work on that. So what we did, first we analyze the trajectory. So that means this is the complete one. That is only the SiO4. And then you see not only one SiO4, then all SiO4 are going back and forth position. So the last picture is they are going right hand side, left hand side, right hand side, left hand side. That's what I am telling the back and forth. The next one, these are the time scales, how the A, B, C, D oxygens are moving. So sometimes A is going to B position, then next B is coming to the A position. So that's the word I am talking about, orientation or rotation of that anion. Then what it does to the magnesium ion, this is the next one. The dots are magnesium. SiO4 is the anion. So when it rotates, it is actually pushes the magnesium out of its environment, then getting it back. That is the trigger point for the conductivity or for the diffusion of the magnesium ion. So then we wanted to quantify. So that part is the only left over. Now we know there is a different mechanism is going on. Due to polyanions, the magnesium ions are moving, basically affecting diffusion and conductivity. So then there are two concepts, the rotation of anion, which is SiO4, and your diffusion of the cation. Are they correlated? That means if it will rotate faster, then cation will move faster. If it rotates slower, then cation will move slower. Yes, they are. So that's what these are very quick mathematical. Till now I didn't show any equation. Just please let me show this type of equation, otherwise I will be not happy because we use all those equations. And in a simple way, this is called mean square displacement equation. This is the Einstein equation. T equal to infinite, only this equation is valid. That's what I was talking about the time scale. This equation, diffusion equation is only valid when T will be going to infinite. In the whole world, we cannot go to T infinite. But what we have to check, my mean square displacement is better so that I can calculate diffusion coefficient and the conductivity. And how I am calculating? I am calculating from XYZ position changes with the time. So that's what I can do that. So So another also we talk about that orientation. Now you can see the silicon oxygen vector. At T equal to 0, whatever the vector position magnitude. At T equal to some time, it will change its position. Its direction will change. We wanted that angle distribution. It is a little bit of mathematics. If you cannot follow, fine. Later also I can explain you. So that it will be the orientation and this is translational. So these are two correlated ones. Now these are some plots. So first plot is that mean square displacement. Second plot is orientation. So maybe I can skip this part. Now I will directly go to what I did to the temperature. So initial points from here to here, this is my simulated. And the last 2 points are at 290 because my experimental colleague they wanted at 290. Who does experiment at 1300? Now when I see this is called RNS behavior. When I connected this, that's what it is reaching there. So that is my predictor or extrapolated conductivity that side and diffusion coefficient that side. Whenever it is RNS behavior, I can calculate the barrier. What is the diffusion barrier for that type of movement? And finally, so what we did here, we have ionic conductivity, and we have here the tau value. So whatever plot I showed, whenever it is any function is decaying, if I feed that function to any exponential or what is the behavior of that function, then I will get the tau values. What is the rate of decay of that function according to the process? So that's what I am doing. So this is for cobalt and this is for nickel. Now you see the correlation. Whenever conductivity increasing and your rotation is increasing, conductivity increasing. But there it is related, but there is a anomalous behavior. So that it is very also surprising what we saw that it may be at a different temperature because these are the different temperature data. There is some phase transition is occurring. It was not earlier planned. That's what we saw. Maybe we have to study more what exactly happening in those scenarios. But still we have the dependency. Okay, so this is the final slide. So now what I showed you from the trajectory and what I told, can I put in the PPT for a simplified version? So this is the way it is happening. It is a rough sketch. But still, I can show that, okay, whenever it is going back and forth, how it is going for this way. So this is the rotation and this is the translational motion. Okay, so I don't have time. So I have done with this one, and some of the part, these are for the liquid electrolytes. So here we are talking about lifetime versus the conductivity. That means when two cation anions are coming closer, what will happen to the conductivity? When they are going away, so how much they are staying as a friend, so then that will decide also conductivity. That is another correlation. So maybe that's all from my side. And I am very thankful to Odisha Chemical Society, the convener or organizing team, and OUTR, and this is my research book. And this work done by Rachita, and there are three students from Odisha, and funding our chemistry department and NSM IIT facility for competing. And thank you for attention.
Nice presentation. But before this, let me say, whoever is speaking, he is saying that I am speaking to students, all are students, except me. Except the speaker and his direct teacher, all are students, because we are all Gaya Gujarat. What you spoke, we could not understand. We are learning also.
So question.
Yeah.
Actually, it's a nice talk, but I want to get some correction actually. First of all,
what we are using is not at all our first principle calculation, because we have no exact functional. Okay, but what we have missed actually, which are actually called the first principle calculations or ab initio methods. That's Kapil method and CI method, Patamisa method. That I want to just add.
Yeah, I can talk you. Please, let me know. I will come to your place. If you are from Odisha, I will, because within that time I could not cover. So I will be very happy to.
You are starting from that. So first you should mention that ab initio methods are different actually.
Yes, you are right.
Time was right. I have a question. Yes.
What about impurity? It's an ideal system we are dealing with. In case of impurity, in real situation, how to handle it?
So, if one experimental colleague can tell me with 100% accuracy that I have 2% impurity, I can add. So I wanted the atomistic details of that impurity, but I don't know, then that's why I cannot do. Suppose whenever this is crystallizing, somebody telling, okay, some amount of, sulfur is there or something.
Sulfate and sodium ion.
There. But
very easy to enter anywhere.
So I just wanted that weight percent or atom percent. If you can tell, I have 2%, I can add there. Yes, it will affect. Because it is 100%.
Again, nobody can say that. Let us say he is starting from ball to atomic level, and the property of ball cannot be set at the atomic level. Can never. And from atomic level, you simulate anything you like. It cannot be. You cannot make an experiment.
Based on many
in your picture you showed, let us say you are having a model which is linear model. Then only you can predict. If the model is changed, then you cannot predict at all.
Absolutely.
And you are saying that we can go to 273 by doing 1100. Absolutely wrong, I would say.
Correct.
Because if the model is wrong, then everything. Okay. Question from us.
First of all, very talk. Just for my curiosity, as you are doing classical MD, and in classical MD for biomolecular simulation especially, and we are just doing that ionization by adding sodium ion and that corresponding to chloride ions. Sir, my question is, if when you are doing the material simulation like in labs, especially in case of the magnesium and silica system, and the ionization is doing as such the as like the classical MD system or like something?
No, this is classical. What I showed you, but we develop a method, accuracy of the FD, but it is a complete classical. So we will treat magnesium as the point charge. You take the magnesium and charge this one to +2, and you put another counter charge there. So basically here, as it is the transition metals, and sometimes they do the charge balance there. Not sometimes, every time they will do this one.
So in biomolecular simulation, we are just neutralizing in a sodium and chloride system.
Sure.
Somewhere also they are also using the magnesium and their corresponding anions. So my question is, whenever we are doing the material simulation, if the ionization is doing as such or something different?
No. There is nothing. So it is a closed system. It is not open system. What I mean here, your no transfer of charge or anything is happening to that system. You assume that there is nothing maybe contaminated, something like that. So that means whatever you put, the charge will be the whole system charge. Now you wanted neutral. You wanted positive, add more sodium. You wanted negative, add more chlorine. It will be the whole system. But you wanted neutral, put the equal amount of sodium and equal amount of chlorine. We assume that when chlorine and sodium, because this is the fully dissociated ion pairs. That means you put there, they don't stay as close each other. So that means they are apart. That means overall system will be neutral. But it depends on our requirement whether it will be positive charge or negative. So there is nothing like ionization.
You can modify that.
Same thing.
So thank you. Give a big hand to
thank you.
Thank you, sir. Now I request BK Mr. Sir to felicitate. Now I request Dignitary, Dean Academics, to felicitate Sir BK Mr. Sir.
So next is we have to continue since there is a going in delay 1 hour delay time. Let CPET sponsored PL Naik Memorial Lecture. It will be delivered by Professor Arun K. Nandi, Emeritus Scientist, CSIR, School of Material Science, ISS, Kolkata. It will be chaired by Professor Bulla Behra. I request Professor Behra to please come to the dance. Professor Behera obtained his MSc degree in chemistry from Ravenshaw College, Cuttack, 1965, and a PhD degree in chemistry from IIT Kanpur in 1970 in spectroscopy. He began his teaching career as a lecturer in chemistry at Inaugural College and was there for a short period. After completion of PhD, he joined as a lecturer in chemistry at Sambalpur University in the year 1971. Its book Experimental Physical Chemistry was highly acclaimed and was awarded one of the best 5 textbooks in chemistry in the 6th World Book Fair 1983. The book was recommended by UGC as a textbook for all Indian universities. He has successfully guided 10 PhD scholars and several MPhil and MSc students. After his superannuation, he was a visiting professor in different universities, including Utkal, Parampur, Vaivati, and Sambalpur University. He has published 41 research papers in journals of national and international repute. He was awarded Best Teacher Award in Chemistry by Orissa Chemical Society in 2000. Sir, now I request Professor Behera to please chair the session. Let the issue be solved here. We don't have to go for any break.
I know Professor Acharya. I never expected to start here and say something, but I was happy when he invited me to preside over the function. Well, this is Professor P.L. Naik Memorial Lecture. So I would like to tell a little bit about Professor P.L. Naik, his achievements, etc. Professor P.L. Naik was my teacher in MSc at Revensa. A nice, handsome young man, teaches well. He did research with Professor M.K. Rao, published many papers, maybe more than 100, 200 papers, and guided a number of MPhil and PhD students. As a man, he is very nice. He had been to America for higher studies. He was a good teacher. And what else I should say? That he started polymer science in Orissa. Lot of work, lot of publications in foreign journals. I am doing research at IIT Kanpur. I used to come after some papers of Professor Naik, and I was really happy that he initiated polymer research in Orissa. A number of students are guided by him. Anyway, he is a noble soul. At least he was very good to me. I was not his student, just in MSc he taught me organic chemistry. Now, in honor of Professor P.L. Naik, I would like to request Professor Arun Kumar Nandi to deliver a memorial lecture. Professor Arun Kumar Nandi is currently an emeritus faculty of School of Material Sciences, ISCS, Kolkata. Professor Nandi received his MSc from Bardhaman University in 1977 and PhD from ISS. Okay. Okay, so it won't do any, okay? PhD from Jadavpur University in thermodynamics of polymer and polymer solvent mixing, Professor S.L. Bhattacharya and P.M. Modi, and postdoctoral doctorate from Institute of Molecular Biophysics, Florida State University, USA. He was a recipient of MRSI bronze medal, M. Santama Award in Polymer Science, the Society for Polymer Science India, 2004. CRSI bronze medal, Chemical Research Society of India, 2006. Professor J.N. Mukherjee Memorial Award, Indian Chemical Society, 2015. In 2012, American Chemical Society honored him as one among 20 to 30 highlighted Indian authors published high quality research in SS journals. He has supervised 37 PhDs and co-authored more than 250 publications. It is a pleasure to listen to Professor Nandi, and I invite Professor Nandi to deliver.
Okay, I first thank the organizer, particularly Professor Acharya, for inviting me to give a memorial lecture under the name of Professor P.L. Nair. Anyway, it was written in the letter that we have to talk on synthesis of polymers. So I shall try to give an idea how I can synthesize various polymers from a polythiazine chain by grafting it from there. So grafting, I think we can physically imagine from the banyan tree. The shoots coming from the branches of banyan trees is very much analogous to grafting in polymer chains. So this is the grafting, okay. So grafting, this is the polythiazine chain, and this red one, I make it for one chain and the blue one for another chain, so that a block is formed. So what I want to tell here is the grafting of block copolymers. That is, we can first, we can prepare both by two ways. That is, directly from the polythiazine chain we can go, we can grow the chain, or we can repolymerize the block polymer and then graft on it. So these are very similar to the grafting of small trees from the branches of the trees to get high yielding crop. And also this is very similar to natural graft when grafting from natural graft, as like from the branches of the banyan trees. If you visit the botanical garden, say banyan tree which is more than 300 years old. So this is the introduction. Now, why I choose this problem in this system is that it is a immunoscientist project scheme. We thought that we can interpolate the conjugation length by changing the pH of the animated graft components, so that it will be pH dependent, and when they are strongly ionic, they will repel each other, and the polythiazine chain will then be elongated, and therefore the conjugation length will increase, and also therefore the band gap will increase. And the red and blue chains are representative of two polymers. One will be thermoresponsive, another will be responsive. So it will create a lot of materials by regulating the temperature and pH of the system if you can graft these polymers from the chain. So we have used both this technique as a grafting form and grafting tool to obtain our derived system. Why we use polytherapy? Polytherapy is very important conducting polymer for its unique property, because unique optoelectronic property, but still is quite insoluble, and so we have to make it functionalize, and functionalization, then it will be soluble, and then we can use operating properties or different applications. This is the, and in this figure, we have done a lot of work since 2013. Single polymer was made first, and we made a review. First, it was published in 2018. We were students, and again, like we should write a review on polytherapy. So in 2024, I had written another one, including some peptide linkages attached to the polymer. So in this, we started our work, but when we are talking about these things, that we will search literature that if anyone done this type of things, and it is we found only one work by Abdullah et al. Who made that to polymerize the reactive substrate polytherapy by cyclic voltammetry on ideal surface, followed by polymerization with methyl methacrylate to get this PTG block polystyrene. And this is published in 2011. And later on, they also made another with the same technique with polystyrene and polymethyl acrylate by this adaptation technique. But they have not reported enough qualitative properties. So this is an important field, we thought, and we did the project with this idea to work there. Now, I first did the grafting technique, and the grafting is the process. That means you can separately make the block of polymer and graft on the polyethylene chain. So for this purpose, we make a polyethanol, and we procyanate it, make it block it by TS group, procyanate group, and then polymerize with phenol chloride to get the polymer, polymer, and then we replace with azide to make the azide group. So now it is suitable for coupling with reaction. So we made an ion substituted alcohol. We use and you say that for caprolactone with phenolphthalein catalyst, we can produce the polycaprolactone with ion. And this is then made reagent, BIB, bromide, so bromide. So this is bromine is there. So with this, we make the HRP reaction, and this is the with DNA, dimethyl ammonium methacrylate, which is a peak sensitive polymer. So we can make these polymers for three polymer, pre-graft polymer, block polymer we have produced. Then we have coupled poly A plus poly B by the peak reaction using CPR peptide ligand system in PHF. So we have characterized them by NMR. From the NMR analysis, we have found that about 13 caprolactone unit is degree of polymerization of caprolactone is 13, and that of DMA is about 33. So, and this all the coupling is also confirmed by NMR for the appearance of the peak at 7.45 ppm assigned to the diagonal ring for bi-coupling. Now we try to study the morphology, and you see that there is good bicellular morphology in the system, because at the surrounding of this black there is white corona, and here also if we increase the pH from 3 to 10 and 3 to 7, you will see vesicle. This is an important thing because here the protonated NCHT group becomes somewhat deprotonated as pK of DNA, ENA is PDMA is 7.5, and so therefore these two polythiophene chain and the collapsed DNA chain along with the caprolactam chain forms the wall of the micelle, all the vesicle and this vesicle surface, as you say, at the see it inside very well, and inside some water is present, and as soon as you dry it, you will see from the vacant space in the microgram. And when you increase the pH more, this there is at pH 10, the outer surface protons get deprotonated and they will form multivesicular aggregates. Now, if we increase, this is from the DNA study, so if we increase the pH, the value of this hydrogen diamide changes increases from 50 nanometer at pH 3 to 60 nanometer at pH 7, and also the case to 164 nanometer at pH 10. The chart is also evident from the determination measurement, where determination drops from 30 to almost 0 at about pH 10. So this proves that the charges are removed from the surface of the object. Now, if you go to optical properties, you see that the absorption property is a boosted. This is the chain is acting like a spring, and at pH 3 it is elongated. So now you just have peak at around 400 nanometer absorption, but as soon as you are increasing the pH, it is 395 nanometers. So it is chain gets somewhat quiet because the repulsion between the ionic charges has decreased, and this is also true for pH 10, and the similar is also case for the fluorescence spectra shown here. Most important thing comes if you measure the conductivities, and conductivities at pH 3 is found to be 4 times higher than that of pH 7 or pH 10. Now it is if you measure the current voltage property, you see that these systems pH 7 and pH 10 all are the IV curve is all are coinciding with the x-axis, that is the voltage axis, and there is no much increase or decrease found here. But when we have increased the scale, we got this one to increase. Rather, pH 3 shows a different phenomena. Here you see that there is a sudden increase in the current with increase in voltage. This is an interesting thing. One thing that it becomes electronic conduction may increase. That is because the repulsion of the pendant dimethyl ammonium group increases the conjugation length, and therefore the band gap decreases, and therefore the current should increase. And that is the only thing. There's so much about 4 order increase in this current is not possible. So we thought it must be the ionic parts are contributing to this conductivity. So that is the organic mixed and ionic and electronic conductivity is present in the system at pH 3. And here the ions are which are flowing is coming from the chloride ion, which are the counter anion of doped NCH3 group by HCl. So there is oblique property also present in the system. Now, since this process is a lot of chemistry is there, so we try to make a grafting form technique by one-pot synthesis of a graft polymer from polythiophene. So this is by this it produces you use 2 polymers. That is one is the DEGBAM, which is temperature responsive, another is the which is pH responsive, and we have been able to synthesize PDMA, and PDMA-3, this PDE-10, PDE-3 block polymer, and also another one where the sequence is changed, that is PDMA-10 and PDMA-3. So the procedure is really complicated, and here we will use this thing. Here we use 3-hydrogenol, and we then attach with the liquid that glycine. Then we make polymerized chloride to get the vacuum inhibitor PI. This PTIs then reacted with Degmap to get this polymer Degmap, and then we must polymerize again in set after 6 hours. We are giving the same pot DNA when this block polymer is with DNA at the last. Same technique has been used there where DNA has been added last. That is, DNA may added is fast, and therefore DNA will come in there fast, and then the red one is DNA is coming fast, and then the Degmap was added after 6 hours, so you get the Degmap, so you will draft from the polyethylene tension directly the block polymer. That is the grafting from technique. And this is the random copolymer we have also synthesized. That is for both the monomer 1:1 ratio, and we got this random copolymer. This is the animal characterization of these polymers, and the molecular weights of the graft polymers has been calculated from situation with the ratio of the respective stimulants of each component with that of PTI, and from there the X1 is calculated, and N0 Degmap and N0 DMMA are the respective monomer, and that of N0 PTI for the monomer. From there even graft was calculated for the the partition of this graft polymer was very much evident from this sick places. This is the green one is called the PTI, and then we turn to the PTI Degmap, and then the blue one, that is after polymerization, the synthesis. So in 6 products left, that means that the emission volume is lower and the molecular weight is higher, as the family in the same principle. And they are also you find in the case the same thing is observed, whereas in the copolymer only peaks are observed, and this is the red one is for the copolymer, and green one is for the PTI, so that also sits to the lower emission volume. Now, polymers have characteristics are given in the table, and here and P1 has 3 DNA and 10 Degmap, whereas P2 has 10 DNA and 3 Degmap. So they have closer proximity. They have DNA means closer proximity to the 10, whereas P1 Degmap is the closer proximity of the PDC. Now the morphology is started. You will see that there is also micelles of P1 and H3, and there at temperature micelles are increases. The flux of the Degmap as a LCSM statement has increased, and there also you will see increase that pH from 7, you will get higher size micelle, and this is also true if we go from which have data side access. And but when you go for the polymer, that is when DNA reactivated, you will get these vesicles morphology. The vesicle is coming because of the fact the PTMA is present directly linked to the PTK. That is, and that's why at the bottom state they will develop some water, and this water will be related in the system, and the interior and the physical surface is produced by the pigment and around the PTK, and therefore we got the physical surface, physical morphology. So this is the way we can get this morphology in the. This is very much well understood from the skin. This is the physical. This is the micellar morphology. First part is the micellar morphology, but that one, if we increase the pH, DNA protons down, and so the DNA chains will collapse and the micellar size increase. And if you increase the temperature, the Tegman chain will collapse, and that will increase the micellar size. And in the P2, the DNA is inside the vesicle, and as soon as you increase the pH, collapsing of PDMA chain is occurring, and this is the if the temperature increase, the collapsing of this chain is occurring, and that will increase the size gradually. We have also found it from the DNA analysis where the data size at pH 3 is much lower, but at pH 710 is much higher, pH 710 is much higher, and there is a jump there. We think that this is for the LCS of the polymer system, this system, and this is gradually increasing. Someone? Same thing. That illustrates systematically how the morphology changes with pH and temperature, and here is the vesicle. Vesicle area is gradually decreasing as we increase the pH. The DNA becomes more neutralized, and therefore you can get the vesicle larger due to collapsing from the outer side, and aggregation occurs. And with increasing temperature also, there is more aggregation coming from the Tegman rate of the scale. So this is the site. From the GLS analysis, you can get the various sizes, and for P2 polymer, you see that I have the lower side at pH 3, but as you increase the size increases, and how also size increases, and this down is coming from the LCS system, and it will take the size 5 minutes. So you take this one, and similarly the other ones. So I'm not studying about absorbance, which are very much dependent on pH, and this is clear. It's also different from P1 and P2, and you will see that there is some shift in the pH, the peak, and also the pH maximum is somewhat of fast decrease, that is induced quenching, and then elevation induced emission at pH 10. At pH 7 there is elevation induced quenching, and at pH 10 elevation induced emission is occurring there in the P2 system and also P3 system. Most important thing comes when the IV plots are shown here, and in the IV plots you will see that there is a certain height in the conductivity in the current and in the ohmic property, and here also the signature of signature of memory is here because the current is stored there, and for P2 the memory is very higher than P1, and for P3 is also memory is higher. But it is intermediate between that of P1 and P2. And as you increase the pH, both memory and the ohmic properties decreases. Now important things are coming. Now here the conductivity is for P1 is 0.2, P2 is 0.25, and P3 is 0.24. But if we increase the pH, conductivity will decrease because the gel becomes, the polythermic gel becomes quiet. We have also measured the photocurrents, and photocurrents, you see that as you make the on or off, that is if you make the on fast, it is increasing very fast, then slowly, and this is also there, and most prominent there is when fast increase followed by slower increase, and this is also true in case of P3. Now if we compare these photocurrent properties, that P2 shows the highest photocurrent efficiency because of the adjacent regions, and at P3 more percent, and therefore electron hole separation occurs very easily, and these photons, the electrons can move very easily through the conjugated chain, showing higher photocurrents. The IOF by IOF is also highest in P2 than in P3. It is higher in P2 than in P1 and P3. So this is the, now we have also calculated the analyzed dissipation through these equations, and we measured the growth and decay times, and the growth and decay times is found to be the lowest for the P2 because this polymer if you get very fast response, the current, the electron hole separation going very fast, so photon current is increasing very rapidly. And this is also what to. Okay. We have also made another procedure to graph polymer, and here also grafting. That is grafting process is applied. We polymerize it with a initiator, trichloethanol initiator, and then coupled with 3-hydrogen acetic acid right there, and we got this copolymer. And this way we measured, and I think we will be very similar. And here all cases we got the physical, and also we have significantly in the absorbance as well as Coulson property and the excitation spectrum. So this is a bimodal memory we observed in the system because of the vesicle surface, inner and outer. The electrons can be stored easily, and electrons can be stored easily in the outer surface as well as the inner surface of the vesicle, in the two bimodal memory. And the ohmic property is also present here, and this is the photosynthetic curves, and if you compare grafting, if you compare this, grafting 2 is better than grafting from, because there are about 80 times increase in the conductivity, here also 72 times in photoconductivity, so grafting on 2 is better, or grafting 2 is better than grafting from technique, and we have these conclusions, and which is represented here, that we have able to synthesize 3 different copolymers, block copolymers from polyethylene using various techniques, showing different properties. And I acknowledge the students. I also written a book, Polymer Functional Graphene, and thank you for that.
Thank you very much. The memorial lecture, there will be no.
Okay. Thank you.
Thank you very much.
I now request Professor Behra to felicitate Professor Nandi. Now I request Professor Das to felicitate Professor Behra. Next session will be to again memorial lecture. I now request Professor Sastra Shamal to chair the session. Professor Shamal joined Odisha Education Service in 1977 as a lecturer in chemistry at MPC College Baripada. After completion of his masters, he obtained his PhD degree from Utkal University in 1985. University in 214. He has over 100 publications, book chapters, topical reviews in major international journals, 15 world US/Korea patents. He served as the principal Sasibhushan Rath Government Autonomous Women's College, Berhampur, where he retired in 2012. He received the prestigious Justice Rajkishore Das Memorial Award for his contribution to science in 2010 and B.S. Gupta Best Teacher Award from Orissa Chemical Society in 2012. Sir, I now request to please chair the session. And he has to deliver. And the talk will be delivered Professor Gangadhar Sahu Memorial Lecture by Professor T.P. Radhakrishnan. I now request Professor Radhakrishnan, please come to the dais.
Before I introduce Professor Radhakrishnan, let me say a couple of words about Professor Gangadhar Sahu, who was my research supervisor. I did my PhD with Professor Gangadhar Sahu. May I now request Professor Radhakrishnan to kindly come here and introduce. Let me introduce you. He is Professor Gangadhar Sahu, and the memory of this memorial lecture. So Dr. Sahu did his MSc and PhD, MSc from Ravenshaw College and PhD in Physical Chemistry from the University of Patna, working under the guidance of Professor Balabhadra Prasad. He started his career in JM College, then Ravenshaw College, Then he was the principal in Bhadrak College. He was also the first regional director of Eastern Zone of Indira Gandhi National Open University. He is well known for his extraordinary administrative acumen, unparalleled leadership, qualities, courage, dynamism, and he is extremely brilliant teacher, extremely brilliant, very meticulous and very systematic teacher. Under his guidance, I learned less science, more administration, and how to guard public property, to be very accurate in maintaining financial profiles of any institution. So I am really fortunate that I am asked to chair this session. And before we go ahead with the proceedings, let me briefly introduce Professor Radhakrishnan. Professor Radhakrishnan is currently a senior professor at the University of Hyderabad. He completed his MSc at IIT Madras and received his PhD degree from Princeton University, USA. He was a postdoctoral fellow at the University of Texas. Then he joined the University of Hyderabad as a lecturer. His research interests involved design and synthesis of novel molecular materials of interest, molecular crystals, nanocrystals, nanoparticles, ultra-thin LB films, polymer metal nanocomposite thin films, optical, nonlinear, optical, optoelectronic materials, material structure function correlations. Professor Radhakrishnan has more than 50 publications in highly reputed international journals and more than 5,000 citations with a high index of 39. He is recognized with various highly prestigious awards such as the J.C. Bose National Fellowship, Silver Medal of Chemical Research Society of India, Ramanna Fellowship of the Department of Science and Technology. With these words, let us give a welcome to Professor Radhakrishnan to start his lecture.
Since we are 1.5 hours late almost as per our schedule, so it was decided that oral presentation which are scheduled for today, that is OP1 to OP15, it will be shifted to tomorrow. OP1 to OP15, their presentation schedule is shifted to tomorrow. Okay. Tomorrow during that same oral presentation time.
Thank you, Chairman. Good afternoon or good evening to all of you. It's a great pleasure to be here at OUTR. Let me thank Professor Acharya for the invitation. And it's a great privilege to be giving this memorial lecture. I read a little bit about Professor Gangadhar Sahu. Nice that his student is chairing the session. I read a nice blog by his daughter, Deepika Sahu, which was a very touching one and gave a lot of insight into the great man that he was. An extraordinary teacher, a great human being. So I am delighted to be giving this lecture today. So I'll talk about chemistry, and being a materials chemistry conference, and I've been a practitioner of materials chemistry, it will deal with materials. And I'll give several data and results and so on, but the thrust of the talk is to give certain concepts, because we believe that the research should focus on developing ideas. Data and details are secondary. So the ideas that I will talk about is the in situ chemistry inside thin films to fabricate materials, and a couple of concepts that we have developed. One is called dip catalyst, and very recently something we have named as electrodes. So being a materials chemistry conference, to highlight the importance of materials, I use this slide in most of my talks. The story of civilization is essentially the story of materials, because even in history books, people define the various eras of civilization based on the material that people used, obviously, stone, wood, or copper or alloys, and so on. And it continues, obviously. We call the silicon age and talk about the carbon age which is coming. And interestingly, there is certain cyclicity to the whole thing. Seems like the Stone Age and Silicon Age are not too different in terms of chemistry. And so also wood and carbon. So essentially the materials define our civilization. So it's sort of intimately connected to our day-to-day life. And materials obviously come in very many forms. We have excellent talks already about various kinds of them, polymers and gels and so on and so forth, and electrochemical materials. So in Hyderabad, we have been working on molecular materials for a long time, molecular crystals, molecular thin films and so on. And we have worked on various aspects of it, which I am not going to talk about today, but just for students and people who are not familiar with our group. So we worked on dipolar molecules, looking at nonlinear optical systems, developing the idea of crystallinity and amorphous nature of solids, looking at highly fluorescent solid state materials, using them in variety of problems like imaging and things like that. So this is a topic that I am not talking about today. So today I will talk about basically materials in different forms. Polymers, of course, is an extremely versatile field, as the previous talk also showed. And combining it with metals and semiconductors, you have basically composites. So these two are extremely different types of materials. If one looks at their general properties, in general, metals are hard, many of them electrically conducting. Polymers, on the contrary, are exactly the opposite in very many different ways. So if you want to sort of marry these two extremes, one obvious way is to take the metals and semiconductors in the form of nanoparticles, polymer as a thin film, and then you get into the nanocomposite thin films. And these are extremely versatile because you can try to exploit various mutualistic effects between the polymer and the metal or the semiconductor and their unique properties, each unique in their own ways. So the outline of my talk is basically about these nanocomposite thin films. The methodology we developed, a very extremely simple method, has become quite popular in the field, the in situ fabrication, and there are very many unique things that you can do with them. And just give a flavor of a couple of interesting applications they have in optical and sensing things. And that's on go on to focus on this idea what we have developed, what is called dip catalyst. And the last one we will wind up with the idea of using the electrocatalysis, and that is where the idea of electrodes come in. Basically gel coated electrodes. Just a fancy name, but sometimes it's worth to give names, as we were told in the morning. Names are important. So the in situ fabrication started, actually this work we started sometime long ago, nearly 20 years back, aiming at a totally different goal. The idea was to grow some crystals, molecules, some ionic crystals, ionic conductors and so on inside polymer films. And this was done by my student at that time, Shatabdi, who is now a principal scientist at HCL Pune. So we basically mixed silver nitrate. The idea was to make silver iodide actually at that time, later on inside PVA, to look at ionic conductivity issues. But when she mixed the silver nitrate and PVA, was chosen as a convenient polymer, and spin coated and heated it, it turned yellow. And somewhere around those days, there was the boom of nanotechnology, nanomaterials and so on. So I've read somewhere that silver nanoparticles are yellow in color if you have the right size, because of the complementary absorption of ultraviolet or blue light. And indeed, if you take the absorption spectrum of the film before heating and after heating, just about 60 minutes, you see the very nice plasmon peak coming up. So this was the beginning of this whole thing. It was not a planned one, but accidental one. We did not have an electron microscope at that time, so we had to collaborate with people in CCMB, Hyderabad, who had a good team. And the basic chemistry is very simple. It's the tolerance chemistry that we do in BSc and MSc labs. If you take something like silver nitrate, add a reducing agent, you get silver atoms. And if you have good stabilizing materials around, then it would be formed as nanoparticles. And polyvinyl alcohol is both. It's a good reducing agent because of the hydroxy groups, and it is a polymer with good coating capability. So it happened to be for tutors that we used it. So nanocomposite thin films can be made in many different ways. One is to make the nanoparticles, take the polymer, mix them and coat them, or do layer by layer assembly and more expensive methods like plasma deposition and so on. So in situ synthesis turns out to be an extremely simple, and we are doing actually chemistry within the polymer film. So the concept is very simple. This is the general idea. This is, let's say, cross section of the polymer film. You introduce the metal ion by just mixing aqueous solutions and spin coating, and then you provide energy in the form of heat, or it could be light. We have done all these different things. So essentially, if there are right functional groups on the polymer to reduce the metal ion, then it would reduce it to the atoms, and given some thermal energy for diffusion is somewhere near the glass transition temperature of the polymer, then they will diffuse and form particles. So this is the essential idea, and very parallel one can be developed for semiconductor nanoparticles also, which I am not showing. You can do the very similar things. So this is the first example that we did to make silver nitrate PVA, and you basically get the plasmon peak rising in about, and it's extremely low loading of silver in PVA, as you can see. It's the weight ratio, mild temperatures, aqueous solutions, and you all the green methods, and you get a very tight distribution of particle sizes. So this is widely used, and it's cited quite well, and more importantly, many people have, at least about 100 of these papers have used this method to make these nanocomposites. So I think that idea is much more important than actual system. So this is basically the protocol, just to run through. For practical purposes, we actually coat a polystyrene layer because that can be dissolved, and then you can lift off the actual film of PVA containing the metal precursor. And when you heat it, you see color change. If it is gold chloride, it will be yellow, and when you heat it, it will become sort of pink or violet depending on the concentration. Then you can actually peel it off or actually dissolve the polystyrene, so you get this extremely thin, about 50 to 100 nanometer thick films floating, which you can actually directly put in a TEM and do microscopy. So you actually generate the particles and see it as formed. So that is the advantage of it, and there are various good things about it. And you can do this with variety of metals, and we have published several papers on this. This is another example of palladium, which is extremely important as a catalyst. So we take potassium palladium chloride, PVA, and essentially heat it. And to prove it, of course, you do a fair amount of microscopy. So before heating, you get basically some kind of a dendritic kind of growth of these, and upon heating, the morphology doesn't change much. Actually, many of them become thinner wires. But what is interesting is if you look at the electron diffraction of these, you are starting, of course, with the crystalline material of palladium chloride. On heating, you basically get palladium, some unreacted palladium chloride, and the byproduct, which is potassium chloride. So it's essentially simple chemistry happening inside the solid polymer film. So the potassium chloride can be dissolved out, potassium palladium chloride can be dissolved out in cold water, and then you get basically pure palladium PVA film. And you can use it. We'll show some examples of uses later on. You can do a variety of nice, unique things with it. For example, if you take a weakly reducing polymer like PVP, has some strange chemistry which we have proved in the supplementary of this paper and so on. You can actually see this whole process happening under ambient condition over a period of, actually you can say about 36 hours, the plasmon peak of the silver grows, and this is basically the film changing over a period of 2 to 3 days. And I don't know if I can run this, but there is a small film here. Yeah. So it's basically the AFM images taken over almost 24 hours or maybe 10 to 15 hours. So you can actually see the part. This is something that you cannot do in a solution chemistry, but you can easily do in a thin film of a polymer. Yeah. So, and you can modify this in very many different ways. For example, you can make bimetallic films, which is what Keshav did, who is now at Tokyo University as a postdoc. And you can basically make silver PVA, add some palladium chloride, do the right galvanic pair, then you can generate these silver palladium bimetallic films. A lot of microscopy is needed to prove what is going on. Depending on the concentration of the palladium chloride, you can get hollow particles and all kinds of things. Due to the different rates of diffusion of silver and palladium, you get this Kirkendall effect, they call this. And you can also make semiconductor particles. This is an example which we will take up again in the electrochemistry part. So this is again nickel chloride with iron chloride. You can make nickel iron oxide. It's a good electrocatalyst, so that is why we made this. So how we can use it is something that will come up. So there are many unique aspects of this. For example, I already showed you that it's quite versatile. You can use very many different metals, choose the right kind of polymer to reduce it, and you can make very unusual materials. For example, mercury nanoparticles. You hear a lot about silver, copper, gold, metal oxide nanoparticles, but mercury nanoparticles, there are not many. In fact, many of them are made inside glasses by capillary effect and things like that. But here, you can take mercurous nitrate or mercuric nitrate also works with PVA, and then you heat it. Yeah, basically the plasmon spectrum. This is actually the plasmon peak of mercury, which is computed a long time back. So it's right in the place. And in electron microscope, by cooling it to -120, you can freeze them into nanocrystals, see the diffraction pattern and make sure it is indeed mercury crystal. And here again, if you do this at room temperature, you can actually see the mercury nanodrops. Yeah, mercury is evaporating. Yeah. So at room temperature it will disappear. But if you keep it at cold, then you can do electron diffraction and so on. But if you just keep it at room temperature in a closed vessel, it stays almost for a year. This is under electron beam that they evaporate. And what is the use of this? The nice thing is the famous particle size dependence of melting temperature. In gold, for example, it's very well recorded. When you go to low, extremely small particle sizes, it goes well below the melting point of bulk gold. And this follows the Gibbs-Thomson equation, which you can actually show. In this case, using a single experiment. It's a long experiment in an electron microscope. You continuously heat the film from low temperature up to ambient temperature and keep checking the particles, and when the diffraction disappears, you know that it has gone from the crystalline state to the molten state. And it fits nicely the Gibbs-Thomson equation. So these are nice things which you can do only with this chemistry inside a polymer film. And others have done this work from some other group. You can do electron beam writing of wires, but they do exactly the same chemistry. This paper was published a few years after we published this silver nitrate PV, and they did exactly the same thing. Electron beam lithography and some other examples I will show as we go along. And there are a lot of applications you can develop. This is the first one which we did in that first paper we published in 2005. So this is basically nonlinear optics, where you can do optical limiting, because metal nanoparticles are good optical limiters. When you go to high flux of laser, they get this absorption, excited state absorption, various phenomena which will cause it to cut off. It goes away from the Beer-Lambert's law. So you can, this kind of similar thing, this is a group from Japan who used the same silver PVA, doped a little bit of rhodamin, and created what they call a random laser within the polymer cavity. So there are a lot of things one can do with this. And you can do Raman scattering, SERS. As an example, we use the silver with some, it's a sort of a copolymer, this PVVV, which allows you to grow slightly bigger silver nanoparticles. So if you do analyte solution on a plain glass plate, you get very weak signal. But if you coat it with this polymer film containing silver nanoparticles, then you get very strong SERS effect. And you can see these SERS effects. And you can make it very sensitive using silver gold alloy. But again, we were looking for unique uses of this technique. And one is that you can actually coat this film inside a capillary, ordinary melting point capillary. You just dip it in a solution, it sucks up the silver nitrate PVA, heat it in a furnace, it converts into silver PVA, and then you can take a cross-sectional SEM to prove it. And then you just take the analyte solution in that, put it under the laser beam, and you can record a Raman spectrum. And to prove that it is indeed coming from, so this basically that experiment is showing when you focus the laser beam here, you get strong signal, here no signal. When it focuses here again, its signal will come. Proving that indeed it is the solution which is absorbed on the silver PVV film or PVA film here that gives you the Raman signal. So you can make chemical sensors, which was done by Ramesh, where you again use the galvanic reaction between silver and mercurous or mercuric or even alloying with mercury to cause the plasmon peak to decay, and then you can quantify this and make a good, you can get a very nice linear correlation of the relative change in the absorbance due to the plasmon and the mercury concentration at the ppb levels. So I am running through this quickly because I wanted to come to the dip catalyst. So there are many things you can do. So this is the other idea that we developed, because as all of us know, these nanoparticles, because of the high surface to volume ratio, have very good, are very useful in catalysis. But then there are some basic questions which arise. In catalysis, of course, if you have the nanoparticles, you have large surface to volume ratio, so they are almost molecule-like and therefore highly efficient. Therefore, they are excellent homogeneous catalysts. You can also immobilize them in a matrix, and then you can reuse them, so you can get the advantages of heterogeneous catalysis. So you can actually harmonize these two homogeneous and heterogeneous traits of catalyst if you are able to use the nanoparticles. However, there are problems, recycling issues. If in principle a catalyst can go on forever, but in practice all kinds of poisoning, loss during recovery, all kinds of issues do happen. So for example, recovery normally it is done, you have to do some filtration, magnetic separation, there are various tricks people use to get the catalyst out. So, but in all of them you have always, every cycle you will be losing 10%, 20%, 30% of the catalyst. So what about mechanical separation? So the idea is very simple. Suppose you have a reaction system, you have a film, the catalyst inside the film, you drop it into that, and then the reaction runs, then you pick it out, and then you recycle it. So it's almost a trivial thing to say. Hari did this experiment in the, again now quite a long time back. So we made a thick film. For this purpose, we want a freestanding film which you can actually handle. So we made a multi-layer structure. The reason will be obvious as we go along. So this film has actually a thick PVA middle layer and some silver PVA on the top and bottom at both sides. So you get a lot more catalytically active area. So this is actually how a film looks like. You can do cross-sectional TEM to prove what you're talking about. And as a prototype reaction, we looked at the nitrophenol reduction, which is it's like the Drosophila of catalysis. So you basically put the film inside the cuvette and then you run the reaction. So the solution is basically nitrophenolate plus borohydride in water, and the catalyst is the silver which is inside the yellow film, and then you can do in situ monitoring of the reaction by putting it in, everything inside a UV visible spectrometer. You take the spectrum, the plasmon, sorry, this is the peak due to the nitrophenolate, nothing to do with the plasmon, because the plasmon peaks will not come in interference because they are not in the beam, they are outside the beam. So this is basically the solution spectrum, and you can see the pseudo first order kinetics of the change, and these are all well known. So what is new here? The new thing is that if my student removed the film, then the reaction stops. So if you just took out the film after some 200 seconds, the reaction doesn't proceed. The absorbance of the solution doesn't change. If you put it back, then it continues with the same rate constant. So this is why we call it a dip catalyst. Now this is, obviously you can do a lot of recycling just as a schematic. You introduce the film, you run the reaction, then you just take it out, wash, dry, and then put it back. So just to prove the point, this reaction, there was a report of 20 cycles, so we did 30, just to prove that you can go beyond. And still the yield is still pretty good. So that means you can create a large turnover number. It's the same catalyst particles, same material. Of course, you have to make sure there is no leaching. And how do you do that? You can look at the plasmon peak of this film. You take snip of a small piece of the film, do the electron plasma absorption, or you do the electron microscopy and see what happens to the particle. After every 5 cycles we were doing it to prove that okay, things are pretty much okay. Some slight aggregation does happen, but not very, and you can see that it is actually due to the swelling of the film. This is an atomic force microscope image to see how much the film is swelling when it is put in the aqueous medium, and this is sort of a model which explains why this works. So this is the 3-layer structure that I mentioned. So molecules have a lot of access through the swollen. PVA is a reasonably hydrogel kind of material. It can swell in the water, so it gives a lot of access for the reactants to go in and products to come out. And to prove a useful reaction, we also did the palladium catalyzed Suzuki reaction and showed again fairly large turnover number you can generate with this. And this again, a lot of people have utilized this. This is a paper from a group in Portugal who developed what they call a dip catalyst reactor using some Schlenk kind of setup. And this was very pleasing. Very recently I saw a paper from some unknown admirer of this work who wrote that the dip catalyst is an extremely, we used some very nice words by the way. So it was very pleasant to see this kind of a thing from some unknown group in China. They have also used a dip catalyst. And this has caught on at least in a small community, as this data shows from the SciFinder. Over the period of last more than 10 years, 15 years, almost these are the papers which have dip catalyst in the title. So that means they were actually developing this and also quoting the work. So now that is the regular chemical catalysis. So again, by sort of some sheer accidental thing, one of my students tried to use this on an electrode because one of my other postdocs was doing some water splitting reaction with cerium oxide and so on. So my student put some polymers on top of it, and then she came and showed me there is some water splitting happening. I said, no, this is an insulating polymer, it cannot do this. Then Divya was the student who did this. So she had made this nickel iron oxide combination. Actually, this was optimized after some effort. I think she initially made nickel oxide, and it does show fairly good this oxygen evolution reaction. It shows, these are all well-known catalysts, well-known processes, everything is known. But what is interesting is that by by modifying the nickel iron ratio, you can get a decent overpotential. So this was just the beginning of this whole thing. But you can get a decent overpotential, nothing extraordinary here. But what was important is that it's an insulating polymer, and therefore why it would allow any electron exchange onto the electrode. So basically the electrode is essentially an ITO plate, or it could be a nickel foam, any conducting material, on which we coat the polymer with some metal oxide precursor like nickel chloride or something, and when you heat it, it generates the nickel oxide particles inside. And that film is just dipped into water and you apply the potential and do the LSD and all. But what was interesting is, again, we did different reactions. Hydrogen evolution is the normal course of process with the ruthenium oxide, again well-known catalyst for this. But the important lesson that we learned from here is that if you choose the polymer, we took different polymers, and it is critically depending on the swelling ratio of the polymer. So if you increase the swelling ratio is actually decreasing to the right, then you see the overpotential is rising. It's the same catalyst. In fact, we made sure the catalyst composition, loading, everything is identical. So the polymer has an important role here. So essentially what it means is that the polymer swells. So basically the aqueous electrolyte gets actually confined in the polymer. This is our working hypothesis. And a few more advantages which we have proved over a period of time. So the overpotential and the swelling have a reverse correlation, inverse correlation. So more recently, this is my student who is still there and the previous postdoc. So we looked at some chitosan is again a good hydrogel material. So you can use practically any kind of catalyst. This is a Prussian blue based catalyst, and it does work. And here one more interesting thing came up. If you use a simple naphthalene as a binder, which is the most conventional, commonly used one, the same catalyst, if you do a lot of OER cycles, you see the overpotential pretty much remains the same. It's slightly decreasing, but then at some point it starts getting worse. But with the chitosan, after around up to about 3,000 cycles, it continuously goes down. And then it sort of becomes steady. It doesn't improve anymore. But it does come down. And for this, we had to do a lot of control experiments to prove what was going on. Actually, the morphology changes. Yeah, if I remember it correctly, this is the after cycle. This is after forming the chitosan sample composite film. But if you go on cycling, actually their porosity increases. You look at the electrochemically active surface area, it actually increases and sort of becomes constant after some time. And you get a fairly, the green curve is the one with the chitosan polymer. With the Nafion, actually the current decays after a short time. And many things become better by using this insulating but swelling polymers as a sort of a coating. And this is the last experiment that I will show you here. So this is with palladium with another hydrogel polymer, PHEMA, and you simply coat this nickel foam with this material, and then again you get this improved activity as you go along. Here actually the palladium nanoparticle morphology keeps changing with a lot of cycling, and you get fairly good Faraday efficiency and all kinds of steady current in chronoamperometry and things like that. And the last thing that this was the last one, not the previous one. So here we showed that actually there is a lot more to this. It is initially we thought it is simply the confinement of the electrolyte inside the polymer film, which improves the kinetics. The Tafel slopes and so on show that. But here we found one more thing. You can actually go to a fairly high current, because much of the literature on water splitting is confined to 10 to 50 milliampere per centimeter square, which is of no use if you want to scale up things. So you have to go to now what they call industrially relevant 1, 2, 3 ampere per centimeter square kind of current densities. So we took that as a challenge. We could not go very high, but we could go up to about 1.5 ampere per centimeter square. And what is interesting here is, this is again, these are the layered hydroxides put in chitosan polymer. But what is important here is this blue and the green one are the ones with the polymer, the chitosan polymer, and the other ones are the controls. And actually you can see the other ones where you don't have this hydrogel polymer, after when the current goes beyond something like 0.7, 0.8 ampere per centimeter square, then they start fluctuating and a lot of disturbance starts happening. And in fact, some of them completely disappear. They cannot be taken up to higher potential, but the other ones. And that means there are several advantages for this composite film. The few of them are listed here. One is, of course, it protects the catalyst against leaching. You need some binder. Nafion works very well, but Nafion is sort of not so hydrophilic. But these are hydrophilic and highly hydrophilic, because hydrogels, water can go inside. And the polymers are, the electrolyte is confined inside, so improves the charge transfer kinetics at the electrode. And finally, one more important thing which is emerging in the electrochemical literature from whatever I read, we are not electrochemists, so we are learning everything on the way, is that in many of the water splitting at least reactions, or wherever there is a gas evolution, the gas bubbles can block the active sites of the catalyst, the catalytic electrocatalytic electrode. And that reduces the efficiency of the whole system. So you need a good gas disposal mechanism. So people have been designing what are called aerophobic electrode surfaces by machining the surface, by coating all kinds of interesting things. The hydrogel seems to work very well. And how do we know this? Of course, we calculate the Faraday efficiency and show that with the hydrogel it is good. And this is what we call the normal electrode, where there is no hydrogel. And again, if the movie works, I don't know this sometimes. Oops. Is there a movie file on this? I think media player will know. Okay, if it doesn't work, I think it's, yeah, it is running, yeah. Oh, it's not running. You can just click on this. Yeah, just run the movie. Okay, sorry, it doesn't work. Anyway, but this is not moving anymore. Okay, that's good enough. Okay, if I could, actually you can see the bubble in the movie, but you can clearly see with the gel electrode, the bubbles are much smaller, and actually the evolution is much quicker if you look at the actual movie. And then you can quantify it by collecting the hydrogen gas over a given period of time. So I'm sorry if I went a little quick because it's late in the day and I didn't want to tax you with too many details, but I hope the message is clear that one can develop these new kinds of ideas. The so-called big catalyst and electrodes are our latest contributions in this. So in conclusion, these can be developed by chemistry inside a polymer film. You can do this dip catalyst and all these nice electrodes. So let me acknowledge all the students and postdocs who worked on it. Anu is still working on her PhD program. Some collaboration from Professor Vijay Mohan Pillai. I'm learning electrochemistry from all the electrochemists in the country. On and off, I call them up and try to learn whatever I can. And these were the funding agencies. And before I close, this is the contract with the publisher. So this is a textbook published by RSC 2 years back, the textbook on materials chemistry. Being a conference on materials chemistry, I thought it would be relevant. Thank you for your attention.
Professor Radhakrishnan, my guide was a very good teacher, and I'm sure you are also a very good teacher. So, as it is the memorial lecture, there will be no questions, but I strongly encourage the students to interact with Professor Radhakrishnan during dinner time. Thank you very much, sir. Thank you.
The next lecture is again another memorial lecture. It will be presented by Dr. Sandeep Basu, but before that, may I have the pictures, please? Sir,
in the screen.
Okay, that's the screen. And can we have Dr. Basu, please? Before we start the memorial lecture, let me introduce
the audience, Professor Ishar Mohanty. Professor Mohanty is a brilliant professor and researcher. Did his MSc and PhD, DSc from Banaras Hindu University. Later on, he moved to Cambridge for maybe postdoctoral work. So he served Utkal University Chemistry Department, and he was a great scholar on radiation chemistry. So he had many PhDs on this subject, 32 PhDs, 175 research papers, including papers in Nature. He passed away at a very young age of around 61. way back in 1982. His students have instituted this memorial lecture. All his students, they have contributed for Orissa Chemical Society having this memorial lecture since now. So I'll now introduce the speaker, Dr. Sandeep Basu. He is currently working as head Radiation Medicine Center and Dean Academic Medical Health Sciences BARC, Bhava Atomic Research Center. He has completed nuclear medicine course for doctors and MSc Nuclear Medicine and Molecular Imaging Technology and MSc Hospital Radiopharmacy courses for science graduates at the Radiation Medicine Center aimed at developing training manpower in the field of nuclear medicine. His area of expertise involves clinical nuclear medicine, PET, radionuclide, nuclei, theranostics and therapy. He has more than 500 peer-reviewed publications and 40 book chapters. He has been recognized with Sati Swarup Bhatnagar Prize in Medical Sciences, Department of Atomic Energy Homi Bhabha Science and Technology Award, Homi Bhabha Memorial Oration by the Society of Nuclear Medicine, Alavi Mandal Award from Society of Nuclear Medicine USA, and Department of Atomic Energy Scientific and Technical Excellence Award. So with this brief introduction, let us welcome Professor Basu for the memorial lecture. Professor Basu, please.
Thank you. At the outset, I would like to thank the Orissa Chemical Society, particularly Professor Acharya, to give me this opportunity to invite me and deliver this presentation. Professor Mohanty, on his name, this lecture is instituted. We already heard about him. He was a remarkable man, and his particular fascination was radiochemistry, based upon which I just chose where are the areas that we in the clinical areas we are using radiopharmacy and radiochemistry in a big way. So in my lecture, first we will see very briefly on a bit on the workflow and functioning of a nuclear medicine department, how radiopharmaceuticals are used, and the major developments in radiochemistry and radiopharmaceuticals over the last 15 to 20 years, and some major clinical applications in cancer and the developments in India with indigenous developments. So just to show you the institute that I belong to, this is Radiation Medicine Center, which is Tata Hospital's annex building. The first 5 floors are nuclear medicine department, and the primary job that we do is patient service, human resource development. As he mentioned, we have our MD program, we have our MSc nuclear medicine NMMIT program, but very importantly, over the last 2-3 years, MSc Hospital Radiopharmacy and Radiochemistry program has been instituted as the first program in India, and of course research, basic and clinical, bench to bed, including clinical translation of radiopharmaceuticals. So with 3 pronged approaches, we work here at Radiation Medicine Center. And this is one remarkable letter in 1962 which Homi Bhabha wrote when he invited Dr. Gigi Boy, who was the first head of Radiation Medicine Center, to open up a nuclear medicine center. And there he mentioned that we are at present expanding the medical division very substantially. The Tata Memorial Center and Indian Cancer Research Center has been transferred to the administrative control of Department of Atomic Energy, and steps have already been taken to set up a nuclear medicine center in a portion of the Tata Memorial Hospital. This will be enlarged in due course into a large center for the whole country and housed in its own building. The interest of our users or the public, we are also interested in promoting the uses of isotopes in medicine for research, clinical investigations and therapy. And with this, the Radiation Medicine Center grew with Dr. Gigi Boy as the first head of Radiation Medicine Center. And over the last 25 years, I am there at this center, and what we do is we are regularly in touch. So as I told you, the 5 floors are Radiation Medicine Center, and the rest of the part is again Tata Hospital. This is the rest of the Tata Hospital, and of course we are regularly in touch with BRC and BRIT with the radiochemist on a regular basis for uses of radiopharmaceuticals for cancer diagnosis and treatment. So this is the current workflow we have. So we have an OPD service, then clinical panel of doctors, postgraduate doctors, then we have this diagnostic imaging and PET CT and SPECT. We have the lab, thyroid, where radioimmunoassay and IRMA are being used. Medical cyclotron is a very, very important one where radiochemists play a role in our branch, and we have it at the basement of that Radiation Medicine Center, where regularly the PET radioisotopes and radiopharmaceuticals are being produced. So the first cyclotron of India at Radiation Medicine Center was instituted in 2002. Today we have around some time back 24 medical cyclotrons in the country, which supplies the PET radiopharmaceuticals in different nuclear medicine units in different hospitals. This is just an example of the PET CT scanner that we have. This is the PET CT, so the CT gantry is there, PET gantry. So one of the major development over the last 20 years is what we know as hybrid imaging or fusion imaging in medicine. So what is it? We only had PET, and now we always combine this with CT. So what does CT do? CT does a kind of a thing called mu map, and attenuation correction factor is generated. So you have a combined PET CT imaging. So PET gives a high sensitivity, whereas CT gives a very good analyticals. And 2010 to 2020 was more where a lot of therapeutic radiopharmaceuticals came into. So therapeutic radiochemistry grew in a big way. And if we see the national stats, which I have written down, we have around 490, nearing 500 PET CT centers, nuclear medicine departments 544. So something which was 8-9 in 2008, today the country has nearly 550. So such has been a major growth, and I will ascribe to this major growth of this nuclear medicine branch to the radiochemistry growth. And again, as to tell today, in any cancer hospital, PET CT is a mandatory thing, and as I told you, it grew primarily during the first half of 2000 to 2010. Just to show you the radiopharmaceuticals that we use, when 2003-04 we started the PET scans at our center, we were only using this FDG. Until maybe 5 years back, FDG was the major one. So roughly, I would tell roughly around 80 to 90% of PET scans were with FDG. And just to show you the number of agents that grew, 2011-12 we had this gallium DOTA tape. Gallium DOTA is your bifunctional chelates and tape. This is somatostatin receptor targeting tumors are targeted by this. For prostate cancer imaging, we started gallium PSMA 11, and then just post-COVID, if I have to see at our center today, we do 10 types of PET scans. 6 to 10 is the number. Copper chloride, gallium nonaga RGD, which is angiogenesis stressor, then FAPI, which is fibroblast activated protein inhibitor, then pentixafor, and then exentin for different malignancies. So just to tell you what kind of a growth that this branch has, that from 2020 to 2024 we have added up 5 new PET scans at our center with different developments. Most of them are indigenously produced today in India. And with regard to radionuclide therapy also has come in a very, very big way. The branch, when we were student in 1990s, when we were doing post-graduation at this center, it was only thyroid cancer and radioiodine and mostly diagnostic. Today we have this many treatments with nuclear medicine that are there. Thyroid cancer was there earlier. 2010 we started neuroendocrine tumor with lutetium dotatate. Lutetium is the therapeutic radionuclide which is a beta emitter. Prostate cancer is being treated with lutetium PSMA, bone pain palliation by lutetium ETTFP. And then we also had this indigenous production of yttrium-90 at BRC that we started from 2019, which is neuroendocrine tumor by yttrium-90 for large volume tumors. And then from 2021, we got permission to use alpha agents. Presently, the country does not produce alpha agents. Alpha radionuclides are all imported from Germany or from USA. So actinium-based radiotracer, both for neuroendocrine tumors and prostate cancer. Extremely costly treatment till India produces them. It is even at our government center where everything is subsidized, is 4 to 4.5 lakhs per site. And then we have two new agents for lymphoma and breast cancer. Lutetium dotatreximab for lymphoma and lutetium dotatrastuzumab for breast cancer. So these are the ones we are treating today. Roughly 11 to 12 new treatments that have come up over the last 10 to 15 years. So what is theranostics? Theranostics is nothing that today, it's in very simple terms, you have a lot of side effects in chemotherapy. And what are the major advantages of these radiopharmaceutical therapies? You have targeted treatment. You do a scan and then you use that same ligand, radioligand, use it with a therapeutic radioisotope such as beta, lutetium or yttrium or an alpha agent. Then it goes only targets those agents. So its side effect is the patient's overall tolerability profile is very good with this kind of a theranostic approach. So gradually, these are gradually replacing the toxic chemotherapy as and when this is available. And so this is the production scheme of lutetium which is being used in BRC. So you see the country has a medium flux reactor. So we produce the lutetium 177, which is a major metallic therapeutic radionuclide that is produced by direct route at BRC, and the one that is imported it is through terbium. So at present we use this indigenously production, and this I would consider a major kind of a societal benefit of doing atomic energy research in this country. I can just tell you, if I have to import this lutetium, it is 1.5 lakhs per cycle. Whereas the countries in our our center, we are treating with 15,000. So 1:10 ratio because of indigenous production of lutetium. So such kind of a thing of doing an indigenous atomic energy research in the country. So roughly as we see radiopharmaceutical wise, because of BRC's production, 1:6 to 1:11 ratio. So that is the kind of a thing that we see compared to if we have to import the radioisotope. Yttrium-90 has come from 2019, and we have started using it in large volume tumors, in lymphoma and in neuroendocrine tumors. Alpha radionuclides, as I told, so this has come in a big way. So the cases where beta radionuclide does not work, alpha radionuclide is very useful, and the one that is being used is actinium. So this is what we are including. The other two ones that are coming up in a big way is 223 radium and 211 astatine in different cancer. 212 lead is another one. So this, as I told you, this we don't have it in the country, indigenously produced, and we import on a regular basis. So about the theranostics, two major success that we had, and probably I was very much associated with at our center to develop over the last 14 years, is treating neuroendocrine tumors and prostate cancer in metastatic stage. And this primarily happened because BRC started producing indigenous lutetium from 2009, and 2010 our first patient was treated. So today we have more than 14 years experience, more than 10,000 patients treated at our center, which is probably in this part of the world one of the biggest treated in neuroendocrine tumor, and very good success rate. So So much so that at one time, which was primarily a domain of chemotherapy, is now on a regular basis treated with lutetium dotatate. Neuroendocrine tumor, prostate cancer with lutetium PSMA, we have now 7 years experience. Our first patient went in 2017. And as I told you, lutetium rituximab in lymphoma and trastuzumab, we have just in breast cancer and lymphoma, we have started treatment since 2022 after the just to show you some examples how effective it can be. So this is a patient where gallium dotatate PET-CT has been done, neuroendocrine tumor. You see all these black dots. These are bilobar hepatic metastasis. This is the pancreatic tumor, which is showing up. So it comes back from the GI unit of DMH, telling that this cannot be operated, obviously interpreted. So this is after first cycle of lutetium dotatate and after 3 cycles of lutetium dotatate. So your bilobar liver lesions have gone, only the pancreatic lesion remains, and that makes it operable. So, and again, as I told you, the major advantage compared to these all patients at one time were going for chemotherapy. Today, this entire treatment from chemotherapy has shifted to this radionuclide theranostics. Again, very well tolerated. The patients are themselves their referral source. And such good response that these many of the patients that we have got has gone to near complete curation. Again, just to show you, a lung neuroendocrine tumor, all over spreaded disease before first cycle of PRRT. PRRT is peptide receptor radionuclide therapy, and before first cycle and before third cycle. A very aggressive tumor in rectal neuroendocrine tumor, as you see, extensive disease, pre-treatment and post-treatment. So this kind of a response that we have seen in over 10,000 patients that have been treated in our center over the last 14 years. So just to show you that, you have these ABCDs. What are the things? Equivalent results. So that kind of a thing that we have achieved with equivalent results. So that kind of a thing that we have achieved with this development in radiochemistry. And just to show you that this is our one MD student who published the data of last 10 years experience with 7 years follow-up with 468 patients being treated with this lutetium agent, and the data has been excellent with this indigenous production, similar to what is reported in the literature. The point is the indigenous production of lutetium and this radiopharmaceutical is as equivalent as is imported one. This is just a dosimetry result. I will not go into details, but just to tell you the dosimetry result also. Before any radiopharmaceutical goes for patient trial, we have to do extensive dosimetry. Our health physicist does it, and with this excellent dosimetry, we find the result along with literature, which is very good. The other very important development, I would say, in this chemistry domain is to see, these different radiopharmaceutical tracers. They see they do a very good molecular probing. The example I will take again from neuroendocrine tumor. The tumor, see, you have 10 patients. 10 patients will behave differently, and you can choose. You can do molecular probing with this radiochemistry. So we do regularly somatostatin receptor test PET and glucose PET. So what are the these are the group of tumors when we started in 2000. These are the group of tumors when we started in 2010. It was almost 100% mortality rate, even if when we just treating after 1 or 2 cycles. But using this particular regimen where we use dotatate with chemotherapy. So what happens is when we see this dual tracer positive, so this kind of so it really helps in personalization of treatment. So by doing a good probing of the tumor, so we see the somatostatin receptor expression and glucose expression with FDG and dotatate. So that's how we are doing personalization. And with that result, we now have around 84%, where there is not nearly 100% mortality rate. Today we achieve around 84% good success rate with partial response and stable disease and control of tumors. So that is the kind of an advantage. Again, just to tell that how advantage, yes, it has been this radiochemical probes in tumor treatment. So this is the kind of a regimen that we follow at our center with using dual tracer PET when a neuroendocrine tumor comes for this. This is one neoadjuvant treatment, so same that targeted therapy pre-surgery and post-surgery. So when you have a tumor which encircles more than 180 degrees of the tumor, it becomes inoperable. So can PRRT work there? So there we have used this, and if you see roughly our result is 1/4, so 25% of these patients, which is published in JNM, a respectable journal at our branch. So roughly 1/4 of the patients have shown such a good response. Alpha, when we use, this is one area, yttrium 90 and alpha. So this patient who has shown very good response with lutetium comes back post-COVID time. Again, disease has flared up. This is the time where we are using alpha. As I told you, alpha is now not produced in the country, alpha radionuclides, and it's quite costly, and many of our government institutes, patients cannot afford. There we are using that at the time when it shows resistant to beta agents. So this lutetium-based targeted treatment, we started with NET, but so many other somatostatin receptor targeted tumors show up and are being considered now for this kind of a treatment. Just to show you how we developed this treatment, our first patient went in 2010. We first have to do dosimetry. 2010-11 we did dosimetry. 2011 we started dual tracer PET-CT in our center, and it gradually became routine. 2012 we started clinical application of PRRT in different tumors. We extended it. 2012 we started using dual tracer PET-CT on a regular basis in personalization. 2012-13 we started sandwich chemo PRRT regimen, which I told combined because we are losing those patients. 2014 we started using it in neoadjuvant. 2015 we started carcinoid heart disease. It is also affected because of their chemical substance secretion. 2019 we started low PRRT with yttrium 90. So that is the kind of a thing that we developed with indigenous production of lutetium. ERC's lutetium was available since 2009, and our first patient went in 2010. So that's the kind of a story that we developed for neuroendocrine tumor. In country it is entirely indigenous. America's first lutetium dotated treatment, it's actually India was quite early starter here. They started this treatment in 2018. By that time we had already 8,000, 9,000 patients treated. At our center only, I'm sure with AIMS, PGI, everything, there will be several. So we were very early starter because of country's indigenous production and use, and so many thousands of patients have got benefited. And just last two slides, prostate cancer we have started in 2017. We have covered roughly around 2,000 patients, and this is again a receptor called PSMA receptor, prostate specific membrane antigen, which is highly overexpressed. This is now the third line treatment in metastatic prostate cancer, but I believe with its very well tolerability, it is frequently coming up as the first line or in the second line in metastatic castration resistant, hormone resistant prostate cancer. These are being increasingly considered. Just to show the dosimetry data that we obtained with lutetium PSMA therapy, which has been done during 2017 to 19 by our health physicists. So that's the kind of thing I thought I will share with you regarding regulatory tumor.
Dr. Basu, PET scan saved my life. I was being wrongly diagnosed as a cancer patient by CT scan, but PET scan saved my life. That 18 fluorodeoxyglucose that was injected, and I was declared as cancer free. So I'm extremely delighted that our country is now self-reliant with a growing population and a staggering rate of cancer growth. You have not only a responsibility but you get solution to this. So thank you very much. That's all. Give him a very big hand.
So, sir, I now request Professor Samal to felicitate Professor Basu.
Sir, I have to felicitate you, sir. So I think for today, the technical session is over. Within next 10 minutes, we can start the GP. So we have to start here the GP, and all the live members they will be stay here so that we can discuss the agreement for the GP.
Or 10 minutes after that.
Jenna.
Thank you.